This course covers the foundations and principles of Six Sigma and Lean, along with the value that both of these quality and productivity improvement methodologies bring to an organization. This course also includes the key Lean tools that are used in the typical Six Sigma project, and how Lean and Six Sigma can be integrated into one methodology called Lean Six Sigma. What is Six Sigma? It all begins with an important metric, and that metric is defects per million opportunities, or DPMO. DPMO is a scientific measure and a way to calculate the number of potential mistakes or defects we get when we provide a product or service. This DPMO metric sits inside the organizational system within which Six Sigma operates. The next part of this system is called the improvement methodology, and the phrase for that is called DMAIC, which translates as define, measure, analyze, improve, and control. This improvement methodology, in addition to the metrics, is part of an overall organizational system within which we use Six Sigma to improve business processes of all types. So why Six Sigma? Well, for one reason, there's a definite proven track record. The Six Sigma term was popularized by General Electric and Motorola back in the 1980s and 1990s. But the reality is, Six Sigma has been widely adopted by industry leaders of all kinds in all industries. The Six Sigma basic techniques have been in practice for nearly 100 years. Six Sigma provides a very good toolkit and methodology to accomplish a number of things. Six Sigma is not limited just to manufacturing, which is the industry where it was born. This methodology has been successfully deployed in every kind of business. Profit, nonprofit, government, financial services, and manufacturing are examples of industries that benefit from the application of Six Sigma. There are a number of benefits to any organization from using Six Sigma, and we're going to talk about that next. All industries, whether they are for profit or not, are concerned with operating costs. All organizations must consider revenue now and in the future. So bringing down cost and bringing costs under control is always critical. Six Sigma has been a very effective method to accomplish this by using proven methods to reduce the cost of quality over time. Another key component is driving customer satisfaction. Six Sigma initiatives that are being implemented the right way are focused on the voice of the customer, and also focused on making changes that reduce variation, reduce inefficiencies, and improve quality in our processes. Another benefit to this is that we can improve the net profits and the company's value over time, and that's a good thing. Organizations that are focused on making money now and in the future need to leverage techniques like Six Sigma to ensure long-term success and viability while never losing their focus on the customer. This topic addresses the concept of defects per million opportunities, or DPMO. As we're able to measure and capture data about something, we can begin to chart it and evaluate its relative performance against a goal or a mean measurement. And using the methods for Six Sigma, we would begin to understand, with the use of standard deviations, how our performance compares to that goal with respect to an upper or lower specification limit. Anything outside these limits will not meet the expectation for what it is we're trying to produce and deliver to our customer. The chart includes the mean or goal, while the increments further and further from the mean represent increasing standard deviations. While many operations may set a level of tolerance at 3 standard deviations, plus or minus from the mean, if our process is operating at a level of Six Sigma quality, we are setting a much higher expectation of quality. An operation performing at a level of Six Sigma quality is 99.9997% defect-free, meaning only about 3 defects per million opportunities are expected. What is the difference between an operation where the deliverables are expected to fall within 3 sigma versus an operation that operates at 6 sigma? The difference may surprise you. Here is the difference that Six Sigma makes when an operation is able to limit defects to only 3.4 per million opportunities in its processes. At 3 sigma, this could mean losing 20,000 pieces of mail per hour. But with Six Sigma quality, only 7 pieces of mail are lost, which is a monstrous improvement. What about 5,000 incorrect surgeries per week versus just 1.7? Or outages of electricity of almost 7 hours per month versus a very, very rare 1 hour every 34 years? How about drug prescriptions? 54,000 prescriptions that are wrong is way too many, considering it could be a matter of life and death. Six Sigma quality suggests that it should only happen only once every 25 years. How about landing airplanes? Thankfully, airlines mostly operate at Six Sigma quality today, and as a result, we don't see a lot of airplanes crashing. However, it would happen a lot if they only operated at 3 deviations or 3 sigma in their performance. Six Sigma is very adaptable, and with a little bit of effort, any organization can work toward this level of performance. Six Sigma quality can affect every single industry that we work in, from manufacturing to consulting, profit to nonprofit, government to the private sector. A great application of Six Sigma quality can be evidenced in customer-facing organizations like call centers and contact centers that serve customers. But there is no upper or lower limit in terms of the size or type of organization that can adapt and use Six Sigma successfully. In this topic, we will review the Six Sigma timeline and get an understanding of the evolution of Six Sigma over time. The important Six Sigma term, standard deviation, was defined in the 19th century, but if we go backward in time to the late 1800s, we had Frederick Taylor and Tayloristic thinking. Taylor's economic theory, the division of labor, gave rise to a lot of the things that we would call Six Sigma today. In the 1920s, we had folks like Henry Ford and Walter Short, George Box, and others that were doing development around Six Sigma as we would recognize it today. As you move into the 1940s, there was a big push by the U.S. government to support military manufacturing. This is where the notion of statistical process control really came to the forefront. These included the early teachings of statistician Walter Short, and then after World War II, we had Dr. D. Edwards Deming and Dr. Joseph Juran. Their work in Japan led to the development of quality as a competitive differentiator for the Japanese. It was during this time that the Japan Union of Scientists and Engineers was born and began to create some of the foundation for what we later adopted as Total Quality Management, or TQM. As we moved into the 1970s and early 80s, it was Michael Harry and others working with Motorola and General Electric that crafted and branded the concept of Six Sigma as a term to bundle these methods together. This has all led to the modern day, and Six Sigma being applied in many different industries. Now we will cover some key improvement concepts that have been developed over the years. Back in the early 1920s, there was the plan, do, check, act cycle. Then as we moved into the 1960s and 70s, this led to statistical process control and the formation of the Japan Union of Scientists and Engineers. Then the United States began adopting and embracing Total Quality Management, or TQM, in the 1980s. In that same time frame is when quality circles, developed by the Japanese, began to be well understood. Moving into the late 80s and early 90s, we had the integration of ISO 9000 with Total Quality Management, and the development of the Baldrige criteria for performance excellence. Now we will explore the Plan, Do, Check, Act, or PDCA cycle in more depth. It generally starts with a plan of understanding. What is it that we want to change, and why are we changing it? Then we take action to actually do it, followed by the all-important check step. Sometimes this is actually referred to as study, but it's validating to determine if what we did actually accomplished what we planned. If we don't pass the test in the check step, we would initiate another cycle of PDCA. So PDCA is a cycle of continuous improvement to improve processes. We may implement the PDCA cycle along with statistical process control, where we track data and determine if the number of defects is acceptable or not. Continuing with the theme of total quality management, This evolved in direct response to the increasing competitiveness of Japan in the 70s and 80s, and taking business away from the United States. This was a United States-based initiative around branding total quality, which was a precursor to what we would call Six Sigma today. During the 1990s, we saw the ISO 9000 standards being developed. Quality-focused organizations incorporated ISO 9000 standards in order to win recognition and credibility within their industries and with customers. The Baldrige criteria is another set of standards for performance excellence. The criteria includes 7 important elements. The elements are leadership, strategic planning, customer and market focus, measurement, analysis and knowledge management, human resource focus, process management, and finally, controlling results to create repeatability and capability within the organization. The evolution of Six Sigma as we know it today is largely credited to the work done at Motorola and at General Electric. Michael Harry and many other very prominent quality leaders were involved with that. Their early work led to the worldwide acceptance of Six Sigma as a practical set of methodologies to improve results for any kind of business. In this topic, we will discuss the DMAIC methodology and how that relates to the PDCA cycle. DMAIC is a 5-step process. We start with define. This involves really understanding the issue we're trying to address, determining the outcome we want to accomplish. From there, we need to measure and determine the inputs and the things we can measure and potentially improve. Then we analyze and determine the best actions to implement the next step, which is to improve the process. Then we move on to control. During this step, we make sure we achieve the results. We use that information as an input to the next iteration of the DMAIC process, and we start all over again. In contrast to DMAIC, the Plan, Do, Check, Act, or PDCA cycle is very similar, but a bit simpler. The Plan and Do steps correlate very much with define, measure, and analyze. And then the Check and the Act correspond with improve and control, and making sure that we actually get the result that we're seeking. The similarity is that both of these are intended to be cycles of continuous improvement, and neither is wrong or right. They're just different and helpful to us in the practice of Six Sigma. Now we will discuss the transfer function and how it plays into Six Sigma. And it starts with understanding the meaning of the letter Y in the equation. The Y represents the output, the result, the actual process that we want to improve, or the outcome. The Six Sigma process takes inputs, applies a transformation, and produces outputs. In the function used here, X is the input, F is the transformation applied, and Y is the output. These are the variables that actually contribute to the success of the process. The F, or the function of X, gives you the Y result. Another way of thinking about this is that the X inputs go through the F function of transformation, generating the outputs or the Y value. Now we will talk about the transfer function and how that relates to DMAIC. For example, let's just say we're going to call technical support to address a problem with our computer. This is the define step of DMAIC. When we call, a series of things are going to happen. Let's say that the Y in the transfer function represents how long it takes for you, the customer, to get the answer to your question. Now let's identify the X factors. These are the various steps that would take place through the entire call to resolve the technical question. These also represent the measure step of DMAIC. Once we have all those measures, we move on to analyze and determine which are the critical few factors that make up most of the time, and what is the normal variation of that range of time. Then we determine what we can do to add efficiency and to shorten the amount of time to resolve the customer's issue. Once we've done that, we can move to the improve phase and actually implement the countermeasures and changes. From there, we move to the control step of DMAIC and verify that the Y in the transfer function was improved. If we remember, the Y is how long it takes for the customer to get their answer to their question. Then we measured it with the X's, Then we move through the analysis and the function. We actually improve the value of y by applying the steps of DMAIC. Since this is continuous improvement, we can go through the process repeatedly. This simple 5-step process is very powerful if we're willing to follow the rigor of Six Sigma. There are other improvement methodologies that we can leverage in the practice of Six Sigma. Statistical process control is one of these, in which we have upper and lower control limits. We monitor processes to determine if and when they go out of control, and we use that to trigger root cause analysis and improvement. Statistical process control tools can actually trigger cycles of DMAIC to improve a process. We also have variance and defect reduction tools correlated with total quality management, or TQM. These can be very helpful in analysis and improving processes. This is part of the analyze and improve steps of the DMAIC cycle. Another improvement methodology is teamwork, and the notion of quality circles. This concept was developed by Toyota, and it aimed at a team-based approach to leveraging the DMAIC methodology, along with statistical tools and variance reduction tools like those that we've just discussed. In this topic, we will discuss Six Sigma projects and some of the important things a yellow belt needs to understand. First of all, the typical duration of a Six Sigma project can vary dramatically. They can be very short, just hours, or a few days in the case of a small quality team effort to make an incremental improvement. Or it could take a year or longer to get to the end result. That said, it's pretty typical for Six Sigma projects to run 4 to 8 weeks to gather the data and move through all of the stages of the DMAIC cycle. The contributions of yellow belts are very important as a critical team member working to achieve the results. We have master black belts, or black belts, who actually sit on top of the process and manage the projects. We have green belt level skills with heavy involvement in the analytics and information gathering, analysis, and implementation. Yellow belts are very critical as well, as team members, and those who are providing inputs and support for ongoing implementation. The purpose of various projects varies dramatically, but generally they're going to focus on the following things: reducing the variation of a customer's experience, getting things to market quicker, eliminating errors and mistakes, and finding ways to reduce cost in operating processes. There are some important considerations as you move into implementing Six Sigma. The first and foremost is management buy-in. If you don't have support, sponsorship, and adequate funding, it's kind of a no-go for any significant project. Another thing to recognize is that Six Sigma is not always suitable for every single problem we face. We don't want to have that one-tool mentality where we treat every problem the same way. Also, don't overshoot. Start small and then go bigger as we develop confidence and abilities in the organization. And don't miss the opportunities to innovate and reinvent ways to improve our performance. There are times we don't use Six Sigma. Other methodologies might be in play. They could be business process management projects, business process reengineering, or maybe lean types of projects. We want to make sure we understand what's already going on before we try to introduce Six Sigma. We don't want to bite off more than we can chew. If the scope is too big and we can't break it down to specific outcomes, that could be a roadblock. Other thing to watch out for is when the cost to implement actually outweighs the benefits. For example, if we spent 100 hours working on our project, but we're only going to save 10 hours a year of effort, then maybe that's not something we should be pursuing right now. Another important concept when introducing Six Sigma is the notion of conducting a readiness assessment. We start with defining the outcome that we're seeking. We also need to define clear success factors for the organization and the people involved. How will success be defined for them? Also, do we have reliable data? Do we have the right participants who support success for this project? Then we have to build a solid business case for using Six Sigma. What is the value of the improvement? What is that worth to us as an organization? Who would see that as valuable? Who might resist it that we need to address as part of the process? And do we know what the return on investment would be for implementing these changes? Let's take a deeper dive in assessing organizational readiness. How does the future path compare to the present situation? Are we addressing something the business actually needs now? Are we evaluating current performance? Do we have a strong rationale for applying Six Sigma to our business and to the particular problems that we're trying to solve? And then finally, is something else going on that we need to recognize that could perhaps solve this problem? Is there an alternative solution? Is Six Sigma actually the right thing to use? Only when you've asked all of these questions can you be certain that your organization is ready to implement Six Sigma for a given problem. There are 3 steps that need to be followed to assess organizational readiness. Step 1 is assessing the outlook and the future path. Ask the question, is change a critical business need now? Step 2 is evaluating current performance. Ask the question, is there a strong strategic rationale for applying Six Sigma to our business? Step 3 is reviewing systems and capacity for the change. Ask the question, can existing improvement systems achieve the degree of change needed to keep us successful and competitive without using Six Sigma? In this topic, we will determine what brings value to an organization applying Six Sigma. To get started, let's first consider customer satisfaction. Focusing on the voice of the customer to drive change and improvement in the organization is absolutely critical. And this is where Six Sigma tools to analyze data can be very helpful to understand what customers care about. Six Sigma gives us tools to address the inputs to future strategic planning by addressing marketing effectiveness, how to get things right the first time, and what is it the customers are really interested in with respect to our products and services. A fantastic toolkit in the Six Sigma bag is called Kano. Kano is a way of gathering data from customers and beginning to understand what's important to them that really differentiates us. What are the things that we can do more of that add more satisfaction? And what are the things that they are neutral about or could be dissatisfiers in that product or service that we provide? If we move on now and think about strategic planning, Six Sigma analytics can help us determine the customer satisfaction factors and use these as key inputs to the strategic planning process. We can use Six Sigma to understand key financial drivers within the operations of the organization and where we need to focus our improvements. There are very powerful tools around product and service development that can help us get to market much faster. We want to rigorously examine features and functions that we plan for future products, and then we determine which of those are particularly important to the customer. Then we determine how we're going to incorporate those at the correct level of quality and speed to earn the market share that we really deserve. From an organizational culture perspective, using the rigor of Six Sigma for chartering, developing metrics and controls, and engaging quality circle teams can really drive an organization forward. Profitability is always important, and we need to continue to reduce costs. Six Sigma is very helpful in accomplishing that. Reducing costs of quality is an important aspect in bringing down costs as well, because organizations could be spending as much as 20 to 75% of the cost of sales in just assuring quality in products and services. With increased market share, we continue to work towards shorter product development cycles, being tightly aligned to the customer's needs, and doing everything better and faster than our competitors. Getting introduced to the notion of lean or lean manufacturing in the service sector is all about recognizing that it's a continuous improvement initiative. It has important elements, such as streamlining and improving processes. Taiichi Ohno is considered by many to be the father of what we call lean today. According to Mr. Ohno, the essence of lean is that we first calculate from the time that we receive an order for a product or service to the time we get paid for that fulfillment. The objective is to make that time frame progressively shorter and shorter. Lean is about reducing waste across the entire value stream in terms of time and effort on the part of human beings. This results in maximized value, better efficiency, quality, and customer satisfaction. In the manufacturing sector, there are many examples of lean. One small company producing sheet metal and wire products moved away from a batch and queue approach to a lean manufacturing approach. In doing so, they were able to drive down costs by 30% the first year and reduce lead time for customer orders by 50%. Conversely, in the service sector, a large nonprofit financial services organization used the practice of lean to focus on their process flows. They were able to reduce the time to respond to customer inquiries by 50%. They reduced their backlogs for claims by 80% and measured a 50% improvement in customer satisfaction at the same time. There are many advantages to being lean, and it starts with improved process efficiency and flexibility by taking out the waste and removing the impediments to a smooth flow of products and goods. After that, it's about reducing lead time and cycle times. How long does it take for us to fulfill that customer order? Can we speed that process while simultaneously improving the quality that we deliver to our customers? At the same time, we can provide very meaningful communications with our stakeholders. Stakeholders include our employees, our management, our vendors, and even our customers through the application of techniques like Kaizen or change for the better, integrating people on teams and making improvements. We also explore opportunities to better leverage the resources that we have and reducing the resources that we need. These are very powerful techniques. The value of lean to an organization has many facets, including that it creates a real purpose. And that purpose starts with the customer, as it does with Six Sigma. There's a Japanese term called Gemba, which means going to the point of attack. In lean, it is at the point of attack where value is created, where we actually do the work. We allow our employees to reach their full potential by being extremely inclusive. Lean, by the way, is a very team-based approach to continuous improvement. It leverages the technique of Kaizen very much. Kaizen involves all employees in the process of continuous improvement. Lean identifies the value-added activities and separates out non-value-added activities in order to eliminate them as we go. This brings increased value to all of our stakeholders. We can drive this improvement to our bottom line by reducing wasted effort and time that doesn't add value that our customers are willing to pay for. Let's talk a little bit more about eliminating waste and what the value of this concept is. It involves identifying at the task level where we spend time and money. What adds value? What doesn't add value? And of course, there are things that are necessary but don't add value. We progressively determine how we're going to separate the activities and eliminate the non-value-add activities immediately. In the longer term, we work on the root causes for those necessary but non-value-added activities to determine if we can do anything about those as well. We prioritize based on the voice of our customer. It's important to recognize that this goes beyond what the customer gets in the product or service. It also includes our internal process customers. Who is downstream in the process that depends on me to do my job right the first time? We need to understand their voice and meet their needs as well. By doing that, we become more flexible, and we can increase the speed of what we're doing across the entire value stream. We also can begin to use a simple technique called Pareto, or Pareto diagramming, where we identify which 20% of the activities are associated with 80% of our opportunities or problems so that we can work to improve those. As we address those vital few major causes, this results in speeding up the processes inversely and proportionately, and thus reducing work in process, or WIP. This in turn gives us great opportunities to minimize processes and product complexity by rationalizing and reducing redundancy wherever we find it in our processes. In summary, the cornerstones of lean are eliminating waste, prioritizing the customer, knowing that process flexibility increases speed, understanding that 80% of problems are caused by 20% of the activities, realizing that the speed of a process is inversely proportional to work in process, and minimizing process or product complexity. In this topic, we will discuss some key lean concepts and process steps. To support that, we have a 4-step pyramid to represent the concepts of lean. These concepts revolve around identifying value, the value stream, pull, and perfection in the execution of lean. Let's start with identifying value. Identifying value should always start with the customer. These can include the customer we ship the product or service to, or the downstream process customers. A great exercise in identifying value is to break down a detailed invoice for your customer that shows every activity and what it costs. The customer could review the invoice and cross off certain activities, saying, "You know what? I don't see this activity as adding value." This would be a great indicator that we need to improve the process. This could include things like wasted movement, rework, or maybe extra inspection time because we have trouble getting the process right the first time. So what is it that creates value in the process or product? There are many pieces to this, but if we start with what is seen as valuable by our customers and then try to determine what brings the most value for the organization, we're off to a really good start. The next important concept in lean is what's called the value stream. A value stream is any X series of activities and processes that create value in an organization. We can break down the steps and use a technique we call value stream mapping. We typically capture cost and quality data and the amount of time that elapses as we move along the value stream. We should be including suppliers, the organization both upstream and downstream, and even customers in that process. We also need to consider identifying and eliminating waste steps in the value stream. With all that information, we can consider restructuring activities and processes to improve overall performance, not only for the organization, but most importantly, in the opinion of our customers. The next important concept is the notion of pull. Pull is the idea that instead of pushing inventory through the system by planning and anticipating how much might be needed, we actually allow the customer to trigger a pull of inventory based on consumption. By doing that, we can greatly reduce and eliminate wait time that's associated with traditional planning processes. Inventory is always there. We can use one and then we can get one. Through the use of pull, we can drive total inventories way down. In fact, we can almost go to zero inventory. We can minimize inventory by only having the minimal inventory necessary to create a time buffer between steps in the process, but no more than that, to support seamless execution based on demand from the customer. Perfection. Dedication to continuous improvement is absolutely critical in the practice of lean. All organizations would quickly agree that from a safety perspective, the only acceptable goal for safety would be zero. Zero injuries, deaths, lost time, accidents, or even near misses. We have to have the same attitude toward waste and defects in our processes. Zero is the only acceptable goal. While we may never actually get there, we have to be committed to continuous improvement to drive perfection. We should create feedback loops with our customers to get the customer voice in the elimination of waste as well. The customer will continually define for us what value added means, and that can change over time. Now we'll take a moment to discuss the process steps for lean. It starts with identifying value in the organization. This is very important because it helps define the direction for the organization. We use the customer's inputs to define what value actually means. From there, we map the value stream. It makes sense to start at the end with the customer and work backward through the process. You can create current state maps that represent the current situation, and then think about future state maps. When you compare the two, you can identify what needs to be done to create better flow. You can remove obstacles and bottlenecks, organize people and resources better, and take steps to ensure quality at the source. Then we can address the concept of pull. We want to establish a smooth pull through of our inventory to support the entire process. We minimize inventories and we manage demand so that we can have ideal logistics and execution. Then we seek perfection. This includes incrementally modifying and improving our practices over time to continually eliminate wasted time and efficiently execute the entire end-to-end process. Think about it as a never-ending cycle of continuous improvement that's driven by changes and the needs of our customers. In this topic, we will explore the concept of value added. Value is defined by how well a product or service actually meets our customers' requirements. An important question we can ask to determine value is, will the customer be willing to pay for this? If the answer to that is clearly yes, then we can argue that it has value. So value added includes activities that actually add value to the end product and that our customer is willing to pay for. So logically, we would say that non-value added would be any activities the customer is unwilling to pay for. So let's say we provided a detailed invoice to our customer and we broke down every single activity that was included in the price. If the customer was able to cross off anything and say, hey, I don't want to pay for that in my price, that would help us to identify the non-value added activities. Let's explore this in more detail. There is a very helpful 3-point test. We can break down each activity in the process, perhaps using value stream mapping. For each activity, we ask 3 critical questions. Does it fulfill our customer's need or preference? Does it physically change something about the product or service? And is it done right the first time? We have to say yes to all 3 of these questions, or this step in the process may not add so much value. For example, let's say you went shopping for an article of clothing, and you had a coupon with you for a discount. If you take the clothing and the coupon to the checkout, and they quickly and efficiently scan it, and you receive instant savings, that's value added, and they're actually doing it right the first time. However, if they have to stop and go find a supervisor to get approval or go research it someplace before they can give you your discount, you probably would not see that as value-added activity because of the delay and not getting it right the first time. Let's discuss non-value-add activities. Just because we mark something as non-value-add doesn't mean we can necessarily scrap it. For example, with physical items, we may repurpose it, recycle it, or sell it at a discount. Or maybe it's something we have to do because it's necessary to operate the business, or it's a regulatory standard. We also have to support activities such as human relations, information technology, finance, and legal could fall in this category. Or maybe our customers have given us mandates that require additional inspections or documentation before we can provide that product or service. There will always be some non-value-add activities that we just can't change easily. The concept of lean includes the classic 7 wastes. Let's start with overproduction. This is any effort beyond what's required to meet the customer requirements. Building inventory or having a bunch of people sitting around waiting for a phone call is a form of that. After that, we have extra processing, which can include reworking a product or service. Motion would be the physical movement of people, material, and information that's taking up time or space, but not really adding value. Waiting would be delays, both planned and unplanned, that consume time and money, but don't really add value in the opinion of our customer. Transportation would be trucking, logistics, and shipping in excess of the minimal requirement needed to deliver it to the customer. Inventory would be excessive inventory beyond just what's needed to support a smooth pull of production of information through the value stream. And then finally, any defects. This includes any need to fix, repair, scrap, or otherwise correct and inspect that could be avoided by doing it right the first time. In this topic, we will discuss the tool of just-in-time, or JIT, that's part of the lean tool bag. Just-in-time is important to us because it's a very clear and easy-to-execute control of inventory processes. It controls the flow of materials and products to meet the drumbeat of customer demand, also known as takt time. We don't have the waste of waiting with a well-executed just-in-time system. We use one unit of inventory and we're able to get another one immediately and move on. And we can minimize waste such as storage costs. One example in the manufacturing industry is automotive assembly plants and the practice of sequencing. They trigger automotive interior trim like headliners, door trim, and instrument panels to be assembled nearby and then delivered in exactly the right order of color and combination exactly when needed. In the service sector, a great example would be hot dogs. And a really cool process I've seen is where the order ticket is stapled to a paper bag. The paper bag moves down the counter as you do, and each team member adds the ingredients so that when you arrive at the end of the counter, there's your bag ready to go, hot and fresh. Just-in-time is based on the pull manufacturing approach, and it's driven by various kinds of signals such as Kanban, or visual signals, or Hijunka box, or other techniques like that. The benefits of JIT involve controlling inventory, controlling the flow of materials and products, reducing weighting, and reducing waste. JIT is based on the pull manufacturing approach. Production is driven by signals and it's used to create synchronized assembly lines. The benefit of this is that it helps create synchronization between assembly lines. You can actually have visual signals to pull in components just when needed for finished products. This in turn results in a much smoother flow of production and reduces the overall inventory cost to operate the business. There are many benefits and limitations associated with just-in-time. We can free up working capital in the form of inventory throughout the facility. But we can also free up space. For example, a printing company was considering expanding its facility to accommodate pre-press operations. But after using just-in-time techniques, they freed up so much space that they avoided spending $100,000 for added square footage. As a result of successful JIT, we may be able to downsize and save on rent, heating, and cooling. We also can reduce wasted motion and efforts associated with maintaining inventory. We can also have more working capital than what would have been allocated to the purchase and maintenance of excess inventory. Now, there are some caveats for each of these techniques. We need to recognize that just-in-time is not necessarily a good fit for all applications. The benefits of using JIT are that it frees working capital, makes space to use for other needs such as production, allows downsizing to lower cost, generates less waste, and lowers inventory costs. One of the limitations of JIT is that it does not work for all replenishment scenarios. Additional limitations are the distance from suppliers, potential supply shortages, a sudden spike in market demands, and delays in the delivery of materials, to name a few. For example, what if we are far from the suppliers? If we are in the United States but the supplier's in China, they're going to need to ship the product by boat. It can be very difficult to design just-in-time in that kind of situation. We have to make such significant buffers in our calculations that we're probably better off using enterprise resource planning or a technique like that. Another potential issue is the potential supply shortages that could happen in the market. Does this product have a volatile supply base? Is there a risk of tsunamis taking out the supply source? Are there other things that can create significant risk to us with respect to supply chain execution? What about a sudden spike in market demands? If we design our inventory system to work with just-in-time at 100 a day, but suddenly the market spikes to 1,000 a day, just-in-time isn't going to respond very well to that particular problem. Finally, can there be unexpected delays in the delivery of materials? This is often driven by things like the weather, or cross-border movement of materials and goods through customs, or perhaps transport issues associated with things like railroads, or special kinds of transportation equipment required to move the product or service that are not predictable. In summary, before implementing JIT, it's important to examine both the benefits and the limitations based on your specific operation. Poka-Yoke is an important aspect in the application of lean in production environments and in service environments as well. Poka-Yoke translates roughly in Japanese as mistake-proofing. We also might hear it as error-proofing. What we're doing with error-proofing methods and Poka-Yoke is determining where human errors can occur in a process. We work to continuously eliminate these mistake opportunities and to make it easy for the human being to get it right the first time. So for example, in an assembly area, we're going to be assembling a product with screws. If we position and stage the standard work so that there are exactly 10 screws available for each assembly, it gives us a visual signal when we've used all 10 and there's none left over. That would be an example of error-proofing the application of an assembly operation. In the service sector, we may use color-coded forms. Or maybe the information technology system does not allow us to exit a screen until we properly fill in all the required values in certain fields. There are many types of Poka-Yoke devices. There's really no limit to these, but let's cover some of the important ones. The first would be checklists, so that we don't forget the important things that need to happen, and the particular order they may need to follow in order to ensure a quality result. Screening is also a very powerful technique, giving us the ability to force the accepting of legitimate values or options within a given process. Simple screening devices might prevent problems with accepting agreements that we don't want when we're accepting software licensing. And-on lighting or signaling methods are very powerful with different colors of lights, denoting different actions by the support team. And finally, control methods, such as color coding or providing safety mechanisms so that we have smooth movement of material without injuries or safety problems or damage to the product. There are endless examples of how Poka-Yoke can be utilized. In a manufacturing example, we may have checklist, screening, signaling, and control methods all in play. Additional examples may include enclosing the moving parts of a machine so no oil or chips could fly up, and loose clothing cannot get caught in the gears. Some machines are designed so that safety doors must be engaged before the tools will move. We have computer controls and computer-aided manufacturing tools that allow for fewer mistakes by the operator in terms of programming the equipment. All of these Poka-Yoke devices help to prevent or minimize human error. In this topic, we will discuss the concept of Kanban. Kanban is a Japanese term associated with the notion of a white card, or a card that you can see and touch. But in reality, it's any form of a signal that can be used to pull materials into the value stream. It could be anything: colored golf balls, bins or containers, empty spaces on the floor, lights, or sounds. A great advantage of using Kanban and pull is avoiding overproduction by only making what's needed when it's needed. Making sure we have only enough material in the system to meet all requirements to pull things through helps us reduce inventory beyond the absolute minimum levels. Minimizing inventory and work in progress also means better product quality, because we'll have less inventory moving through the system that could encounter problems that need to be fixed. However, there are disadvantages as well. Whenever we have major disruptions in delivery of materials, it can cause a Kanban system to break down. The notion of Kanban pulls works like this. We have a customer, which could be the end customer or a downstream operation. The Kanban stream begins with the supplier, who provides the material flow to production. From production, there's a product flow to the customer. When the customer requires a product, a Kanban pull signal is sent to production from the customer. Then a Kanban pull signal is sent from production to the supplier. When we use the standard amount or unit of material, we create a Kanban pull. This could be a physical ticket, or a container, or a signal that's going upstream. This authorizes the feeder operation production to produce another unit and ship it down to the customer. When we consume the raw materials in turn, we would have a Kanban pull that goes upstream to our supplier. This process simply repeats, again and again, over time, to continually refill that standard unit in response to Kanban pull signals between us and our customers, or between us and our suppliers. There are many examples of how Kanban pull can work. For example, in a manufacturing organization, I once used this technique to manage pallets. Pallets were used for shipping, and because of intermittent demand requirements from our customers, we often ran out of returnable packaging. Because it was impossible to plan how many pallets we would need, we simply created a standardized footprint in the parking lot. and we authorized our pallet supplier to come by every 2 business days, take an inventory with the checklist, and then come back 2 days later to fill the empty spots. By doing this every 2 days, we never had more than the footprint would allow, and we had enough on hand to handle any spike in demand from our customer. In the service sector, maybe we would be doing claims processing. And in the claims area, we would have bins from which we're pulling the claims ready to process. As the bins become empty, they could flow upstream to the mailroom, where they can refill the bins with more claims to process. This in turn could trigger a pull from the mail holding area to bring in more unopened mail to be processed to refresh the inventory of claims to be processed. There are many great opportunities in the application of Kanban and pull. It reduces inventory, work in process, and cycle time required to support our customers. It can also reduce turnaround time for a given customer demand. It also reduces machine downtime because we won't run out of things we need to keep everything productive. At the same time, we can improve visibility of quality issues. That said, there are also issues and challenges associated with the application of Kanban and pull. We need steady flow along a fixed path. Large variations in volume or product mix can disrupt the flow and undermine the performance of the Kanban system. It may not work so well when there are vast differences that separate our assembly plans and our suppliers from one another. Another obstacle could be unexpected demand in the market, which makes it very difficult for the Kanban system to respond quickly to meet that market demand. There are many applications of the physical Kanban signals. We could use containers or physical cards. For example, I worked with our suppliers to use standard containers for raw materials to supply my automotive supplier plant that was making parts for the auto industry. The returnable container would have a standard amount of material, and when consumed, we would return that container, and that would trigger replenishment. The same concept can be used with a physical Kanban card as well. There are some issues with cards, particularly when we're not co-located with our suppliers and our customers. If there are long physical distances between the point of use and supply, we have to move the cards physically, or scan them, or somehow fax them. And if we lose cards, that can be a real headache. A modern intervention that's working extremely well is what's called an e-Kanban system. So, in an assembly plant or production facility, as we consume a standard amount, we could barcode scan or use an RFID scan to say we've gone empty. This signal transmits automatically to our supplier department or outside supplier, the authorization to make and ship another unit of inventory. The newer approach using e-Kanban system is a great adaptation that integrates technology with Kanban cards to overcome the challenge of distance. If I were only allowed to pick one tool out of the entire Lean Six Sigma tool bag, it would probably be value stream mapping. A value stream map depicts the flow of resources and information as it goes across the entire value stream. It defines and shows us how value is derived and delivered from start to finish. We need to remember that waste disrupts value flow, and waste could be of all kinds. A current state value stream map may demonstrate the effort required, the time required, and defects and mistakes that occur in our present operation. We would also like to have a future state value stream map to show the entire value stream in an ideal situation. We should recognize that value stream mapping is a technique to identify value and waste, and it gives us clues about how we can address these for continuous improvement. Using a simple example of value stream mapping using a popular technique, we can identify some basic information being captured. The flow of information is represented with single, skinny arrows with some kind of production scheduling pushing things to execution. An output may be a signal to push things through the process. We use a directional arrow to show the movement of the physical material or the information coming from the supplier source, moving through the process, then off to some kind of transmit mechanism to our customer, who in turn is probably communicating, electronically or otherwise, the requirements to us to drive our production planning and control process. so it gives us a sense for the flow of information and material across our value stream. There are 4 steps in the process of analyzing the value stream. Step 1 is defining the product family. Step 2 is creating a current state map. Step 3 is creating a future state map. And Step 4 is planning the implementation of improvements. To analyze a value stream, we have to start with first defining a particular product or family. And generally, you shouldn't overshoot this too much or bite off more than we can chew. It's usually a good idea to pick something very discrete. A particular piece of information we're going to process, like an insurance claim. Or a particular part we're going to produce, like a stamping that's used in a mechanical assembly. We define this product pretty narrowly, and then follow it through the process. You kind of staple yourself to it by becoming the thing and marching through the process. You capture what happens to it as you create a current state map. Once you've done that, you can do the analytics and move into analysis and identifying what could be done in the future state for a better future state and better results. The real benefit comes in when we get to the very end of the process and we do the analytics comparing the current state to the future state. If we evaluate the current state, we can identify 5 different steps. In the future state, we've noted a design work cell Kanban burst, and we've done a project to combine these 3 operations into one. We moved away from pushing things through the value stream, instead now pulling them through. The benefit can be quantified in the amount of effort and the amount of time. In the current state, the value add time is about 45 minutes per unit going through the value stream, and about 15 weeks of total lead time to get things through. In the future state, we drop that down to 31 minutes of value add time, which is about a 33% improvement in productivity. And we reduced the time from 15 weeks to just 10 weeks of total lead time. What an improvement using value stream mapping can make. Six Sigma and Lean are complementary methodologies, and in fact, they overlap a great deal. However, it's important to recognize there are important differences between the methodologies as well. First, let's think about the focus. The focus of Six Sigma is around eliminating sources of variation, the number of mistakes and defects we're making, as opposed to Lean, where we're trying to take unnecessary time out of the process and eliminate waste wherever it happens. The methodology associated with Six Sigma suggests a very rigorous 5-step process. Define, measure, analyze, improve, and control, where we're gathering data and going through a number of different steps that are highly rigorous and very oriented around data. With Lean, we're less focused on the data, at least the precision of it. Lean uses a 4-step process of identifying the end-to-end value stream, identifying the opportunities to improve the overall end-to-end performance, designing a solution, implementing the solution, and taking steps to make sure that the improvement is continuous and lasting. In Six Sigma, we tend to be very focused on a point in the value stream. The performance, say, of a single step, and our ability to produce quality at that step. Lean, on the other hand, considers the entire process, and what we can do to improve the process to deliver things faster, with better quality, and more efficiency at the same time. The key tools associated with Six Sigma are narrowly focused on specific problems and very statistical in nature. We use metrics and statistical process control tools to bring things under control and keep them controlled. Using a Lean line of thinking, we might use tools like theory of constraints for identifying bottlenecks and removing them. The concept of removing muda, the Japanese word for waste, is another technique. We eliminate waste through the use of value stream mapping, pull systems, the 5S methodology, the notion of standard work, error proofing, creating flow, and more. The success of Six Sigma depends on reliable data and scientific methods. This is a bit different than Lean, which is about eliminating waste and taking non-value-added time out of the process wherever we can. On the Lean side, we're less concerned with precision in the data. Instead, we're seeking information about what to improve and why to improve it. It's about total value stream performance and overall customer satisfaction. Lean focuses on removing waste, improving the overall operation of the business, and being committed to continuous small incremental improvements over time. In total, between both of these toolkits, there are more than 100 different defined tools that can potentially be learned and mastered in your learning journey. Zero defects and zero waste. We may never get there, but we want to be continually dedicated to improving quality, while at the same time working toward a totally waste-free value stream that delivers results that our customers want to pay for. Remember that all of this is inspired by the plan, do, check, act cycle of continuous improvement. PDCA and other methods like it tap into systemic problem-solving tools. The Six Sigma statistical tool bag, the DMAIC methodology, other methodologies like the 5 Whys, and additional tools like Fishbone or Ishikawa diagrams, and many more. Both Six Sigma and Lean depend on teams and people being motivated to come together and work toward a common purpose. Both require significant buy-in by the organization as well. Without that, we can't get the commitment and the support required for success. Both methodologies, and particularly when they are leveraged together, are proven to deliver significant benefits in customer satisfaction, employee satisfaction, overall cost reductions, and making the company a better place to be. Integrating Lean and Six Sigma is the focus of this topic. Think of them as pieces of the puzzle that interlock and create tremendous value for any kind of organization. One of the techniques I like to do when doing value stream mapping is to take the data output from the value stream mapping and begin to identify which relative few steps in this value stream account for most of the effort that's being spent. At the same time, I examine the steps to see which few steps make up most of the defects and the mistakes that we're finding across this value stream. These would be the key vital steps where the bulk of the opportunities lie. Next, I decide which tools come into play. We can use Six Sigma to reduce the variation and reduce the number of defects. And we can use the Lean techniques to speed things up and create stability in the process. Lean and Six Sigma overlap and are very powerful when working together to eliminate waste and variation to drive value for any organization. Remember, on the Lean side, we're going after speed, flow, eliminating waste in its various forms, and removing constraints that are preventing a smooth flow of product and value. We are also working to increase flexibility and reduce complexity. At the same time we're working on this, we will also identify opportunities to strategically and tactically apply Six Sigma concepts. With a focus on what the customer requires, we work to reduce defects and improve our performance. We also engage in fact-based decision-making, optimizing and controlling the infrastructure and developing teams of people that can support us as we develop and implement our overall methodology. When working to integrate Lean and Six Sigma, there are some considerations. The various criteria include the time frame, the nature of the problem, capacity for culture change, and just how pervasive the problem is. When comparing Lean and Six Sigma, it becomes evident that certain methodologies have advantages in certain circumstances. For instance, if it's relatively inexpensive, low risk, and we can do something quickly, the Lean tool is superior. However, what if there's a lot of risk associated with making the change? If safety is a top priority, and there is a risk compromising safety in implementing a change without thoroughly testing it, we're probably better off using Six Sigma tools. That would take a longer time with much more rigor in the data analysis. If we want to go after the waste and improve velocity, where we have too much inventory, Lean is the great way to go. If, however, we are making a lot of mistakes and we're putting a lot of inventory through rework because we can't count on reliable results, this is where Six Sigma is very powerful. What about capacity for change? If we want to ease change into the organization, build quick wins, and drive long-term behavior, Lean is a wonderful technique. With Six Sigma, it can take longer because we need data and a longer period of time to show the results. Finally, the pervasiveness of the problem is a consideration as well. Is the problem isolated, or is it something we can easily identify and go after as low-hanging fruit with lean methods? However, if mistakes and defects are rampant, it will require a more intensive and data-based approach utilizing Six Sigma. The stages of Lean Six Sigma deployment follow the plan, do, check, act cycle. This includes identifying an opportunity, designing a solution, implementing it, and then moving into a continuous improvement cycle. To do that successfully means we have to equip people with the right skills and the knowledge about what we're doing and why we're doing it. Sharing the objectives will help others to participate and support us in taking action. We need to recognize the all-important customer and how they define value using voice of the customer data collection tools. From there, we can identify existing opportunities. We can observe or measure the current situation and identify the biggest sources of waste and variation that we can immediately address in order to increase value for the organization and for our customers. Designing a solution very often is dependent on some level of process or value stream mapping. There are 4 stages in a Lean Six Sigma deployment. Stage 1 is Identify Opportunity. Stage 2 is Design Solution. Stage 3 is Implement Solution. And Stage 4 is Ensure Continuous Improvement. The steps for Stage 1 are employee training, recognizing customer-defined value, and identify existing opportunities. In Stage 2 of Lean Six Sigma deployment, we design the solution. Let's consider an example where we're mapping out the flow of a direct mail piece. It begins with the compiling of names and data. We then verify who we want to send our offer to, based on their credit. We merge that data and we transfer it to our vendors, who actually produce the flyer document. Finally, we will send the document to the vendor who will actually print the flyers and mail them to our customers. In this situation, the task is to develop a new mail piece in 52 days. The master schedule has 5 activities, each having a varying duration. The first task is compile names, which takes 3 to 6 days. The next task is verify credit and addresses, which takes 16 days. The third task is data merge, that takes 31 days. The next task is to transfer to vendors, which takes 1 day. The final task is to print and mail vendors, which takes 10 days. The total lead time is 61.64 days. One of the important things about designing a solution is to zero in on where we get the biggest bang for the buck and where we're likely to find our biggest improvement opportunities. So if we evaluate the limited data, with 61 days in this value stream, reducing time sounds important. And we calculate that just 2 of these 5 steps make up 47 of those 61 days. That would be a clue that maybe we want to focus there first. So how do we identify which improvements to address first? Well, there are some pieces to that. We want to assess the impact. We need to understand what the low-hanging fruit is that would affect people the most. We might want to prioritize those things where we can involve people in the solution. People would have to support that and maintain it in the future. We also like that to be highly visible. We need to generate quick wins early in the implementation of Lean and Six Sigma. We have to be very cognizant of these issues as we move through the process. In the third stage of Lean Six Sigma deployment, we decide which improvements to address first. We then prioritize low-hanging fruit, which are improvements that involve workers and processes that have highly visible waste. To ensure continuous improvement, it is important to create employee buy-in and ownership. There are many things we need to do, including deploying high-performing teams' methodologies, involving people in the process, training them to be cooperative and communicating to gain their support. We need to listen to and honor people in the process. We need to commit to eliminating defects and waste in our process, and the focus is 0. 0 defects and 0 waste. We also need to ensure that those processes and improvements are sustained over time. There are a number of tools that can help with this, such as error proofing or Poka-Yoke, standard operating procedures, balanced scorecard, and other things like statistical process control. But we're never done. We need to remember that Six Sigma and Lean Six Sigma together are a continuous improvement methodology. In the fourth stage of Lean Six Sigma deployment, we ensure continuous improvement requires employee buy-in and ownership, a need to continue to find new ways to eliminate waste, ensure that improvements are sustained, generate new ideas, and act on ideas. We also need to remember that ideas are great, but until we act on them, until we take action, ideas have no real value to the organization. So from a Six Sigma perspective, there are many lean tools that we want to apply. For example, just on a general level, we need to apply the notion of value chain and value stream, creating flow, and perfection in the ability to process, to execute flawlessly. We also don't want to overlook many different process improvement tools that we use. For example, waste elimination techniques. The use of value stream mapping to help understand where in the value stream we can make improvements that would have the biggest effect on the customer and on the organization. Can we put in Kanban and pull systems? Make things just in time. Create better flow. We're looking to leverage the tools of Kanban, pull signals, and things of that nature, and leverage things like Poka-Yoke and error proofing with standard visual work throughout the process. And finally, let's discuss lean tools used by Six Sigma. The general lean concepts that may be used are the ideas of value chain, flow, and perfection. The process improvement tools are waste elimination, value stream mapping, pull systems, just in time, cycle time reduction, continuous flow, Kanban, and Poka-Yoke. And the control tools are total productive maintenance, or TPM, visual factory, and visual controls. This course provides an overview of project teams, and specifically Six Sigma project teams. It also includes the different tools and techniques that teams use to communicate and make decisions, and how team members can best contribute to the success of their projects. To be successful, we require teamwork in the execution of Six Sigma. The successful implementation of the Six Sigma methodology is dependent on high-performing teams that come together to collaborate on getting a result. All teams go through a developmental cycle, from the time they form until they adjourn at the end of the project. The traits of high-performing teams include seamlessly sharing skills, honoring ideas, and empowering individuals. Everyone must be actively involved, and through collaboration, we drive consensus to reach our goals. Process improvement teams tend to come together around very specific kinds of objectives. For example, a team may assemble with the purpose of reducing the amount of time it takes to complete a specific step in the value stream. The team will focus on that very specific business or operational process. They will have urgency around getting rapid results, and they'll be highly committed to making things happen. Another aspect of process improvement that focuses on process is that we want to focus on the low-hanging fruit, or the improvements that have high impact, are very easy to execute quickly, and of course the actions that will generate a good return on investment. Quality teams are often formed and kept intact for a longer period of time. They tend to drive efficiency for a couple of reasons. They may improve a particular process or add or remove a process. Processes may also be restructured or realigned. Finally, a quality team may be involved with developing a quality plan so that we can help the organization operate in a consistent manner, follow best practices, and get consistent quality results. Quality teams provide strong support to make those things happen. Ad hoc teams could come together to solve a very specific problem. For example, we may have a one-time problem that's popped up, and we need to pull some people together to address it. They tend to operate with a pretty limited lifespan and may only come together just one time to accomplish a very specific set of goals. They usually come together with a very well-defined purpose and a very clear idea of what success would look like. These teams could be interdepartmental or cross-functional, with lots of different functions within an organization. Or they may include specific stakeholders close to the work itself. Self-managed teams correlate very highly to the concept of quality circles and Kaizen circles. They tend to be formed around repeating processes that occur on a routine basis. For example, at a manufacturing company, if we had a group of people sharing a number of machines to produce a product, they may come together every day in a very short meeting and talk about the things that happened yesterday. How can we get better? And how are we making progress toward our quality and throughput goals? In a service environment, such as a technical support contact center, where we serve customers, we may come together and talk about call volumes, allocation of resources, and creative things we could do to deliver better service every day to our customers. A great feature of self-managed teams is that they require minimal supervision from management. Instead, they have team leaders who work inside the teams to facilitate their work and remove the barriers, as opposed to managing them. These agile teams can make a huge impact on organizations and have a lot of flexibility to take on a wide variety of projects over a period of time. There are many important aspects about the characteristics of Six Sigma teams that we need to understand. First, Six Sigma teams are ideally multidisciplinary and cross-functional. The reason for that is we want to avoid what's called groupthink. We want to make sure we're viewing the entire value stream across the process. We need our team to be able to share information and expertise seamlessly, and be able to share resources between our teams. An important consideration is mapping talents to the specific needs of the project and the team. For example, we need subject matter experts. Will we need suppliers to this process? Would we want customers to be involved as well so that we can have their point of view? Is there a specific technical, organizational, or communication skills that we want to have present in our team so that we have a balanced approach and all of the talent skills we need to be most effective? Teams can be formed for different purposes and for specific projects. Examples of various teams include process teams, quality teams, ad hoc teams, and self-managed teams. An ad hoc team could be formed and end in hours by solving a very specific point solution for some kind of problem, whereas a self-managed or self-directed work team could exist for years with a pretty stable number of team members and has a team leader to facilitate the team activities. We need to maintain flexibility. The reason for that is the nature of projects changes over time, as do our objectives. Team members may come and go over time as well. We also need to quickly adapt to meet new challenges. For example, one team I helped form was focusing in on the human resources hiring process for a state government agency. Over time, there was a need for support to roll out a new HR solution, and all of the hiring managers in the bureaus needed to adapt. This team very quickly took on that new challenge and was superior in their results. Resources, roles, and responsibilities are always very important. As we move through the process, we need to create a detailed work breakdown structure, and the team will begin to define roles, responsibilities, and necessary resources. Who or what will be needed? When would they be needed? How much of their time would we require? What kind of subject matter expertise, technical or information technology support do we need? It's good to think about relationships and reporting structures as well. We need to have the right people engaged with the right people, if you will. But we also honor the organizational structure, the hierarchy of who reports to who, and make sure that politically we're aligning things in a manner that's going to be best accepted by the entire organization. In this topic, we will examine the evolution, forming, storming, and norming of high-performing teams. There are a number of things we need to be aware of with respect to project team dynamics. The first is that team member dynamics will change over time. Different people can assume different roles. Some people can emerge over time to be strong team leaders or facilitators. People will get to know one another better, particularly as they move into the norming phase of team development. The other thing that happens is that the nature of the work evolves over time, and things may get more challenging as our project progresses. Strong leadership is very important and critical for high performance. The manager's role is not to manage, but to consciously lead the process by guiding people, managing performance, and ensuring that we have good stakeholder communication. The manager also helps to resolve breakdowns in communication and addresses any conflicts that might arise in our groups as well. We are going to explore each of the stages of team development a bit more closely, starting with the forming phase. As we put people together for the very first time, we're not confident, right? Many of us may be anxious, not sure why we're here, or maybe even upset we've been asked to drop other work or add new tasks to the work we're already doing. It's during this phase that we begin to formalize team roles and define the responsibilities of the team members. The team leader or facilitator is critical at this stage because their leadership is important to how successfully the team is going to come together. The facilitator and the team leader needs to pay attention to the process, make sure that the structure is clear, and act in a directive manner at the beginning of the team building process. Over time, their behavior can change as the team dynamic begins to evolve. The storming stage is highly creative, and we may start to experience some friction. We may have some disagreements. People are trying to figure things out, and we may begin to encounter differing work styles and different ideas. This is where conflicts are likely to arise. If we don't have careful facilitation by the team leader to move things forward and keep everything on the same page, we have a risk of failure. While storming is a normal step in the progression of team development, we need to avoid stagnating in this area of low productivity and high conflict. The team leader's role is absolutely critical here. They must coach and guide the team. Ground rules should be established, a code of honor that includes how we are going to treat each other and talk with one another in a productive and supportive way. The team must remain focused on the end game and the common goals and objectives. If we do those things, we can move out of storming and begin moving on to the important norming stage. In the norming phase, things really begin to gel. Collaboration comes together. We begin to see each other's points of view and become more cohesive. We begin to understand our purpose as individuals and as a team. The norming phase includes higher productivity as conflicts are resolved and the team members become more comfortable with each other. It's during this phase that the team leader can finally take a little breath and take a little step back and let the team members take more responsibility for the process and the resulting actions. In this topic, we are going to begin with the performing stage of team development. But first, let's review the previous stages. During forming, we came together and figured out our purpose. During storming, we worked out our differences and tried to figure out how we were going to work together. And then during norming, we started to gel and become productive. Next comes the performing phase. This is where we have the highest possible level of productivity with the least amount of friction within the group. It's during this time that the team members collaborate and become unified around an outcome. The team leader hardly has to direct it all and becomes more of a facilitator, allowing the team to work through the processes. The leader is there to delegate and remove obstacles, allowing the team to become high-performing. During the performing stage, we've got to make sure we celebrate breakthroughs and small successes. Later, as the team progresses and as the project matures, either completing or getting very close to being completed, we reach the adjourning stage. We may disband the team because the objective has been met, or we're far enough along that we can delegate the remaining pieces to the team members. At this stage, it may be difficult for some team members to let go and move on. However, since projects are temporary in nature, this stage is a normal part of high-performing teams. Adjourning may also occur if there's no new defined work for the team to address, or the future objectives are undefined or uncertain. This may be a signal that we need to adjourn the team. Also, some team members may begin losing interest, or may be pulled away before everything is complete. This may be an indicator that it is time to close out the team and assign those final tasks to a few remaining individuals to independently complete them. We must never forget the recognition stage. The team leader is absolutely critical here to make sure that the team gets the credit, and not the leader or facilitator. It's at this stage that the process review inside the team and with sponsors should occur if it hasn't already. This is an opportunity to list the things that went well with our team, and to identify and document the lessons learned so that things will go better next time. During the recognition stage, we want to celebrate successes. Make sure the organization is aware of what this team has accomplished, and make sure that they get the thanks they actually deserve. The effort to recognize accomplishments is very important because it sends a message to everyone in the organization through positive reinforcement of what we value as an organization. What we care about will show in our actions, not just in our words. In this topic, we will discuss brainstorming. It's important to remember that brainstorming is a process, and it's a fantastic technique for generating ideas regarding improvements in processes. Once some initial ideas are generated, we can build on one another's ideas. Going into a brainstorming session, it is helpful to have some ground rules so that there's no judgment and no self-censoring by anyone about their own or others' ideas. At this stage, we just want to capture all those great ideas and get them down on paper so that we can work with them. Everyone should have a say, and we need to listen carefully to everybody's thoughts and leverage individual expertise as well. You could think about brainstorming as a 7-step process, and the first couple of phases are very important. Albert Einstein once said, "The formulation of the problem is often more essential than the solution." Identifying the problem is the first step of brainstorming. In order to be effective, we need to be very clear about the topic of our session. We must be specific with a goal and hold each other accountable to stay on point as we generate ideas. It is also helpful to have reference information available during the session. This may include value stream maps, studies, statistical analysis, and cause and effect analysis information. From there, we want to move on to generating a working list of ideas. The more ideas you have, the more likely you are to find some excellent ideas that you can leverage going forward. We want to welcome all ideas, no matter how outrageous they may sound. We want to remain in an open frame of mind. The facilitator has a critical role to make sure everybody participates. One suggestion is that in the first round of brainstorming, every team member needs to offer up at least one idea, ensuring full participation. It is critical to record all the ideas and keep those visible to the team at all times. It's often a good idea to take a little break and let the ideas settle, then come back to them a little later and move into the next steps of the process. It's during the next phase of evaluation, analysis, and presentation that we begin to evaluate those ideas and use more of a critical eye. Is that idea practical? Who would need to be involved? What could pose a challenge? Would it cost a lot of money to do that? Then we can rank the ideas based on various criteria. For instance, the impact from the idea, how doable it is from a political and team perspective, and maybe the cost. Once the ideas have been ranked, we can drop the low-scoring ideas and narrowly focus to just those which have the greatest merit. Then we can assess top ideas based on feasibility and the impact or cost-benefit from implementing them fully. Finally, we can prepare a report to our sponsor or executive team and seek approval to implement the solutions. Nominal group technique is another great technique for group decision-making. Unlike brainstorming, which can be rather energetic and loud, and which is a group activity, nominal group technique does not require any significant personal interaction. The first step is to start out with a topic or problem that's presented by the facilitator. This needs to be open-ended, allowing for many ideas about solving the problem. We ask the individuals in the room to privately write these ideas down. Since there is minimal interaction, the technique allows for anonymity. There should be no self-censorship because the ideas are not presented in a public forum. The nominal group technique can be very helpful when some members are not as vocal or willing to voice their thoughts. Perhaps the issue is very controversial, or we have low levels of team cohesion. Providing a quiet, isolated environment for idea generation may be ideal in this case. Nominal group technique is a 5-step process. First, a problem is presented. Second, members write down ideas. In the third step, ideas are shared aloud in turn. In the fourth step, members score or vote on ideas. And then finally, ideas are ranked based on score. The first step involves the following. The facilitator presents the topic or problem. There may be a brief discussion for clarification, and participants must confirm understanding of the problem and/or goals. For example, a problem statement might be, we need to improve customer satisfaction for our contact center where customers call for technical support. What could be done to improve that? Then we allow the ideas to flow. In step 2, we ask the members to write down their ideas. We might do a little brief discussion to get started, and then ask folks to work in private and generate as many ideas as possible during a set period of quiet time. In step 3, we ask our participants to read off their responses one at a time. No discussion or questions are permitted during this process, unless they are related to the procedure. We cycle around the group many times, allowing participants to share their ideas. Participants may skip their turn if they wish, and may jump into the next round if they have an idea when called upon. All ideas are documented and nothing is left out. We record the responses on a flip chart or highly visual place until each participant has given several responses, or until we've run out of time or ideas. Next, we give each idea an identifier, such as a number or letter. We discuss each idea in the order it appeared. Then we ask the participants to determine which ideas, maybe the top 5, that make the most sense for them. And privately, they might record that on their own papers. They may turn those papers in, and the facilitator will determine which 5 ideas receive the most interest. Then we can introduce these top 5 ideas back to the group and ask the participants to rank them by allotting 5 points for the most important one and 1 point for the least important. Again, participants can record the responses privately. They will turn their papers into the facilitator, who will add those numbers up across the entire group. What this does is it selects and ranks the ideas without anybody being called out for their opinion. Everyone is able to remain anonymous. As the facilitator reviews the responses, they will record them in real time and visually. Participants will be able to see the aggregation of ideas and scores, and everyone will learn together which ideas received the highest score. From there, a report can be prepared showing the ideas receiving the most points, so we can move on to the implementation process. Even though there may not be strong agreement about what to do next, we certainly have the group's opinion about what's important and which ideas should be pursued. Multi-voting is a group decision-making technique which allows us to prioritize our options from a large number of ideas or solutions. The benefit of multi-voting is that choices that are favored by the majority will make the list, even if these choices may not be everybody's personal top choice. We could use this technique after brainstorming or after nominal group technique idea generation as well. Let's compare the attributes of multi-voting with those of brainstorming and nominal group technique. We will evaluate the categories of discussion, interaction, consensus, benefits, risk, and then optimal group sizes. If we review these for a moment, we'll identify some differences between the 3 techniques. Nominal group technique involves individuals with very low group interaction. This is very different than multi-voting and brainstorming, which are very much a team sport. Reaching consensus is a little different too. We'll use scoring in multi-voting and nominal group technique, but with brainstorming we rely on discussion. The benefits of each are pretty obvious. With multi-voting we can generate a lot of ideas and move through them pretty quickly. With brainstorming we can generate a lot of synergy and energy in the room, and with nominal group technique, everyone has a voice. Everyone will be engaged and everyone will contribute. The biggest risk with any of these is the concept of groupthink. This is where all the participants fall into the same mindset and don't challenge each other to truly be creative and look at all points of view. Since nominal group technique is conducted on an individual level, it is less likely to fall into the groupthink trap and more likely to generate a variety of ideas. Finally, optimal group sizes are generally 10 or fewer for a rapid process. We next move into generating a list of ideas or solutions. And as we move through that process, we want to eliminate duplicates. Categorizing ideas into themes can help you find the duplicates and eliminate them. The next step is to give each idea or solution a unique identifier so that it can easily be tracked. We then ask each participant to choose a specific number of ideas, for example, their top 5, and then move on to the next steps of the process. Once we have a specific number of ideas that are uniquely identified, we're able to work with the participants to rank the choices. With nominal group technique, that would be done in an individual, discrete manner. But with brainstorming and multivoting, we would do that very openly. Then we tally the votes for each idea. We eliminate the lowest ranking ones and repeat the process until we get to a specific number of ideas, perhaps the top 5. At that point, we have the few ideas that have the most support and buy-in from the group, and we can move forward to present them to our sponsor and executive team, and possibly begin to implement them. Communication in the context of applying Six Sigma is critical. We must communicate with our key stakeholders and our team members. We need to share our vision for the project, and we need to listen and hear what they say about it too. Are they understanding and interpreting what we're saying correctly? We need to provide training, conduct reviews, share results, report progress, and certainly celebrate success. Everyone must be informed. Communicating effectively can certainly be a challenge, and we need to ensure team members are getting the right information at the right time. A lack of clarity is a prime cause of frustration and ineffectiveness for many organizations. Stakeholders are individuals who differ in many ways: professional experience, organizational status, risk tolerance, and personalities. Understanding stakeholder needs is key to effectively communicating your message. One-way communication is appropriate when no immediate response is required and the communication isn't particularly urgent, confidential, or sensitive. It's also ideal when you don't require confirmation that the message was received. Examples may include email, memos, announcements, progress reports, voicemail, and status updates. One-way communication may be a bit impersonal, but it can be appropriate in some situations. Two-way communications are a little different. This type of communication uses a bi-directional channel of communication. It is real-time, interactive, and allows for immediate feedback. In two-way communication, each party takes turns sending and receiving information. Telephone contact is one way of doing that, or perhaps using tools like text messaging or voice over IP. Interactive communication is appropriate when an immediate response is required, when the information is sensitive or possibly likely to be misinterpreted. It's also beneficial for brainstorming, feedback, and collaboration. Top-down communications are very important when we want to drive influence through the organization. Informed employees are empowered. They understand the strategic objectives of the organization and how their role fits into the bigger picture. Performance feedback is often delivered in a top-down manner. Bottom-up communications are also very important. This type of communication is helpful to inform managers of what's going on and bring them in touch with the front line of the organization. Bottom-up communication can provide progress on performance, reveal the nature of problems, and promote suggestions for improvement. Organizations need to encourage this type of communication and make sure employees understand that their feedback and perspective is welcome. By doing that, we can empower employees to be part of continuous improvement within the organization. It's important to collaborate. We need to promote this notion in today's customer-focused organizations. To serve our customer needs, we must quickly get the right knowledge and information into the hands of the people who need it to do their work. Furthermore, inside the organization, people must be willing and able to communicate across departmental and functional boundaries and listen to each other's needs. We can't forget that our colleagues are our internal customers. Collaborative organizational designs emphasize lateral communication in the form of cross-departmental committees, teams, and task forces. In summary, communication can make or break the success of your organization. A Six Sigma team must ensure that stakeholders and team members receive the information they need when they need it. The value of an agenda cannot be overstated. The key role of the meeting facilitator is to make sure there is a clear agenda. This is essentially a meeting outline, which provides clarity on the meeting objectives. A good agenda will help keep a meeting on track. Everyone should be provided a copy of the meeting agenda in advance. The agenda should include the discussion topics and an allotted amount of time for each topic. If different participants will be leading or contributing to different parts of the conversation, their name should be included next to that agenda item. A detailed agenda eliminates the risk of missing important topics or accidentally getting off topic in unrelated discussions. When we're creating an agenda, it's important to recognize differences between an effective agenda and one that is ineffective. Let's start with the purpose of the meeting. It must be clearly stated so that participants have an understanding of what we're here to do and what we aim to accomplish. Any available background information is also valuable. This can include situation statements, activities from past discussions, prior action items, and status of any ongoing items. The agenda topics need to be clear and concise, in a logical order. An effective agenda is delivered to all participants in advance of the meeting so that they'll have an opportunity to review the contents and so that everyone comes to the meeting with some basic understanding of what will be discussed and why. We also want to contain the discussion duration. This gives us some structure around the amount of time for each topic and encourages us to limit the meeting to a realistic number of topics. Having too many topics or not enough are both a problem. Consider a checklist when creating a meeting agenda to ensure that all of these considerations have been made. This will ensure that you avoid the pitfalls of ineffective meeting agendas, which can result in wasted time and not effectively addressing important issues. Meetings with no agenda create all kinds of headaches. For example, we could be wasting a lot of time due to confusion and a lack of focus around the key things that we're trying to accomplish. Important points could be missed. Finally, the consequence of having no agenda is that our objectives may not be achieved at all. Taking the meeting minutes is always an important task for many reasons. We want to capture all of the details for anyone who could not attend the meeting. We also use the minutes as a historical record of the discussion for future reference purposes, in the event that the meeting participants need clarification, or a reminder of the discussion at a later date. We also use the agenda to track and confirm any important decisions, action items, tasks, and assignments that were agreed upon. Meeting minutes also make it easier to track pending items, as agenda items for subsequent meetings may include revisiting and discussing the status of items that remained open from the previous meetings. Meeting minutes are most accurate and effective when taken by somebody who is a non-participant in the meeting. If that's not possible, it may be a good idea to rotate the note-taking role from person to person, from meeting to meeting. Or you might want to consider recording the meeting for later reference. When taking minutes, only the important points should be recorded, those which are vital to the agenda, involve the outcome of votes or decisions, or those which lead to action items or follow-up. Be sure to ask for clarification if necessary, particularly if you're the one responsible for the minutes and keeping good notes. At the end of the meeting, it may be helpful to flesh things out, while the meeting is still fresh in your mind. Review the notes to ensure they're clear, on point, and specific about any follow-up actions. It's always a good idea to have a participant from the meeting review the minutes and approve their accuracy. Then the minutes should be distributed to all the participants who may review and provide feedback. This ensures complete understanding and agreement from the participants about what was discussed and what the next actions will be. It's always a good idea to use a template for consistency and format purposes, and to make sure we don't forget anything. The template can be used from meeting to meeting, allowing participants to become comfortable with the format over time and the flow of the meeting based on the template. Some key entries in a meeting agenda template might include the following: date, time, and location of the meeting, name of the facilitator, objective of the meeting, the note taker, in case there are questions about the contents, high-level discussion points, and action items or next steps. It's also important to note the persons responsible for taking action items and if there's a deadline. A strong meeting agenda followed by detailed meeting minutes will ensure that your meetings are efficient, effective, and that there is follow-through on action items. Meeting minutes also help create a cohesive flow from meeting to meeting. Project status reports have an important role. They're used to track progress throughout a project. They are also used to capture metrics and changes and to illustrate the ongoing performance of project work. The recipients of a project status report may include the project sponsor, management, stakeholders, or team members. A project status report may be part of a scheduled communication, and it may be used to report on milestones, set the stage to request changes or approvals, or trigger the next phase of the project. There are many different tools that can be used for capturing and reporting. Word processing applications are widely used. Spreadsheets are also helpful for tracking budgets and financial data, return on those investments, and things of that nature. There are also a number of different tools for tracking projects. For example, Microsoft Project is pretty popular in many organizations for tracking project completion activities. There are also a number of document management software products as well. Organizations will often use software such as SharePoint to securely house their documents, ensure version control, and allow people to access the documents from remote locations. We're also seeing a surge in cloud-based tools that allow us to capture documents, notes, and information without the burden of storage on our personal devices. Finally, what is the structure of your project status report? There are several important things to consider. General project information would include the report date, project summary, problem, and goal statements. The summary of key milestones will include our successes as well as any setbacks we've encountered, or any significant risk or issues we've identified. We should also include the current and pending tasks and upcoming key dates. Graphs, charts, and tables allow us to present project performance in an appealing format that visually displays the information. Financial data and performance metrics allow us to quantify our results and to demonstrate if the project performance is in alignment with the plan. Finally, project status reports also set the stage to make recommendations for ongoing project direction or to request additional resources to address any project issues. The Six Sigma hierarchy is defined and illustrated with this graphic. Starting at the bottom of the organization, we have yellow belts, who are working under the level of green belts, who in turn work under black belts. From there we have master black belts, champions, and executives. Executives provide the top-down direction for the organization. They lead the organizational direction regarding what we're going to do, how we're going to do it, and the strategic objectives of the organization. The executives set the direction and the goals, and all levels of the hierarchy work to achieve them. Executive leadership and champions have some critical responsibilities. The CEO and other top executives are responsible for the top-down, bottom-up aspect of success with Six Sigma and Lean Six Sigma. They are responsible for the vision and the strategy of Lean and Six Sigma implementation. They determine how the organization will align its actions with its overall business strategy. Champions are the next level down. These are the folks that actually own processes, secure resources, and sponsor projects. Champions are typically very experienced in the processes that might need improvement. They would have much to offer with respect to the inner workings of the organization on a more granular level than perhaps top executives may be aware of. The champion can ensure that a project aligns with the overall organizational goals and that the corporate culture is being considered by all of those involved with our Lean Six Sigma project. Next, we will examine the roles and responsibilities of individuals with Master Black Belts. They tend to be at the highest level, and there are a relative few of them compared to the rest of the Six Sigma hierarchy. It's their job to consider our alignment with the overall strategy, under the guidance of the executives and the champions. Master Black Belts will most likely teach and mentor Black Belts. They're typically the ones who would approve projects at the next level down. They also assess project performance and guide Black Belts to bring projects back under control. Master Black Belts also maintain expertise in the body of knowledge of Lean Six Sigma and how it will be used in this organization. They also may personally champion and drive certain mission-critical projects. The Black Belt is typically the overall project manager and mentor for very specific projects within the organization. They'll act as a coach and a mentor to both Green Belts and Black Belts. They may also do large-scale training of groups of Green Belts, Yellow Belts, and other employees on the Lean Six Sigma methodology. They are also responsible for complex programs or analysis like quality function deployment, failure mode and effect analysis, or design for Six Sigma projects. They might also lead the effort in a design of experiments to determine root causes and eliminate problems in our processes. Finally, we have Green Belts, who fill the very important role as team leaders. They may lead small teams in specific tasks and small projects. They may also conduct research and provide data for the bigger project. Green Belts may also serve as subject matter experts on key processes. They will also document key deliverables and utilize the tools and techniques of Lean Six Sigma, such as statistical process control outputs, control charts, and balanced scorecards. The Green Belt will gather data, calculate performance metrics, and prepare reports for management. There are many different aspects of Lean Six Sigma projects that Green Belts can accomplish. Their role is key in freeing up time for the Black Belt and the Master Black Belt to tend to more strategic or complex activities. In this topic, we will discuss the role of the Lean Six Sigma Yellow Belt. These individuals have basic training, can help with basic math and research skills, and can offer many other job skills and expertise. Yellow Belts may have specialized expertise that could be helpful with certain projects. For example, if we want to improve how we access a knowledge base for customer support, we may rely on a Yellow Belt who has actually done that kind of work. Yellow Belts have a very powerful role in helping to get at the real minutiae that needs to be understood and managed throughout the implementation of Lean Six Sigma. Other responsibilities of Yellow Belts can include collecting data. There are many techniques that we can leverage at the Yellow Belt level, including things like tally sheets, work observation for value stream mapping data, or doing simple time and motion studies for core data to drive problem solving. When it comes to problem solving, Yellow Belts can certainly help. They're the ones with the subject matter expertise in terms of what works and what doesn't. They may also use their expertise in understanding the culture, the morale, and motivations within the organization. And finally, Yellow Belts provide a great deal of support to Black Belts and Green Belts in getting things done. They may put together a pilot, coordinate and conduct testing, or do a proof of concept to determine the feasibility of an idea. The role of the Yellow Belt is truly universal. Yellow Belts are very important. And one thing we need to remember is that the Yellow Belt member very often is the one closest to the action, closest to the process, and therefore they have invaluable input. I've worked with organizations where Yellow Belts offered a number of excellent ideas and suggestions that we were able to leverage, which directly led to improved customer satisfaction. There are many important roles when it comes to Lean Six Sigma projects. These include the roles of sponsor, process owner, coach and facilitator, and team members. We need to recognize that roles can be combined as needed depending on the nature of the team and what we're trying to accomplish. The project sponsor is very important for setting the overall direction for the project. They're going to ensure that our project goals align well with the business case. They're often a primary benefactor of the overall results we can expect from the project. The sponsor could be a functional manager or perhaps an internal customer. Their primary responsibility, among other things, is securing resources, including financial resources, human resources, IT, and other types of resources. They play a critical role in communications and setting the example for everybody. They need to make sure we're celebrating wins and to help identify and manage risks. The sponsor is critical to the overall organizational change management strategy that the team may need to implement as part of their project. The process owner is usually a functional or operational manager who will own the processes we're working on. They serve as an important subject matter expert. They'll guide and oversee process improvement activities and ensure that our activities are in line with the overall project plan. The process owner will get involved with conflict management resolution and can be involved with removing roadblocks that the team may encounter. The coach is often somebody at the master black belt or at the black belt level, and it's their job to make sure the team understands the tools and methodologies the team will be using. They're assigned to help answer difficult questions and to help solve some of the problems the team is likely to run into. The coach will also be able to review the phases of the team's output. If we're following the DMAIC methodology of define, measure, analyze, improve, and control, there may be a tollgate at each of these phases where they can help diagnose problems, assess the quality of the work, and suggest alternative methods to move things forward. They may also get feedback on the overall effort of the team and provide guidance in corrective actions as needed. The facilitator could be a black belt or green belt, or other person that's skilled in facilitating process improvement. They can provide assessments of project quality at a granular level and provide immediate feedback as needed to take corrective actions. They can keep team members focused on the task at hand and help monitor team performance as well. Facilitators are helpful with recommending improvements and following through during the implementation of improvements. They may also help to overcome roadblocks and help resolve team conflict. Team members. The heavy lifting often falls to the team members, which would often be at the yellow belt level. They'll carry out those specific tasks leading toward a goal. They could have specific skills and expertise that we need, and they can fulfill many different functions, like taking minutes in meetings, helping to gather data, or doing research to support the team. The team member may report to either the project leader or to the functional manager. The work performed by the team member is critical to the success of the overall organization and meeting its objectives. This course covers several of the quality tools that are used during a Six Sigma project. We will discuss how these tools are created and interpreted throughout project definition, data collection, measurement, and analysis. The tools discussed in this course include Pareto charts, flowcharts or process maps, run charts, cause and effect diagrams, scatter plots, and histograms. Quality tools serve many purposes. For example, information in a graphical format is very powerful because it creates a visual image that can be quickly interpreted without the need for lengthy descriptions. Using quality tools that measure performance is also critical. One measurement, defect per million opportunities, or DPMO, allows us to determine how our process is performing in terms of quality. Identifying root causes and addressing them is also very important in the practice of Lean Six Sigma. Root cause analysis allows us to identify the true reason behind the defects and focus our energy on the right things in order to achieve improvements. And finally, we need to assess improvements. DMAIC starts with defining or chartering a project. Measuring involves assessing our current processes and gathering data to determine a baseline. From there, we analyze the process and data and determine the root causes and work to identify the key factors that contribute to the outcome that we need to focus on. Let's talk about the C in the DMAIC framework, the all-important control phase. We need to ask ourselves if we are putting in the necessary control points to validate success, and if we are triggering actions in order to see the results that we expect from our project. The three quality tools we will address here are the Pareto chart, flowchart, and the run chart. The Pareto chart allows you, at a glance, to understand what vital few causes represent the bulk of the problems that we are observing in the process. The causes are ranked in descending frequency, giving all Pareto charts a very similar look. The flowchart is a powerful technique, along with value stream mapping, to understand a process in terms of flow, feedback loops, decision points, and where there are opportunities for improvements. And finally, run charts, which allow us to examine the behavior of data over time. We can see trends, both negative and positive, which can either trigger corrective action or serve to validate that our process is working well, and/or that recent improvements were successful. So just what is a Pareto chart? It's a type of bar chart based on the principle introduced by Vilfredo Pareto, an Italian economist in the late 1800s. His 80-20 rule suggested that a relatively few number of the people, 20% of the population, controlled about 80% of the wealth. That principle has been expanded and built upon over the years to extend to quality tools and projects. The Pareto principle, or the 80-20 rule, argues that on average, 20% of the causes lead to 80% of the defects or opportunities for process improvement. Essentially, if we can identify and address the vital few sources of defects and mistakes, we will see a drastic improvement in our overall operation. By addressing those critical few causes, we can get the biggest bang for our buck and more quickly see immediate and significant improvement from our efforts. When we are defining project scope, we usually have scarce time and money to make changes. If we focus on the vital few top priorities, we can use our scarce resources most wisely. We use this approach when variables can be categorized. We can place them into groupings like the sources of defects or mistakes made by people in the process. When we work to identify top issues, it allows us to take a current state snapshot of the process performance and concentrate our efforts to improve these specific items, and then later go back and check the data again. We may decide to use the quality tools, such as the Pareto chart, flowchart, or run chart to check performance against the previous baseline. If we see improvements, this is a sign that we're doing the right things. If not, we may choose to focus on other causes of the defects and make attempts to improve the process by addressing those. Let's next do a quick video demo using the Minitab tool. With the Minitab tool, we would start with a simple spreadsheet with some data. So for example, we have injection molding defects, short shots, gates being cut short, things of that nature. And during the time period, we captured how many defective results during that time. With the Minitab tool, we can then use graphical analysis tools, and you will see here that there are a bunch of them available to us, like histograms, box plots, and oh, here we go, Pareto charts. And what we do is we click here and we go ahead and generate Pareto chart, and then make changes to it to support the analysis. What we are going to do instead is just go right to the result. Let's take a look at the actual summary report that we would get from running that. And what it did is it took that rough data and ordered it for us in the order of occurrence. We can see here on this accumulation line, we had 221 at this point. And now we got accumulation of 376, etc., where it's adding together these quantities of the defects. Other thing that's very important is that it gives us the percentage of defects. So this 221 is 35% of the total population, giving us a cumulative 35%. And then we can follow this out and say, the vital 80%, the 80-20 rule, these three things are really 80% of our challenge. In this topic, we'll cover the causes and the frequency of defects, and how to create and use a Pareto diagram. This involves listing and categorizing the causes of defects, and then recording the number of defects for each cause category. We then place the causes in descending order, from the category with the highest number of defects to the lowest. Finally, we calculate the total number of defects by all documented causes. In this case, there are 50 defects for cause 1, 30 for cause 2, and 10 for cause 3. We arrive at a sum of 90. This is the total quantity of defects critical for the calculation. From here, we can move on to calculate the percentage of the total that each cause represents. Cause 1 represents 50 defects of the overall 90 defects. If we divide, we find out that 56% of the total population of data, 50 of the 90, of those defects are related to cause number 1. Then we continue the process with all the other causes. For example, with cause number 2 we have 30 defects. That's about 33% of the total data. And then cause number 3 with 10 defects represents about 11% of the data. We know that we are correct when the percentages from each cause adds up to 100% of the total causes. The next step is to find the cumulative contributions for each of the causes. What does this mean? Basically, as we add up the percentages of the causes, one at a time, starting with cause number 1, we'll get closer and closer to 100% of the defects. Let's start with the first cause. There was no preceding value, so we only count the percentage of defects for this cause. That was 56%. From there we can start to accumulate by adding the 33% for cause number 2. This brings us to 89% accumulated defects for causes 1 and 2. Finally, we'll add in 11% for cause 3 to the 89% we accumulated so far. This gets us to 100%. So now we have the total summation of all the defects that make up our total of 100%. Next we can move on to creating the axis and the numeric score scale for our Pareto chart. On the left side we would have the numerical scale of quantities. These are the raw number of defects, before we calculated their percentages. Then we add bars to represent each category of causes and label them accordingly. From there we can move on to add the scale on the right axis. The scale on the left axis represented quantities, and on the right axis we have the percentage this quantity represents. So the 50 defects from cause 1 represents 56% of the total. Then we add cause 2 with 30 issues and 33% of the total. This brings us to 89% of the total. Finally, we add cause 3, which has 10 defects representing 11% of the total. This brings us to 100%. As we add the data, the chart becomes very visual. It allows us, at a glance, to determine what the most important causes are. And these are the causes that we should invest our time and effort in fixing. Pareto's law, or the 80-20 rule, states that 20% of the causes are very likely to lead to 80% of the defects that we need to address. This 80% are in fact probably the vital few that we need to focus on for continuous improvement. This technique is a very useful quality tool we can use if we have valid and accurate data to help us identify our key defects. In this chart, the red box signifies the defects we should be focusing on. Now we have another method that's available to us. It's called the change in slope method. In this method, we examine the cumulative frequency line and notice a behavior where the slope starts out very steep and then breaks and starts to flatten out. It's generally those causes on the steep side of the curve where we need to be spending our time and money in improvement projects. This is the best place to start when it comes to process improvement. Flowcharts and process mapping are powerful tools we use to depict the flow of activities in a process. These show many different characteristics of the process, including process boundaries, responsibilities for the work to be done, the interactions between the steps, possible disconnects where activities aren't really connected to something else that needs to be addressed, non-value-add activities, bottlenecks, and inputs and outputs of the process. In the practice of DMAIC, define, measure, analyze, improve, and control, we often find that this is very helpful to us in the define, measure, and analyze steps. Another thing to note is that process maps and flowcharts are often used interchangeably, although they are not exactly the same thing. A flowchart is the diagram itself, while process mapping is often when we add activities to the flowchart to illustrate a process in order to identify the waste and non-value added activities. Flowcharts often use universal symbols. The first is a start-stop, which is typically an oblong-shaped circle, which would indicate where the process begins and where the process ends. This might have letters in it if you wish to show continuity or sequencing, for instance, where you would point from point A to point B. Next, we have the actual step or the operation, represented by a rectangle. Very often, this is where the money is actually being spent. The value-add and non-value-add activities that use time and money in the company are happening right there. From there on, we have a decision point, depicted by a diamond. This may be a yes-no answer, and depending on the response, you would navigate in different directions on the flowchart. Then we have inspection, shown as a circle. This is the point in the process where quality tasks occur. Next we have delay, which is depicted as a capital D shape. Delays represent a point in the process where nothing is really happening. Finally, there's a symbol for inputs and outputs. It's a parallelogram shape, which looks like a crooked square. Inputs and outputs represent actions or items that enter or leave the process. For instance, raw materials are inputs to the process, while deliverables are outputs. Finally, we have the flow line, which connects all the step-shaped components of the chart. It illustrates the logical flow from end to end along the entire process. Building a flowchart is very much a team activity. And when we think about chartering a Lean Six Sigma project, we typically want to have our key stakeholders involved. That may include customers, suppliers, the project team, and subject matter experts who have expertise and insight into the type of work we're doing. The point of building the flowchart is to capture the what, when, and where of the entire end-to-end process. What are the steps and activities that make it up? Next, we must determine when the sequence of activities occurs over the flow of time, and then where do things actually happen? Where do the inputs come from? And where do the outputs of the process go once they leave the process? For example, on a technical support call, some inputs and outputs are obvious, but others may be more subtle. For instance, what the customer tells us about their question or problem is an input. The ultimate output would be the solution we offer to our customer. Another more subtle input would be what we search for in the knowledge base, and the output that we receive from that search. We need to be very detailed to include all of the inputs and outputs, not just those that touch the customer. There are many ways to define the process boundaries. Generally, you will select a logical start and stop point. Then, work to identify all of the steps that fall within the process scope, but no more than that. Just as we define boundaries in project scope in order to avoid scope creep, we must define the boundaries of our process to avoid biting off more than we should chew. For this example, we will use the scenario of a gas delivery, from the refinery to the gas station. We should consult those who are involved, who actually know about the process. They can help to identify the inputs and make suggestions about how the process works and where we might improve it. We would start at a fairly high level and define the major task and the major decision points. From there, we can decompose the process, breaking it down into the smallest steps and making the connections between the steps. Let's take a look at the example of the gas delivery. The starting point is when the service station is low on gasoline. This triggers an output from the station, which is an order for gasoline. This leads to a step in the operation to dispatch an order to delivery. Dispatch sends the order information as an output, which is received as an input by the refinery. They fill the truck at the refinery. Then we encounter a delay while the truck is driving to the station and filling tanks at the station. At this step, we have a decision point where we ask this question: is the truck empty? Yes or no? If yes, we have to return the truck to the refinery, but if no, the truck can receive input about where to go next and repeat the cycle of filling up another gas station. Now we need to verify that our understanding of the process is correct. We need to show this to our key stakeholders and those who understand the process. Working with your team and stakeholders, you identify the necessary changes or improvements to the process. For example, maybe we can automate the step where the order is generated from dispatch. Instead, maybe we can automate the order process so that we can receive notification directly from the customer to the refinery. Could we eliminate that extra step and still accomplish filling the truck? Using a flowchart can help us to illustrate the process steps, which can lead to important discussions and improvements to the process flow. Run charts are a great technique to track data over a period of time. This graphic includes data points throughout a time series. With this data, we can identify trends and look for shifts in the data over time. This is a great way to determine whether or not the process is under control, or perhaps a warning if the process is drifting with respect to the desired results. Run charts can also be very useful to validate that a corrective action we've taken to implement Lean or Six Sigma improvements is actually working. After implementing a change, we can reference the run chart to observe whether the desired effect is occurring. Is the data improving over time as the process continues over time? A run chart is a wonderful way to monitor progress and process improvement, ensuring that a process is staying in control. The value of the run chart extends to observing results and maintaining control while we're making improvements. As we create a run chart, there are different elements we will include. First, we have the left axis with a numeric score scale of quantities or percentages, or any other attribute you may be measuring. Next, we have the median line. This would be the average of the high and the low values for all the data in our data set. Across the bottom, we have the time series. This could be hours, days, or any other increment of duration. Then we have the data points for the outputs, allowing us to measure an attribute for each unit that was created at any given time in the process. An attribute could be any value, such as weight, length, battery life, etc., for the unit that was just created. If you think of a production line, these could be the units coming off a conveyor belt, one at a time. As they are produced, we take note of the time and measure of the attribute of the output to determine where it falls on the scale. Then we plot that data point and move on to measure the next unit. There are some basic decision rules that we should pay attention to when using run charts. In general, we should expect the data points to be relatively stable, alternating on either side of the median line, and always remaining within a reasonable distance to the median. If you notice a trend where 7 points or more data points in a row fall above or below the median, is an indication that something has changed in the process. In the graphic, on the left side, there is an event where a series of 7 or more data points in a row has fallen above the median. This should be investigated. The run chart on the right shows an upward trend over time. If we examine the data over a series of months, there is a trend where the data is gradually moving upward. Let's do a little demonstration using the Minitab tool to get a sense for how this works. First, we have the data, and this is the data representing the percentage of orders that need to be corrected over a number of weeks of time. So we have 15 weeks worth of data, and these are the percentages of orders requiring work over the 15 weeks. Then we can go and use this handy assistant tool. Go to Graphical Analysis, and then choose a time series plot to see what's going on with the data. Let's take a look at the report using this data. Now, using that data, we see now that we've definitely got a couple of things going on here. Here's the various percentages going up the left side, with the percentage of orders needing corrections over weeks. Here we're looking for patterns and trends. We can see here definitely a downward trend over the 15 weeks. Then this nifty little thing here gives us other data. It actually gives us kind of a smooth line so that we can see what kind of shape that we have to this movement. We see here very steady improvement from week to week. If less is better, which is true in this case, we also have the data for that as well. The mean value is about 20% over that whole data set, with some deviation and some other information. It's very helpful in understanding the data. During the improve phase of a Six Sigma project, team members will use a variety of statistical and non-statistical methods and Lean tools to find underlying issues and ways to address them. In this topic, we are going to learn more about root cause analysis and a 3-step process to fix the root cause, rather than just trying to minimize the effects of the problem. There are 3 basic phases to this process. They include list the possible causes, organize them and group them into sources of causes, and then prioritize the list of causes for the next steps in our process improvement effort. Beginning with step 1, let's begin to list out the probable causes. This is often the most time-consuming step in the DMAIC improvement process. Our time could be spent conducting observations, collecting data, using techniques such as tally sheets, working with subject matter experts, and using value stream mapping to understand what's going on in the process. What's important is that we must have hard data in order for our quality tools to be effective. Some important tools we may use include cause and effect diagrams, relational matrices, the 5 whys analysis, fault tree analysis, and many other tools. Now we are going to spend some additional time on cause and effect diagrams. We categorize and group similar causes together. There are many ways we can group them. Maybe we consider where they happen in a process, or the people involved. One common way of grouping causes is called the 6 M's, which translates to man, method, machine, measurement, Mother Nature, and material. To explain the 6 M's a little bit, the man category would be it was caused by people or the persons doing the work, while the method category might indicate there's a problem with our process. This method may also help us to reveal commonalities between the causes. After we've categorized the causes, we then move on to prioritizing them and identifying the vital few that we want to zero in on. A Pareto analysis can be helpful with this ranking. Perhaps after we rank the causes, we find that the people-related causes make up the largest group. We might then explore that cause in more detail by asking questions such as, are they being trained properly? Do they actually know how to properly do the task? Are they using the knowledge base properly? Or is it something else? Cause and effect diagrams were developed by Kaoru Ishikawa, who first applied them in shipyards in Japan before and during World War II. Later, Dr. W. Edwards Deming adopted this technique as part of total quality management in Japan after World War II. The cause and effect diagram, or Ishikawa diagram, is very helpful in the DMAIC problem-solving cycle. It assists us with defining, measuring, and analyzing a project or process. In this topic, we will create a cause and effect diagram and use it to find the root cause of a problem with our process. Creating a cause and effect diagram is a multi-step process. We begin with a clear definition of the problem or effect. Properly defining the problem is as essential as finding solutions, because we must be clear about the effect, or the problem that we are dealing with. The effect makes up the backbone of the fishbone diagram. Next, we add various ribs to the backbone. The ribs represent the major categories of causes of the particular problem. Once we have added the ribs, we can label the causes. Common cause categories may include any of the 6 M's: man, method, machine, measurement, Mother Nature, or material. The remaining steps are fairly straightforward. Under each of the major causes, we must consider the key factors that come into play in our process. It may be helpful to brainstorm and write down the major factors for each of these causes. Then we may need to dig deeper into the causes to ensure we have considered everything. From there, we can sit back down with our team and stakeholders in order to study and analyze this diagram very carefully. For example, let's consider an issue with consumer loan processing. We are experiencing delays with the processing and we would like to identify the root cause of the delays. The team has brainstormed and determined that there are 4 major causes, represented by the ribs in the diagram. They include loan processing staff's inadequate skills, customers using paper applications, poor quality infrastructure when it comes to our technology and methods, and different loan amounts that may be causing inconsistencies. Once we have identified the causes, we can then begin to dig deeper to explore the key factors underneath each cause. So, for example, with loan processing, we could have lack of experience, inadequate education of the team, inadequate training, and lack of motivation or reward systems in play. Next, we review the cause and effect diagram to determine the major causal factors of the problem or effect. We work together as a group to reach agreement about a clear problem statement. There may be disagreements about this. which could be an indication that the problem is more complex than we originally thought. We will need to fully explore the process and possibly break it down further in order to get at the true root cause. We need to identify one priority to focus on right now. During this process, it is important to resist the temptation to start fixing things too soon. It's important to follow the process and get down to the true issue before we start fixing anything. In this topic, we're going to cover the check sheet, also known as a tally sheet. This is the data collection form that we create in order to capture data about our processes. We use check sheets to capture data very quickly, such as defects found in a manufacturing organization, or the frequency that a particular problem occurs in a process. A properly designed check sheet should be very easy to use and requires no experience and very little training to begin gathering data. This is a good technique for performing a simple analysis very quickly to identify what might be going wrong in processes. In a basic check sheet, we start with a simple matrix form where we list the defects in the first column on the left. Let's say that in a manufacturing process there are a number of defects that could occur with our deliverables. They can be chipped, dented, scratched, or have missing parts. We may place a check sheet on the manufacturing floor and ask the operator that each time we have a defect to make a little tick mark in the appropriate box. The operator would simply tick the boxes for each of the defects they found during the week. Pretty quickly, we'd be able to see at a glance how many total defects we had for the week, and which of these tended to be the issue. We may also accumulate the data over a longer period of time, say over a 4-week period. This will give a more comprehensive view of which of these are the main issues and how often they're actually happening. Traveler check sheets are a very powerful method where we attach the check sheet to a particular order or unit of work going through the system. And at each step in the process, we ask the operators to capture how many defects they found. For example, during the first step in the process, we would note how many defects we found. And during the next step of the process, how many defects we found, and so on. After multiple units have gone through the system, you begin to get an idea about which steps in the process tend to have the most issues. This is another powerful tool called the location check sheet. We can make an image of the item that we are assessing. For instance, in a chemical production process, we may illustrate a nozzle going through a combustion chamber, where it is increasing the energy of the gas in order to create pressure and thrust. Valves then allow the fuel to move through the pumps and into a fuel tank. This is also called a measles chart, because we ask the operators to make little red marks on the chart where they're finding problems. During the time period that we are capturing the data, we have an instantaneous view of where the problems are. For example, perhaps we identify many issues associated with the combustion chamber. Because that's the way it's designed, we can differentiate between which of the two valves is giving us trouble, or which of the two pumps may be giving us trouble. The location check sheet is very powerful and very visual. It allows us to zero in on where we need to focus our efforts first. The next type of check sheet is called a confirmation check sheet. This is a simple method to understand what steps must be performed and in what sequence. For example, in a manufacturing process, we may follow steps in this specific order. Create mixture, switch on the granulator, verify the air temperature is 64 degrees, spray it with solvent, air dry, and inspect for defects. We follow the steps in the correct order for consistency and to get it right the first time. This could also be used for things like troubleshooting technical issues for a customer on an inbound call, or completing an order entry, to make sure that we don't miss any steps, and that we ask all the right questions. Let's recap the elements of effective check sheets. First, keep it simple. If it's too complex to complete the check sheet, it won't get done. All fields on the check sheet must be marked clearly so that anyone entering the data will know what to do and when to do it. Include space to capture date and time, and the collector's name. Then identify the criteria for stratifying the data. For instance, if there are 3 different things that could go wrong at a particular step in the process, we probably want to list each one, or provide easy-to-use codes to quickly and easily fill in the check sheet. Even if we feel confident that we have designed a good check sheet, it's a good idea to run a pilot test with process users. We should ask them for feedback on how we can improve the check sheet so that it will be an effective tool for capturing data about our process. This course covers several performance metrics that are used throughout the full life cycle of a Six Sigma project. This includes the planning stage, while monitoring for ongoing performance and after improvements have been made. The metrics covered in this course include defects per unit, defects per million opportunities, rolled throughput yield, cost of poor quality, and cycle time. Measuring performance is central to the practice of Lean Six Sigma. Within the DMAIC cycle of define, measure, analyze, improve, and control, the measure element is very important. We need to determine the specific kinds of company metrics we will use. For example, if we are in manufacturing, we will be interested in scrap rates or cost of poor quality. In a supply chain, we might be looking at on-time delivery and order fulfillment. In a financial services organization or a customer service organization, we might be thinking about call handle times or the number of calls dropped. In the medical industry, you might be looking at the average days of recuperation from a given surgical procedure. There are many different kinds of metrics in every industry, and performance is important, no matter if the organization is for profit, nonprofit, or government. The concept of Six Sigma quality relies heavily on metrics and comparing a performance against a mean or target value in a process. At the level of Six Sigma quality, we would only have 3.4 defects per million opportunities for a given product or service. In order to determine if we are performing at that standard, we need a couple of things. First, we need to understand what's called an upper and a lower specification limit. They define the range of what's acceptable to meet customer requirements. This could be any attribute of the deliverable, such as a dimension, an amount of time, the concentration of an active ingredient, or any number of things that are important to the customer. If the upper and lower control limits are set at 3 sigma, we're still going to have many defects, especially if we have a high volume of product. That is why many organizations have adopted the Six Sigma methodology. Metrics in Six Sigma are used extensively, and they're used to measure different things about our process. For example, let's discuss DPU, or defects per unit. In the auto industry, one of the things that is tracked would be the number of complaints per order or per car shipped as a way of measuring quality. Defects per million opportunities examines the number of defects across the process and gives us an idea of whether we are within our specification limits and meeting customer requirements. Another important metric is called first-time yield, or FTY. And here we might be examining, for example, the number of calls we could handle on the first try at a contact center, without the customer having to call back or follow up because we didn't do it right the first time. Let's move on to the next metric called rolled-through yield. In the example of an automotive assembly plant, we will keep track of the percentage of good quality at each station or step in the assembly line. Then we would multiply those to get to our value. So if we had a 97% good quality at step 1, 95% good quality at step 2, and 90% good at step 3, we would multiply those 3 factors, and we would find out our rolled-through quality is actually only about 83%. Cycle time is another important metric because we want to measure the time to perform a given task and how much variation we are seeing in the process. For example, we measure the time it takes from a customer placing a delivery order until they actually receive the product, and whether we can get a consistent result from the process each time. Cost of poor quality includes scrap, rework, returns, and expediting that can happen as a result of not doing it correctly the first time. All of these metrics are important, and you will decide with your team and stakeholders which metrics should be applied to your process and how they will be used. Counting defects is an important task. There are many ways we can use the data that we gather during the Six Sigma practice. We want to examine the outputs of our process very carefully and capture data. We may be documenting elapsed time to provide a service, or maybe the weight or color of something, dimensions, or other attributes. When evaluating defects, we may be determining the percentage of rework required, the amount of scrap materials, or perhaps the number of complaints from our customers. We gather and we analyze all of this data to calculate the defects per unit, the overall defects per million opportunities, and the roll-through yield, and how we are performing against the entire end-to-end process. So what are defects? Our customers are actually the ones who primarily define what defects are, and generally a defect means we're not meeting their specifications. Some of the things that will have specifications could be the life cycle. Does the product function for the correct amount of time before it needs to be repaired? Or for a product that requires routine maintenance, is it easy to maintain? Is the product the correct color and size? And does it function the way it's intended to? In the service sector, meeting expectations could mean providing accurate responses within a reasonable amount of time. At a fast food restaurant, was the food prepared quickly? Did the sandwich contain the correct toppings? And was the customer treated in a friendly manner? The causes of the defects are typically found in the process, and they can include defective machinery, human error, and much more. In measuring process variability, we are comparing the attributes of our deliverable against customer requirements. Let's say that the customer requirement is the mean or bullseye of the target, but there's a range of acceptable values that are defined by upper and lower control limits. We determine, along this range of possible results, where our samples are falling. How close or how far from the target are they? Some of the things we might look at could include the weight of a food portion, the time it takes to respond to a support inquiry, or time to repair a vehicle at a repair shop. It could also be a satisfaction rating that we receive from a customer. The values that we gather with this method can be placed and plotted along the continuous scale. They will generally form a normal distribution, with data points tightly clustered around the mean, and also randomly distributed above and below the mean. These data points can be evaluated and converted directly into a sigma value. That will tell us what percentage of our samples are within the acceptable range and meet customer requirements, and what percentage would be considered defects. In this topic, we will discuss the defects per unit, or DPU. We will determine the number of defects statistically we get per unit and the average number of defects in our sample. For example, with a really simple part where we are measuring just one attribute, such as the weight, we might find that we have a tiny fraction of a number like 0.001 defects per unit. However, if we have 50 different attributes we're measuring in the part, or if we are delivering a complex product, maybe we find a greater than 5 or even 10 defects per unit. The reason we calculate DPU is to get a baseline. We need to establish where we are and how that compares to the customer expectations. From there, we need to identify our future improvement activities. In order to figure out where to concentrate our efforts, we can rely on the customer voice, a cost-benefit analysis of our proposed changes, or a Pareto analysis to zero in on the vital few areas where we will get the biggest bang for the buck with our improvement activities. We may also use this to identify nonconformance and where we need to improve our controls to get repeatable results out of this process. Now we are going to use an example of defects with respect to caps on bottles that won't seal. We will divide the number of defects by the number of units that we inspect. Before performing this calculation, it's important to define exactly what constitutes a defect for your specific situation. There's a statistical term called confidence that we need to be familiar with. Confidence is the probability that our sample size properly represents the population that we are testing. The larger our sample size, the more confident we can be. However, since it won't be cost-effective or efficient to test every single unit we produce, we will always select a representative sample. You will work with your team and stakeholders to determine what your level of confidence will be and how many samples you will test. In this example, let's say there are 1 million bottles. And if we want to be 95% confidence with a confidence interval of 0.1, we need to take at least 97 samples and inspect them. If we want to get to 99% confident, we would need to increase our sample size and inspect at least 166 samples. Defects per unit will tell us how well we are performing with respect to the defects found in our sample tests. Let's do a quick little whiteboard exercise here. Now we are going to do a little calculation here of the defects per unit, and let's just say that we have 376 defects that we actually find in this batch of parts. Well, that's good, we found 376, but now we need to divide that by how many samples did we actually look at. So if we had 6,000 samples that we inspected in which we found 376 defects, we would divide the 376 by 6,000, and that would give us the calculation of 0.063 defects per unit. So what that might suggest within 100 units. You would have 6, and for every 1,000 units you would have 63 defective bottle caps. Now we will cover the concept of parts per million and how that metric is used to evaluate our process. First, we begin with the formula we just covered for defects per unit, or DPU. But now we're going to multiply that number by 1 million. So, for example, let's say a manager of a fast food restaurant observes 100 customer orders and identifies 15 defective units. The manager can calculate the parts by million by taking the product of 15 divided by 100 times 1 million. This results in a parts per million of 150,000. Calculating parts per million allows us to consider the big picture and say, if we're going to see 1 million customers per year, are we happy with 150,000 of them having a poor experience of our quality? It allows us to think about how many customers are impacted and if that's an acceptable number, or if we need to target improvement. In this topic, we will cover defects per million opportunities. This formula gives us the mathematical possibility that a process can be defective. It allows us to standardize defects at the opportunity level, and finally, it enables the comparison of complex processes from one to the other. For example, we might use defects per million opportunities for each step in a complex product or process to examine the aggregated risk of a defect or a defective at the end of the process. This is similar to another formula, the rolled through yield of a process, but the formula is different. We add up the defect parts per million opportunities across each step of the process, add them up, and then we compare the complex processes to each other so that we can identify which processes need our immediate attention. There are 3 major components to defects per million. The DPMO calculation looks at opportunities for defects within the units that results in products or services that fail to meet the customer's requirements and their performance standards. There are 3 key pieces that make up the DPMO calculation. It begins with the measurable failure or the defect being found. Then we consider the unit or the final deliverable, whether it is a product or service, that is impacted by the nature of the defects. Finally, we evaluate the opportunity that the attribute within the unit could result in a defect. Let's apply DPMO to an example. Consider the case of an electronics manufacturing company that creates tablets. We are going to examine how defects per million opportunities for the major subcomponents and how they roll up into the end product. So in the case of tablets, each individual tablet is considered a unit, and for the purposes of a DPMO calculation, the 3 major subcomponents are graphics capability, processing power, and battery life. These components represent opportunities for a defective tablet that does not meet the specifications and what the customers expect. The first defect opportunity involves the subcomponent of graphics. An example of the opportunity for the graphics to be defective could be that the tablet is not able to play video. Opportunity number 2 would be the processing ability, and an example of a defect might be that the tablet runs slowly or doesn't run as fast as advertised. And finally, the third defect opportunity could be problems with the battery. This could mean that the tablet has a very low battery life or does not meet the advertised specifications for performance. By combining all of these subcomponents and their potential for defects, we begin to get a sense for the overall opportunity to have a failure in the tablet. If we go back, and determine the defects per million opportunities in these three components, we can begin zeroing in on the one that's the biggest culprit, and then proceed to the other ones that are less likely to fail. In this topic, we will discuss the calculation of defects per million opportunities. We begin with the number of defects found in a test sample divided by the total number of defect opportunities for that sample. Then we multiply that number by 1 million. For example, if we found 50 defects after inspecting a sample of 1,000 units, we would divide that 50 by 1,000 and get to a factor of 0.05. We would then multiply that by 1 million. Our defects per million opportunities would be 50,000. There is an alternative DPMO formula that's also very important to understand. It is different because we have the same number of defects in the sample, but we get to the DPMO by taking the sample sizes times the defect opportunities per unit. For example, let's pretend that we are making steel pipes. In this case, our testing method is a destructive method, meaning that in order to actually get the measurements, we have to cut a piece out of the pipe and measure it in 4 different places to determine if it's going to meet our quality requirements and to capture the data. Since we are taking 4 measurements per pipe, there are 4 defect opportunities per pipe that we test. Destructive testing is a case where we may want to take a specific sample size, say 10 units, every hour for an 8-hour shift. So we would have a sample size of 80 and 4 defect opportunities per unit. And then we can count the number of defects from that sample. Let's say that there were 10. By dividing 10 by 320 and multiplying that number by 1 million, we find out that the defect per million opportunities, without having to destroy every piece of pipe, is 31,250. Let's examine this in detail. So we want to find the DPMO for a process of completing application forms in a financial institution. So here we're going to want to count the number of defects we found and the number of application forms. So let's just say that we found initially 45 mistakes in our forms. Now we go on to say, okay, so let's take a look at the sample size. We're going to divide that by our sample size, which would be 300 different forms that we looked at. But we're not done yet. We now have to think about how many defect opportunities are there in each form. Well, in this case, we have 10 different fields that our operators or technicians need to fill out as they're doing the work. And of course, we're going to have to multiply that by 1 million opportunities to get to the DPMO calculation. So if we work out the numbers here, we would have 0.015, which would then be the calculation of 45 divided by the product of 300 times 10, multiplied by that 1 million opportunities we talked about, and what do we get? We have a DPMO value of 15,000. So even though we didn't find that many, 45 out of 300, because we extrapolated to where these opportunities are, we can see that our DPMO is a pretty high number. Let's move on. Now we can use DPMO to understand the sigma level. This table is populated with the DPMO numbers and the corresponding sigma values. In the previous example, we had the DPMO calculation of 15,000. So according to this table, this would suggest that we have a sigma level between 3 and 4 sigma. If we imagine the normal distribution of samples in a bell-shaped curve, one standard deviation to the left or to the right of center, the opportunity for defects is pretty high, or about 690,000 defects out of 1 million opportunities. If our DPMO is calculated as 308,000, we are probably operating at plus or minus 2 standard deviations from the mean. The defects per million opportunities decreases until we get to a 3.4 defects per million opportunities, or 6 sigma. In this topic, we will cover the concept of yield. Yield is the percentage of error-free output in a given step of a process. We use this to analyze a process and identify problem areas where we need to focus for continuous improvement. This is calculated in 2 different manners. One is called the first-time yield, and the other is called rolled-through yield. The first-time yield is typically examined at the top level for a process, whereas the roll-through yield could look at the entire end-to-end process. For example, I once worked with a large team that was examining the first-time yield and the roll-through yield in an automotive assembly plant. At each of the stations, we measured the percentage of defects while moving through the process. We rolled all of that up and found out that the roll-through yield for the entire automotive assembly plant was only about 21%, meaning 79% of everything had to be reworked or fixed in some fashion before it got to the end of the line. This gave us the basis to go back and identify which relatively few stations needed the most attention so that we could improve the overall roll-through yield. Let's consider an example of first-time yield. We have 10,000 units entering a step in the process, but we have to scrap or rework 1,000 units, so we end up with 9,000 acceptable units. If we do the calculation of the 9,000 divided by the original 10,000, we would find that our first-time yield, also called first-pass yield, would be 90%. Let's calculate first-time yield. We take the number of units with no defects and divide that by the total units inspected. We then multiply this number by 100. This gives us the percentage of the units that make it through the process defect-free. Let's say that we had 18,230 units that we processed with no defects, out of a total of 20,500 units that we actually inspected. We divide the 18,230 by 20,500, and we get to 0.889. We multiply that by 100 to determine a first-time yield of 88.9% for this process. In this topic, we will cover the roll-through yield calculation, or RTY. RTY is much more useful to us as a metric than first-time yield. So, for example, if we have 1,000 units and 100 of them have to be scrapped, then we are left with just 90, which calculates as 0.9 or 90% first-time yield. Then we lose another 50 units at step 2, leaving us with about 94% first-time yield. If we imagine that this is a multi-step process, we can skip some steps in between and resume at step 10. At this point, we are down to 795 units entering the final process, and 690 units exiting as good, acceptable units at the end. The last step would have 87% first-time yield. At a glance, none of these steps are particularly bad, with first-time yield percentages in the high 80s to 90s percentile. But there's more to the story. The formula for roll throughput yield, or RTY, is the product of the first-time yields of each step of the process. The FTY of each step is successively multiplied by the next through a series. Let's evaluate some actual data. The first-time yields of the first 3 steps of a process are 0.987, 0.958, and 0.996. While these numbers are quite good on their own, when we multiply them, we get a product of 0.942. We multiply this times 100, giving us a roll-through yield percentage of 94.2%. Let's examine this process a bit closer. Each step in this 3-step process has a first-time yield well above 90%. So looking solely at these numbers might lead us to think that this overall process is doing pretty well. However, by rolling the yield through from one step to another in the process, we can reveal a very different picture. We calculate that roll-through yield is only 84.9%. Now, that's a big deal. When we think about the whole process end to end, it isn't running at all like the 95 or 93 or 96 that we're achieving at the step level. We are experiencing about 15% of everything going through this process being scrapped. So the correct way to assess yields is by using this continued calculation. Again, remember that yield is a percentage of the product that has no defect. If we take 1 minus the yield number, we get the percentage of the end product that is defective, or the PD for the small d here in the parentheses. So for example, if we had a first pass yield of 0.9345 and we did the calculation of 1 minus that number, we would find that our probability of a defect factor is 0.055. You and your team may find it helpful to keep a Six Sigma conversion table on hand. Using a table such as the yield and sigma level, we can take a probability of defect calculation number and quickly find the sigma that it correlates to. In our previous example, where our probability of defect factor was 0.0655, we can determine that we were actually only operating at about 1.5 sigma. In other words, we are operating at only 1.5 standard deviations to the left and to the right of the goal for this particular process. So that particular example shows us that maybe we're not doing so well, and there's quite a bit of room for improvement. Another helpful conversion table might show us that if our yield is 30.9%, or if our defects per million is 690,000, then we are operating at a 1.0 sigma, and so on. So, for example, with that 93.3% yield, we are going to experience 66,800 defects per million, which is definitely not a good thing for our customers. Metrics such as rolled throughput yield are very helpful in showing the actual performance of our overall process from end to end. With that data, we can determine where we stand in terms of Six Sigma performance. In this topic, we will discuss the cost of poor quality, which is something even the best companies struggle to get a handle on. What are these costs? They are all of the costs, both visible and hidden, that eat into the profit margins of an organization. Costs of poor quality could include activities that don't meet the desired outcomes or activities that are inefficient. Maybe we are achieving acceptable quality, but it takes us a long time to do it, so our operation is too slow. Or perhaps we're utilizing a lot of resources on rework instead of making our deliverable right the first time. There is a calculation for the cost of poor quality. It is the actual cost minus the minimum cost. If we did everything correctly and efficiently the first time, that would be our minimum cost. Then we figure out what we are actually spending. The difference between them helps us to determine the cost of poor quality. There are many types of costs in the area of cost of poor quality. The most severe ones are when the customers reject the deliverable. At that point, we have already created the entire deliverable and shipped it. It is in the hands of the customer, who will be dissatisfied. There will be repair costs, rework, and testing costs, but it goes well beyond that. What about the impact to our reputation in the market? Are we utilizing our resources efficiently? How much time and money do we spend on corrective actions to make the customer happy? Not to mention the confusion and the loss of motivation to our employees. The cost of poor quality can really add up. We can use statistics to interpret the cost of poor quality measure. It's important to understand that for a non-Six Sigma process, the cost of poor quality can be extremely high. I was once working with one of the world's most highly recognized and reputable insurance firms, with their defined benefits organization. They were looking at a process that included about 140 different process steps from the time somebody retired to when we cut the first check for the retirement. We went through the process, and I asked everybody to add up the time spent across the entire process with respect to inspection, rework and verification, and steps that weren't right the first time. They were shocked to find out that 65% of the total cost of the process was due to some type of correction or rework throughout the entire process. Pretty scary. A company running at 4 Sigma could see as much as a 20% of sales revenues being lost. If we are at 5 Sigma, we're doing a whole lot better than that, with closer to 10% lost. Despite our best efforts, some of the largest companies in the world could easily be operating at 8 to 12 billion in losses per year due to cost of poor quality. Next, we will work to establish a baseline and a goal to address the cost of poor quality. We can use the DMAIC cycle to do this. At the define stage, we determine what our current sigma level is in order to understand our true current cost of quality. This may include doing some measurement and data collection to set an accurate baseline. This will allow us to create a clear project charter about what we are trying to accomplish, and provide the basis to track the benefits after our project. We can also use the baseline of cost of poor quality to prioritize the portfolio of projects, so we know which projects to take on to maximize the benefits to the organization. You and your team may find it helpful to keep a Six Sigma conversion table on hand. In this case, if we determine our yield, or the proportion of deliverable with no defects, we can also determine how many defects per million opportunities are in our process. This allows us to then identify which sigma we are operating at. For example, if our yield is 0.945, we can determine that this indicates a 3.1 sigma. In terms of cost of poor quality, our operation has exposure of 30% for the cost of poor quality for the organization. As we improve to 3.5 sigma, still as much as 20% of our production is being lost as waste. At 4.6 sigma, we lose 10%, and at 4.98 sigma, we are at 5% waste. But it doesn't stop there. As we improve our sigma performance and drive down the cost of poor quality, we should also consider how this benefits us in other ways. For example, what do you suppose the impact to customer satisfaction would be as we increase the sigma? What about the impact on market share and top-line growth? If you are moving from 30% to 10% or less cost of poor quality, you are going to see multiple benefits for the entire organization. In this topic, we are going to cover the categories of cost of poor quality. Every organization is unique when it comes to the cost of poor quality, and it's manifested in many different ways. There are three basic general classifications of quality costs that are pretty consistent across most organizations. First of all, we have prevention costs. These include all of the effort and the work to prevent defects from happening. These can include audits, training, following processes, and maintaining equipment properly, and of the activities to get it right the first time. From there, we have appraisal costs. This is typically where we are going to conduct measurements, inspect our deliverable, and perhaps conduct destructive testing. And then we have failure costs. These are the costs that we incur when there is an actual failure or defect, like scrapping parts in-house, which would be an internal failure. And then there's external failure costs. When the deliverable is in the hands of the customer and they experience the defect, they become dissatisfied, and we must ask for warranty, repair, or replacing the deliverable. There are many examples to consider with respect to the cost of poor quality. Again, the categories are prevention, appraisal, and failure. Prevention activities may include planning, pre-production reviews, engineering the product, housekeeping programs, or a zero-defect program. The point of prevention is to take all of the necessary action to do things right and prevent defects from happening. Appraisal includes testing and inspection, audits, security checks, safety reviews, and many other kinds of costs where we are trying to identify issues with quality. We're basically making sure that all of the efforts we have made in prevention are actually working. Then, of course, we have the actual failure costs themselves. The most expensive internal failure costs include scrap and rework. Thankfully, the defects were found before they got into the hands of the customer, but it is still expensive and time-consuming for us to address it after we have produced the deliverable. Quality issues can be caused by, or can cause, issues with morale, absenteeism, and more. External failure costs can include product recalls, customer service problems caused by errors, and late payments from dissatisfied customers. As we move along the scale from prevention to external failure, the cost of poor quality increases, as well as the customer exposure. There are hidden costs to poor quality. Unhappy customers can take their business elsewhere. The cost to replace a customer can be 3 to 5 times the cost of maintaining a customer. Unhappy employees can result in poor morale and high employee turnover. High employee turnover is a vicious cycle. Not only can we spend 100% of the cost of the employee just to replace them and train a new one, it creates a vicious cycle because new people are not as experienced or well-trained. We may then experience internal process problems. While these costs tend to be hidden, they are certainly expensive to an organization. In this topic, we will discuss cycle time and lead time. Understanding and managing these metrics within organizations is critical for customer satisfaction, efficient processes, and competitiveness in the marketplace. It's important to differentiate the difference between lead time for an overall process versus cycle time of the various steps within a process. In this example, we have the cycle times and lead time for the process of publishing a book. The cycle time for the task of meeting with the author is 2 days, but that's part of the bigger picture of the end-to-end process cycle time of 14 days, which is made up of all of the activities across the value stream. Each of these activities has its own cycle time. In order to evaluate a process, we can create a value stream map with headings for each of the activities in the process. In this example, it takes 2 days to meet with the author, and 3 days to read and approve the manuscripts. Then we move on to the proofing stage, which takes 5 days, and another 2 days for the final proofreading. In the final 2-day activity, we post our final publication, perhaps an article, blog, or other announcement to market our products and services. There are many benefits of cycle time reduction. Taiichi Ono, considered the father of the Toyota production system, said that the essence of lean is to continually shorten the time it takes from the time we get an order to the time we fulfill the order and get paid. It's important to reduce waste, but we can't do that without removing unnecessary steps. That leads to significant cost reduction and the opportunity to increase productivity because we're not wasting time and energy on things that don't add value for our customers. Overall quality improvement is realized because in order to take time out of a process, we have to examine the process very carefully. We can learn a lot about what is slowing things down. It could be quality delays for inspection and rework, reviews, or other issues. By getting it right the first time, we can reduce the overall cycle time or lead time and also see big improvements in the quality. We can also decrease product time to the market and improve customer satisfaction. Other major benefits could include improved cash flow by reducing cash required to hold inventory or collecting cash for products that are delivered faster. We can also reduce the amount of working capital that the organization requires in the form of inventories and work in process that's in the system. There are huge benefits to an organization when you experience a 30 to 70% reduction in cycle time. For example, return on assets, increased revenues, less inventory, shorter delivery lead times, and faster speed to market are all things that can be dramatically improved by reducing overall cycle and lead time in the process. In addition to these direct benefits, the dollar value of acceleration in projects could mean millions of dollars for larger organizations. In addition, quality also improves when the cycle times are shortened. We need to think about project overload as one of the major causes for long lead time to get to market. And a longer lead time to market means lost revenue. Another benefit, of course, should be improving customer satisfaction. Now let's explore the breakdown of some of the key elements that make up cycle time throughout the entire business cycle. We build in time for concept and feasibility studies. If we can do these quicker, we can move forward the beginning of the design and development cycle. And if we can accomplish that more quickly, it means we can get to market sooner. This means we get a bigger market share of the market and differentiate ourselves in the marketplace based on speed. Then when customers place orders to us, we can continue to collapse that time and reduce inventory and the cash-to-cash cycle. So think about this as a kind of cascading flow across the whole process around concept feasibility, design prototyping, piloting, production, and phase-out. Anything we can do to shorten this end-to-end flow in the overall cycle is a cycle of continuous improvement. In this topic, we will discuss collecting key cycle time data to be used in the calculation of takt time, an important production metric. In this example, the process for manufacturing precision tools has 3 steps: attaching a lever, inspection, and packaging. For each of these tasks, we enter the observed times for each in a worksheet. We typically would record about 10 sets of samples as a minimum, but to keep it simple, we are only using 6 in this example. Then we will want to add some key parts of the data that we observed, including the most frequently recurring value, the high value, and the low repeated time. The most frequent value can likely be repeated without a whole lot of difficulty by operators. The high time helps us to understand the worst-case scenario, and the low repeats represent a best-case scenario. So if we want to improve performance, we may employ some Lean Six Sigma tools to be able to perform more consistently at this level. It's important to recognize that we can have multiple operators performing the same work simultaneously, or a single operator performing multiple tasks. So, our cycle time worksheet needs to be designed to reflect the actual production processes. When we sample 6 instances of this total cycle time, we can conclude that the most frequently recurring time is 7.6. So what is takt time? Takt time is the required rate of production per time period needed to meet customer demand. Usually it's expressed as a function of units per hour, but it could be daily, weekly, or in some cases even monthly, depending on the process. Process cycle time needs to be balanced to meet takt time, so that we're not overtasking or underutilizing our resources. If our cycle time is greater than takt time, then we're going to have a problem with bottlenecks and not meeting customer demand. We can use our Lean Six Sigma tools to break that bottleneck or figure out how to balance the work differently. Conversely, if the cycle time is less than the takt time, we run the risk of having resources sitting idle, waiting for work, and excess production. Being able to balance takt time and process cycle time will allow the operation to run at the appropriate pace to meet, but not exceed, customer demand. Let's go through a quick little calculation. So let's say that our customer demand rate is about 120 per day, and we need to produce this to keep up with customer demand over an 8-hour shift. So this is the grand total of about 480 minutes of available time that we have for the day. What we now want to do is divide this by 120 to get to our takt time. If we do that calculation, we're going to find out that this works out to about 4 minutes. However, it's not the entire story here. From this 480 minutes, we'll often subtract the breaks and the lunches, and maybe planned meetings that people will not actually be working. So we could have a more accurate number for the takt time. So let's say that we're going to have 40 minutes a day for breaks and other purposes. So I'd want to change that calculation and subtract that 40 minutes from the 480, and instead we'd had 440 minutes available to do the work. This will give us a different result because we'd now divide this by that 120 per day needed by the customer and get a different statistic. This will give us about 3.667 minutes, or if we round that up a little bit, 3.7 minutes average takt time that we want to look at. This would be what we would actually want to be paying attention to as we run through the day for hour-to-hour production. You might want to use this as a much better number to know that we're keeping up with the work throughout the day. This course covers the tools and techniques that members of a Six Sigma team would use to select a project, define what the scope of the project should be, and identify who the project stakeholders are. It also covers how to examine the processes that you are trying to improve, and identify the various components of the process, such as inputs, steps, and outputs. When determining requirements, we have 2 different important perspectives to understand. The first is the voice of the business. This can include the board of directors and executives, stockholders in the organization, employees, and suppliers. The voice of the business must also include government mandates, information technology, and human relations requirements. And we can't forget the operations part of the organization, and the groups like engineering and quality. They all contribute to the voice of the business. We also have the voice of the customer. Remember, the customer should drive us in the implementation of Lean Six Sigma. Many different tools exist for us to capture good information from customers, including customer surveys, customer feedback mechanisms, and certainly specifications that customers give us regarding their expectations for products and services. There are important processes for capturing business requirements, also known as the voice of the business. It typically begins with the overall mission, vision, and objectives of the organization. We might leverage tools like policy deployment or management by objective. We typically focus on things like internal efficiency and productivity. These are often associated with value stream management and understanding the entire delivery of value across the end-to-end supply chain. This is influenced by a number of factors, including the need to solve problems with the process. And we need to remember we are never done making improvements. It's all about continuous improvement, and that is a never-ending journey. We do have constraints, including the constraint of the budget. We can't necessarily throw money at everything. We're also constrained by compliance and regulation requirements. For example, the Federal Drug Administration, or FDA, has all kinds of requirements that need to be met if you produce foods or drugs. The voice of the customer, capturing their information, is all about gathering the requirements and precisely documenting them. Typically, we need to define requirements as quantifiable terms that relate to specific features. The voice of the customer includes important things, such as a complete set of customers' needs, expressed in their own words, reflecting how they view, use, feel, and interact with the product or service, and we need to prioritize these needs based on their importance to the customer. Staying in tune with the voice of the customer helps the organization remain relevant at all times. In fact, Peter Drucker was credited with this statement: "Only two things in business make money, marketing and sales, and everything else is a cost." Without a clear voice of customer input, how do we make sure that we're developing and innovating the right product and services? Let's put the voice of the business and the voice of the customer all together in a Venn diagram, where on the left side we have the important voice of the business inputs, like the need to be profitable, to manage our costs, and continually improve productivity to get good results. Then on the voice of the customer side, we need to include the customer's perspective on what adds value, the fair market price, their requirements for durability and product life cycle. And finally, what are the important features they care about the most? That all comes together in the middle of our diagram with our quality practices, how we design and deliver our customer support, and how we execute on the end-to-end supply chain to deliver the products and services to the customer. In this topic, we examined the voice of the customer process. It includes 5 basic phases, starting with defining the voice of customer process goals. Then we must identify the customers we will gather that information from. In the third phase, we develop a plan about how we're going to collect the data in the best possible way to accomplish our objectives. Then we need to analyze the data and determine the specific customer requirements that we're going to comply with in the design or improvement of our processes. We use the voice of the customer process to determine what problems we should be fixing and what we should be improving, and also to identify where we need to innovate. We can also use the data we have collected for a technique called Design for Six Sigma. If we go back to the beginning of the phases, the first one is to define voice of customer process goals. In order to accomplish the best design or process improvement at the end of the phases, we must first start on the right track with Phase 1. Next, we will explore each of these phases in more detail. The first is defining our goals. What is it that we're actually trying to accomplish? We need to write a very clear purpose statement that explains the problems we're trying to solve and how we will use the information that we gather. We need to be very clear about our process goals. From there, we can move on to identifying our customers. There may be particular geographic or demographic breakdowns that we may want to pay attention to, including age groups, cultural references, and things of that nature. We may also research various segments of the market. For example, people that tend to buy a certain kind of product or service. By taking these steps, we begin to pinpoint which customers we'd like to interview, survey, or otherwise engage with. Then we can begin developing our plan and collecting data from our customers. In this phase, we clearly define what information we're seeking and the best method to get it, whether that's a survey, interviews, Delphi groups, or other methods. Once we establish our plan, we will execute it by conducting the focus groups, surveys, and interviews. We could also mine big data or social media data to give us additional information to feed our process. After we have collected data, we will analyze it and determine the next steps. During this phase, we can use different Six Sigma tools like Kano, quality function deployment, and critical to quality trees. We can also begin to identify trends that we need to be paying attention to. For example, in the Kano model, we determine which features and functions have the attribute of more is better. A good example here would be that higher gas mileage is important to the customer. So the better the gas mileage, the better they like it. We also determine which factors delight them, the things that would really make them excited about our product or service. We also identified the key dissatisfiers. Dissatisfiers are the expected things that, if they're not present, will dramatically reduce the customer experience and maybe cause them to go away. We also use these tools to identify trends and become innovative with our design cycle. After we have analyzed the data, we determine the requirements and translate those requirements into actionable goals and actions we need to take. For example, if we need to improve quality, we might use the critical to quality tree to determine the critical Y outputs from a quality perspective. We can determine the key components that drive the value, drive the function, and drive the Y outcome relating to a customer requirement. We can also identify which processes to address first to improve overall performance. In this topic, we will discuss the use of data to understand our customer requirements. We need to translate those requirements into goals during the define phase in the DMAIC cycle. There are many purposes for collecting the data. We would like to identify customer preferences and needs and any urgent problems that require immediate attention. It would also be helpful to know how we can gain a competitive advantage with innovation in our product or service. What are the desired levels of quality and functionality that customers care about most? And how can we measure customer satisfaction more effectively? There are many dimensions we need to think about. Collecting customer data may inform us about the unmet needs for our product and service, or if there are other products and services we could provide that we aren't providing today. What are the shifts and preferences in the marketplace that we should track in order to stay competitive? We can collect data from a number of different important sources. Data sources can be derived from direct interaction or through indirect sources that already exist. On the direct interaction side, one technique is direct observations. This could include literally standing in a retail store and paying attention to behaviors, or maybe capturing data from cash register receipts as customers exit an establishment. Another direct interaction technique is interviews. This is a very powerful technique to get one-on-one input and feedback from folks. We also have focus groups and Delphi groups, and the use of surveys, both in person and online. There are also indirect sources of data collection. These indirect sources often already exist. For example, we may have outputs from other projects that we're doing. There are industry experts like the Gartner Group, or J.D. Powers for quality satisfaction surveys in the auto industry. We also have market watchers like Consumers Reports, and we can leverage things like big data and data from trade associations and published consulting studies. It's important to recognize that once we have collected accurate and reliable data, we need to convert that data through a process. This process allows us to convert that raw data into useful information that can be acted upon. We may use this information to take a different approach in product development, in the way that we deliver the product, good, or service, or with the implementation of improvements. The key here is that this needs to be actionable. We must clearly identify and state what we need to do as a result of having this information. The customer feedback process is also critical. We determine the method we're going to use to gather the input of the customer feedback, whether it is surveys, end of service, data collection, paying visits to the field, making observations, or talking to the customers. We then convert that feedback into a process that results in an output of information that we can use to act upon. After we have made changes is when establishing a feedback loop is critical. We must go back to the customer and validate that the change had the desired effect on the customer. Are we noticing that something has changed in the marketplace by what the customers are now telling us? Are there shifts in demand? Or are there shifts in preferences? Do we have competition entering the market? Are we observing competitors exiting the market, and do we need to react to that as well? It's often the customer feedback loop that keeps us informed about these changes, so the benefits to creating the feedback loop are many. We can validate customer data and learn new information to support ongoing continuous improvement process in the practice of Lean Six Sigma. There are 4 key data collection methods that we will discuss in this topic. They include direct observation, interviews, focus groups, and surveys. We use these data collection methods to gather voice of the customer data. Direct observation is always very powerful because we get to watch the actual interaction of the customer with a product, service, or process. So for example, standing back and watching how a sales associate handles somebody in a store, or observing the end-to-end process of applying for a license at your local Secretary of State office. We're able to gather realistic information about the actual customer experience. What were the positive and negative aspects of the interaction? Did we witness some non-verbal signals? Are we encountering issues and opportunities that may not otherwise be obvious, or things that the customer may not even notice themselves? Interviews are an incredibly powerful technique, and they're a great way to gather individual perspectives versus group data collection. There are many benefits to using interviews. We can conduct them in person, or we can do it by phone. We can get a unique perspective from each person, and through open-ended questions, we can pursue unexpected lines of communication. We can also ask some follow-on questions and learn a lot about customer viewpoints and the data that goes along with them. We can also gather insights that could lead to innovation. Interviews also create the opportunity for two-way communication, so we can confirm understanding of the question and confirm we understood what the response was. There are some limitations to interviews. It's probably the most expensive technique to collect data. It's costly and time-consuming to convert the data, to write it all down or record it and transcribe it, and then put it into a form that we can analyze using Lean Six Sigma tools. In-person interviews are very powerful, and one important interview concept is something called meta talk. Meta is Greek for above and beyond, and talk stands for the things the interviewee is not saying with the words. We want to pay attention to what kind of rapport we are developing. Can we get visual clues and make eye contact? Some of the visual clues we may want to pay attention to are they comfortable with the topic we're discussing? Or can we sense a level of discomfort with the conversation? Are they confused? Perhaps need more clarification on the topic? Are they angry? Or are they happy? What kind of emotion is associated with the product or service? If there is interest or if there is apathy and a lack of interest. All of these things are powerful attributes of the interview that are very difficult to ascertain in a survey that allows for no live interaction. Now we will discuss phone interviews in more depth. Phone interviews, much like in-person interviews, allows us to assess a wide variety of people. We can use this technique to address some fairly basic or simple issues that you may not want to tackle or address in an online survey. We can gather information very quickly, and it can be done at a lower cost because we don't have to travel anywhere or provide a place to meet. However, there are some issues to be aware of. First of all, we will not have any visual clues. We can't benefit from the meta talk we would observe in a person that we can see. We'll need to focus and listen very carefully to the voice and ask good follow-up questions. Another issue with phone interviews is that often people will not open up and share what they really think. This could be a fear that we could be secretly recording what they're saying, or maybe they just don't feel the human connection as we're talking to them. Focus groups are an excellent method to use where we can gather feedback from a lot of customers all at the same time. It's great for dynamic brainstorming and gathering many ideas and inputs to the problem we're trying to address. It's not nearly as restrictive as surveys or individual interviews, where we have to keep everything scripted, and we can use visual aids to promote conversation. At the same time, there are some limitations and things to be aware of. First of all, we have to have excellent facilitation skills. We don't want to allow this group to fall into groupthink, or have a few vocal individuals or influential people in the group who sway other people's views. In a group like this, some people may feel fearful, or they may be worried about not making a good impression on others, or not having anything helpful to share. Those individuals might shut down and not share as much information as they could. Finally, we have surveys. They are a very powerful and arguably the most inexpensive way to gather quantifiable data. We can use this technique in conjunction with other methods. Surveys are useful for basic or simple issues that we can get on paper, and it's a great way to collect a lot of data in a short time. However, there are some issues with online surveys and paper surveys. For example, it can be difficult to write questions in a very straightforward manner that doesn't allow for confusion. Maybe there are cultural and demographic issues that participants could misinterpret by the way we word our questions. We could also have varying degrees of reading comprehension on the part of those that are taking the survey. If it's an online survey, there may be issues with technological literacy or access to computers. Maybe there's a fear of how we'll use this data, and participants may not give us a straight answer to some of our questions. This is particularly true when we're doing internal voice of customer surveys with current employees of an organization. In summary, there are a number of excellent tools available to collect data from our customers. They include observation, interviews, in person and by phone, focus groups, and surveys. When working to understand customer requirements, there are three key areas we need to pay attention to. For a particular product or service, what are the must-haves or basic expectations? What are the needs that the customer may or may not have stated? From these needs and expectations, we must identify the key priorities to focus on as an organization moving forward. We will translate that information into particular product features, performance measures, and specific opportunities for improvement for Lean Six Sigma projects. Let's begin with the key area of customer expectations and what they want from their experience with us. For example, imagine you're going to the local coffee shop to get a cup of coffee or a hot cup of tea. The basic requirements when you walk in the door might include, I want it to be hot, I want it to be quick, and I want to pay a fair price. But once your basic requirements have been met, there are other things you might expect, like condiments. Maybe you like to use half and half or skim milk, or maybe once in a while some cinnamon. Then there is a level above the expected requirements. These are the things that we desire. These could include the pleasant aroma of the coffee and the experience in the store. Then finally, there may be some nice surprises or unanticipated factors. Is there a wow factor in this experience at the coffee shop? Maybe there are free newspapers available to read while you're there, or a promotional discount on your usual drink, or a customer experience that is especially friendly, like remembering your name from the last time you visited. Customer needs can be broken down into 5 key areas. The first one would be stated needs. For example, if I'm going to go into the store to buy a new shirt, my stated need is, I need to buy a new shirt. I'm going to go into the store and I want that to be quick and painless. Then I have the real needs, which might include, I want this shirt to make me feel good. I want to like the way I look in this shirt. I also may have some perceived needs, including that it must fit right, or it must be a fair price, and it's got to have a nice appearance. I probably have some cultural needs as well. For example, if I'm going to wear this at work, what will my coworkers think? What will my peer group think about this particular shirt? And then there are unintended needs. These are the things I may not have thought about that could be a delight factor. For example, it could be very stain-resistant material, or the shirt could be extremely easy to maintain in terms of keeping it clean. Now let's discuss the product needs that a customer may have. When I bought a smartphone, here are some of the things I cared about. I wanted it to be convenient. I was trying to find a particular phone I could buy nearby or easily buy online. I want the phone to be safe and secure. Will it protect my data? Does it have simple and intuitive features that I can follow and easily use? Does this phone actually make me a better communicator? And can I readily get my questions answered with online help? How about the service for that product? Is it fast? Do they get it right the first time? Or do they have to make me wait and go through a whole bunch of steps to get it done? And then finally, what is the customer experience like? Are they friendly? Do I feel appreciated? Do I feel important? Next, we will explore the service needs. There are some typical things we will experience as we move through a service needs cycle. It starts with convenience. Then we ask, did I feel like the people were courteous, paid attention to me, and actually cared about what I had to say? Did they have empathy for what I'm going through? Were they competent and reliable? Did they follow through and do what they said they would do? Were they responsive? Did they listen carefully to what I had to say? Did they capture it right the first time and make sure that the corrective action was taken? If they came to my house to provide a service, did they act in a responsible manner? Or, if I went to their facility, did I feel safe? Did I feel like I could trust that they were going to do the right thing for me? If I went to their location for service, were the facilities operating as expected? Was it well lit? Was the bathroom clean? Was the furniture comfortable? Was it quiet and soothing to be there? When determining if our service needs are being met, we must answer these kinds of questions. Next, we have customer priorities. There are three key areas we need to think about. The main one is, what are the priorities of our customer? What are those vital few biggest things that we need to pay attention to, that with the least amount of effort, we could have the greatest impact on what our customer actually cares about? Can we meet customer needs and drive some wow factors? Can we address any of the dissatisfiers that could dilute the customer experience? Finally, we have to listen to the customer and prioritize which of their expectations and needs are most important. Project selection is the very first step in any Six Sigma initiative. We need to determine which project we should tackle first. The type of project we select will often dictate which Lean Six Sigma methodology we're going to use. Let's explore the key criteria for project selection. These can include the impact to the customer. Is this really going to make a difference to them and cause them to stay with us or buy more of our products and services? What are the overall benefits? We use the tools for voice of business and voice of customer and other techniques to understand the overall process and the overall benefits. Next, we need to consider sponsorship. If we do not have a motivated and engaged sponsor, we can't succeed. We must have top management support, executive oversight, and resources to be successful. Next, we need to have data. Six Sigma by nature is a data-based approach where we define and measure our entire process. So if we have no data, we can't move forward. Data collection may even be one of the key steps before we can charter the project properly. We should determine if we can make an impact on quality as well. Are we going to actually move the needle with respect to reducing variation or defects? Is the timeline reasonable? Usually we want to get something meaningful done inside of a year, if not months. What about resource availability? Do we have the right kinds of resources to support this project? Who needs to be involved? How much time do we need them to dedicate? And do we have the right funding to support success on this project? There are several keys to consider regarding the steps in the project selection process. The first starts with the short list of project opportunities. What are we actually trying to accomplish? What's the key selection criteria for this project? And what are the prioritized outcomes we want to pursue? Which of these project opportunities has the greatest promise for success and positive impact? And then finally, you've got to pick the right projects. We can't select everything, so we must boil this down to the critical few that can make the biggest difference. The 80-20 rule, or Pareto's law, states that only about 20% of the causes creates 80% of the results. If we select the right projects and tackle the right causes that are leading to most of our issues, we are likely to observe a tremendous impact on our goals. Priority matrices are a very useful way to determine which projects should be chosen first using a scientific approach. A matrix is made up of established criteria, weighting of each of those criteria, and then the use of a scoring and weighted score factor to determine which projects we should take on first. You and your team will determine how the criteria will be scored. For instance, scores may be assigned to a scale of 0 to 10, with 0 as least favorable and 10 as most favorable. The weight for each criterion is multiplied by that score to get to a weighted score for each one. Each project in the resulting shortlist would be scored individually, and then we can compare the total scores to determine what goes first, second, and third in our portfolio of projects for execution. Let's follow this example row by row. First of all, we have sponsorship and top management support. How important is that to us for success of the project? This has been given a weighting of 0.016 out of a total of 1. Then we have the project benefits we expect. This is given a higher weight rating because we want to impact the external customer. We need to drive impact for our shareholders. What kind of bottom line benefit do we get from this? How does this help employee morale? How does this drive improved customer service? What about the internal customers? And are there other impacts from a benefits perspective, such as our suppliers or the environment? What types of resources are needed? And are those resources available? How important is that to us in project success? It is weighted a 0.17 out of 1. Do we have the right scope in terms of the returns on the investment we want to get from this project? Are we clear about the deliverables? Is the time to complete valid? Are we going to do this quickly? Will we achieve the results we want in the time frame we need to? Will it make an impact on our customers in a timely manner? What kinds of team membership requirements do we have? Are the right people available? And then finally, how stable is this process? Is it already basically under control? Can we count on it to repeat once we make our changes? All of these things go together. Finally, it's very important we remember that projects can have different criteria and different weighting schemes depending on what's important to the organization in terms of meeting its strategic goals. So we might give higher weight based on the needs of the business, and that will be determined on a case-by-case basis. Let's discuss some of these attributes in a prioritization matrix and how we use them to compare one project to another. We have the various factors of sponsorship, benefits, resources, scope, time to complete, etc. And then for each, we have the weighting for Project 1, Project 2, and Project 3. We score each of the criterion. We can then follow these down and come up with a total weighted score at the bottom. When we compare the projects, we have total weighted scores of 6.6, 6.81, and 7.01. The project with the highest value is the one we want to tackle first out of this portfolio of 3 projects, followed by the next highest, and so on, until we have completed all of the projects on our shortlist. There are 3 key Lean Six Sigma methodologies we will focus on in this topic. They include Six Sigma DMAIC, Define, Measure, Analyze, Improve, and Control, Design for Six Sigma, or DFSS, and Lean Kaizen. The purpose of DMAIC is to go after sources of variation. It's a data-driven approach to tackle very specific defects or a process step. Design for Six Sigma is more associated with the front end of processes. It could also be known as Design for Six Sigma Quality, Design for Manufacturability, or Design for Assembly. And then finally, we have Lean Kaizen, which is where we attack sources of waste and we reduce the time for processes. This is usually associated with some kind of process or value stream mapping activity as well. DMAIC, or Define, Measure, Analyze, Improve, and Control, is highly suitable when we apply it to the practice of Six Sigma when we have a fairly clear problem statement and a specific desired outcome. DMAIC involves the many little X processes that have an impact on our Y output for the process. DMAIC is very good for problem solving and helps us to address very specific process steps. We can identify where we need to improve the function or the capability of a service step, or reduce the variability that we're experiencing. Design for Six Sigma is used when we're creating new products, processes, and new services. The chart is used to illustrate this concept. On the left axis, we have the relative cost to implement the changes, along with an escalating scale from bottom to top. Across the bottom axis, we have the phases of product development and execution. So we have research, design, development, and then going into full production of the product or service. Design for Six Sigma tends to focus at the beginning of phases, primarily around research, design, and development. This is where we are determining how we're going to design the product and service to deliver high quality. In addition to quality, there are many other attributes, like low maintenance, easy to assemble, or easy to manufacture. As we move into the production phase, Design for Six Sigma may still be in play, but we're more likely to use techniques like DMAIC and Plan, Do, Check, Act, and the application of Kaizen as we move into the production cycle for most organizations. Let's examine Lean and the practice of Kaizen a little closer. Kaizen breaks down as Kai, to change or make different, and Zen, for the better. It's generally associated with a team-based approach to improvement. The Kaizen Blitz tends to be correlated with a short interval, narrowly focused project, and usually lasts 1 to several weeks. We use Kaizen in conditions where we can expect a high impact on efficiency, with a low level of effort, and we know there's a high probability of success. The project is not politically charged, and it's easy to get people to agree with and support it. Also, we may have a lot of inventory, or work in process, known as WIP. We would like to reduce this inventory and any associated bottlenecks. Taiichi Ohno, the father of the Toyota production system, described Lean as reducing the time between receiving the order and getting the money for delivering a product or service. Kaizen is one of the methods we use to do that. In this topic, we'll answer the question, what is a stakeholder, and how do we identify and manage stakeholders? A stakeholder can be any number of folks with a vested interest in our project. Primary stakeholders can be suppliers or a sponsor, those who actually do the work, our customers, and anybody else that can be directly involved with the project. We also have secondary stakeholders. These could be folks in accounting, engineering, sales and marketing, human relations, the quality organization, and perhaps in supply chain as well. They can all have a stake in this project from the perspective that they can support it. They need to be involved, or they're going to need to do something differently as a result of this project. So we have to think big and be very inclusive when we work to identify all the stakeholders that would be impacted by what we're about to do. Identifying stakeholders often starts with a brainstorming session with the project team. We may create a list of everybody we think could be an important stakeholder. An important technique that can be helpful here is called the SIPOC diagram, or suppliers, inputs, process, outputs, and customers, and also sometimes requirements. A SIPOC diagram is a very useful tool we use to make sure we've captured all of our stakeholders. We need to ask who will be impacted, who's going to provide the inputs, who will use the outputs of this process. We may also need to start thinking about who might hamper the process, because not all stakeholders will necessarily be supportive. Stakeholder management is a critical aspect of any project's success. Stakeholders might fear that they can lose their jobs or may lose control over their work. Or maybe they'll have new assignments that they don't like. Sometimes just the idea of change can create anxiety or negativity. We need to consider these factors such as the stakeholders' level of interest and the degree of impact on them, their coworkers, their function, or their customers. And then finally, what is our goal? We need to improve the attitude about our project and control the influence over it. We can do this through meeting with stakeholders, frequently discussing the merits of the project, and keeping them informed of positive developments. We can also share data and outputs transparently, check in periodically to make sure there are no feelings or concerns that we need to address, and we should measure and show progress on a regular basis. The Stakeholder Register is a powerful tool we can leverage. The typical things we would list would be the name, the role or position, and what their attitude about the project may be. We would also indicate what kind of impact they can potentially make on the success or failure of our project. Finally, we need to make sure we're clear about the information that our Stakeholder Register will also include. We might list contact information, the nature of how we communicate with these folks, and more about their expectations from a communications perspective for the project overall. There's a very powerful tool called the Stakeholder Matrix. We start by gauging the amount of power individuals have over your success or failure of this project. This is plotted along the left axis from low to high. And then from left to right, we determine the level of interest they have, also from low to high. Then we try to understand which stakeholder groups go in which quadrant. For example, let's say that stakeholder C showed up in the lower left-hand quadrant. This would indicate that they have a low level of power to affect us and a low level of interest in what we're doing. Then we have folks with a very high level of interest, but not a lot of power over us. This might be suppliers that we pay to supply materials. They have a lot of interest in the materials and doing business with us, but they don't have much power over us. Then we have folks with a low level of interest, but a lot of power. This might be senior level managers in another functional area. They may not be as involved as other stakeholders. Finally, we have the most important group we need to focus on from a stakeholder engagement perspective. These are the folks with a very high level of interest and a lot of power. We need to expend most of our energy in managing their attitudes, how we communicate, how we engage, and how well we collaborate with them to drive project success. It's important that we understand and know who the customer is. It's also important to recognize that we have actually two kinds of customers. We have external customers who are outside of the organization. This would be the folks that buy the product or service we provide. Then we have a group of internal customers within our organization. Think about them as process customers. And if you think about a value stream map or flowchart or a process map, we can envision all of these different customers at the handoffs. A problem that Toyota has talked about in recent years is what's called knowledge disconnect, not knowing what our customer actually needs. That means all types of customers. External customers fall under different kinds of groups. We have the final buyers of our products and services. In a business-to-consumer relationship, the customer buys services and different kinds of consumer goods from a business. We also have what's called business-to-business relationships, where businesses are selling to other businesses, like selling to government, products and services used by businesses, or training services like this course. In a supply chain, we have other kinds of external customers as well. For example, channel purchasers might be folks that integrate hardware and software, or retailers could be as big as Walmart or as small as the corner store. We have resellers like auto dealers, and then independent representatives, like folks that sell Amway products, for example, or Tupperware, or something like that. In short, anyone who pays for products or services is a customer. There are many potential effects on our external customers with Six Sigma projects. Certainly, we want to drive improved quality and service. We need to address and make sure that our customers' most pressing needs or requirements are being met or exceeded whenever possible. we need to drive better communication around everything we're doing with external customers. And then finally, we want to drive better satisfaction with our customer. We want them to think about us as providing superior speed, the best quality and functionality for our products, and the most competitive price, and perceived value for the money they spend. We want to deliver a solid customer experience that results in high levels of customer loyalty. Making a customer unhappy is very expensive. Some estimates suggest that just one upset customer is going to affect the buying decisions of 10 other customers in the future by what they say or what they do after they've had a bad experience with us. Internal customers are very important to us as well. We need to understand how we affect one another. For example, if we make a product or service available to external customers, there could be a lot of steps involved in doing that. Consider a complex manufacturing company and all of the internal customers from end to end. We start with a product development group, and they provide information to marketing and sales to do quoting. Once the customer gives us an order, we hand it off to engineering and production control, and they have to do the production release cycle. Their customers are operations and supply chain management. And then finally we have product delivery and service support teams that receive it next. These would all be examples of internal customers for each other in the entire process. Together they work to deliver our products and goods to our customers. We need to think about each process customer as an important link in the chain delivering value. And like a real physical chain, our ability to serve the customer is directly linked to and limited by the weakest link in our chain. Continuing on, let's examine the potential effects on our internal customers. Internal customers benefit from many different aspects of applying Lean Six Sigma, including more streamlined, efficient, and simpler processes. Six Sigma provides the ability to do rescaling, retraining, and retooling, allowing us to redeploy assets to new value-added uses. We can move people away from doing mundane, wasteful tasks to things that really make a difference. We might even ask the question, if we had 20% more time, what else could we do to add value or impact our customers? Certainly we can change the scope and the schedule of the work, streamline our methods, processes, and procedures to get better quality faster. We can also potentially improve the cost and the outputs, the speed, the quality, the morale, and the productivity overall. In this topic, we will examine process owners and why they're so critical to us in the practice of Six Sigma and chartering Six Sigma projects. The process owner is typically somebody who is leading the overall implementation effort, and they typically would own the end-to-end process. At the very least, they should be a key player in the value stream. Process owners must thoroughly understand this process in question because they are the ones who are going to help define success. In addition, they will help us define how we're going to measure success and how we're going to help align to the company objectives and set targets for improvement. They are also typically responsible for the overall success or failure of the process improvement effort. They ultimately stand the most to gain if we succeed, and maybe the most to lose if we fail. This pyramid of people who are involved with different kinds of projects starts with the champion at the very top. Generally, this person is a top executive in the organization. They could be the value stream owner. In smaller organizations, it could be the CEO, while in larger organizations, it could be the president of a line of business. We often find that these are the folks responsible for aligning our project to the overall business objectives. They have visibility to the market and the customers. They're going to help us to understand and break down barriers to success and help us manage risk to our project. They are employed to help us understand organizational change and management issues. They're certainly going to be important when it comes to reviewing progress on our project. And if we're going to have a steering committee or an overall guiding coalition on top of our project, they are typically going to be directly involved with that, or whatever governance structure we're going to use for our projects. Six Sigma leadership has four major components, starting with the enterprise leadership team, which is typically chaired by the sponsor or the champion. Beneath that, we have a business unit leadership team. This often includes the process owners who actually own the functions or the value stream that we're working to improve. Each project is going to have an improvement project team, and this team may follow various methodologies, including the DMAIC framework, the define, measure, analyze, improve, and control steps, or utilizing the Kaizen or Kaizen Blitz methodology to go after a rapid improvement project. And finally, we have the actual team leader, the coach, the green belts, and the black belts. They work interactively with the team and support the team going forward. They have a very important role here to support and mentor the actual improvement team. There are typically two tiers of leadership. Now let's review these in order. First, we have the enterprise leadership team. This typically correlates with the CEO of the company or the executive level. It's their job to make sure we have the established visions, strategic focus, the right kinds of resources, and that we're focusing in on the right things that make a real difference for our customers and for our internal stakeholders as well. It's their job to understand roadblocks and help us to remove those. Enterprise leadership also helps by facilitating change in the organization from a broad perspective. The other tier of leadership exists where the team operates, and this is where the actual project work gets done. This is where we're implementing the vision, specifying the operations that we're focusing on, and managing the processes, resources, and project goal focus. It's this leadership team that actually manages day-to-day roadblocks and manages change deep down in the organization at the change level. And then we have, of course, the yellow belt. The yellow belt is part of the team that supports the employees in the process. They act as subject matter experts who can bring external expertise to the team. They also help us understand the voice of the process and the voice of customer data, and they assist with brainstorming and prioritizing our projects. Yellow belts are hands-on with actually making improvements and working with employees, stakeholders, customers, and suppliers who are involved with this project from end to end. They may also be involved with the pilots and proof of concept efforts. Yellow belts also get involved when we begin creating actual deliverables for the project. They may develop standard operating procedures, standard visual work, identify and implement error-proofing measures to make the process robust, and keep that effective for the long term. An important objective for every Lean Six Sigma project is understanding the process and how critical it is before we begin to make changes. We need to understand the cause and effect of the various process steps and recognize that everything affects everything else. Business processes are typically a series of events that produce a given output, and more often than not are defined by numerous steps in that end-to-end process. Inputs are very important to us in this entire transformation. The resources are people, material, energy, equipment, information, etc. Inputs are an important part of the end-to-end transformation, getting to the outputs that we're seeking. It's important that our team clearly understands the relationship between the inputs, the process, and the outputs. If we examine the relationship closely, we can identify many X factors that come together to dictate the amount of variability, the quality, and the repeatability of our output Y factor. The variables on the outputs can be many things, including the context of the situation and the environmental influences that act upon the process differently each time the process is performed. The output is the result. We need to recognize that outputs for any given end-to-end process can in turn become inputs to a subsequent or downstream process later on. Determining process boundaries is an important aspect of defining the project and where we are going to be focusing our efforts. For example, with a manufacturing company, we could have process boundaries starting with ordering an aircraft part for an airplane. It could begin with the receipt of the order from the customer of the company. Then we would have the various operations that would occur until we eventually arrive at the inspection of the part, pass, fail. If it's good, we can ship it to the customer. If it fails, we'd rework it and pass it back through. Or we can use a different example, such as a 401k hardship withdrawal. With a retirement services company, We might want to track it from the time the customer submits the online request or calls us through the various processes until we either deny it or issue a check. These are examples of defining the process boundaries in either a service or a manufacturing example. Let's now focus on the handoffs, or what's called transition points, between each of the steps. These locations are where we transition from one functional process to another. Imagine stapling yourself to the information or to the order. Each time you stop and transition from one value-add activity to another, you would be entering another step in the process. It's these critical transition points where handoffs occur that we need to understand. The challenges associated with transition points can include delays, the opportunities for mistakes, and other problems that can affect our customer and the overall results we get from the process. Process swim lane diagrams are a powerful way to visualize and understand a complex process. They depict a chronological process flow from left to right. The process is deconstructed into the various actors and actions to understand the flow of a process. The various functions are represented. In this example, there is the originator, a computer system called SharePoint, general counsel or the attorneys, a supplier for the process, and an accounts payable function. The process begins with an activity by the originator, where they create a new form. Then there is a handoff to another step where they upload the supporting documentation into the system, and then another step where they submit it for approval. This form goes through a notification process in SharePoint, which in turn triggers a review by the general counsel. They validate the form and identify this new supplier. General counsel may notify the originator of the form approval. At the same time, there may be a loop activity because perhaps the originator must submit required material or respond to an issue. And then finally, we can submit the invoice and accounts payable validates the approval. This process swim lane diagram is an example of the flow of the process, with visualization about who does what and when. In this topic, we will discuss the SIPOC model. SIPOC is an acronym where S is for suppliers, I is for inputs, P is for processes, O is for the outputs, and C is for customers. In some cases, we would actually add another letter, R, for requirements. For our purposes, customers and requirements would all be the same activity. There's also some value in starting with the customers and working backward. What is the output that the customer is getting? And what are the customer's concerns and issues that we need to address in the future state? What did they care about? Once we understand the issues, the problems, and the headaches the customer is having, we can go backward through the process and understand and capture all of the outputs that contributed to the customer issue, to the processes, to the inputs, and to the suppliers. It's important to recognize all the different things that can come into play as we make our way through the SIPOC diagramming process. We typically capture this as a spreadsheet or on a flip chart. We can start by asking the question, who are the vendors? It could be a government institution, an engineering function, an HR function providing resources or quality control. It could also be the customer. For many service processes, the customer makes a request as an input to our process, so they're actually a supplier. Once we receive this input, we conduct a value-added activity and give them the output on the other end of the process. Inputs can be raw materials, instructions, data, drawings, specifications, the quality requirements, standard operating procedures, labor, resources, machines, and equipment used throughout the entire process. Then we have the actual process itself, which could take the form of a value stream map, a process map, a swim lane chart, or some other method. What's important is to recognize that the outputs, or the values that we're trying to accomplish, are a product of the various things that go on during the process. So we need to imagine the process as containing several X factors or functions, which give us the quality of the output that we're aiming for at the end of this process. We might think of this output as Y. Outputs can take many forms. It could be value-added task completion that's ready for the downstream step. It could be a report or a finding. It could be a product or a part or an assembly. It could be a new specification we're going to follow. It could be a certification that our customer requires. It could be a check to send to the customer. It might be an approval or permit that we're issuing. And then finally, we have the customers. The customer is the one that actually decides how good is defined and whether the requirements have been met. So they're going to define what the key features and functions are that they care about. We use that information to seek out root cause analysis and work upstream to make sure our process is delivering optimal results. Let me share a little real-life example. One of the projects I worked on was the Parole and Commutation Board for the State of Michigan's Department of Corrections, and it was quite a job to evaluate that process. The suppliers included prisons, legal units, medical records, and the prisoners themselves, and many others. The inputs were many. We needed reports, findings, past files, and the current legislation we had to follow for hearing a parole case. The process contained over 130 steps, and we analyzed them in a swim lane chart. The process also included a deferral process, where we could have inmates going into a holding pattern while we were waiting for information. The outputs were many. We had findings, recommendations, an actual appointment for the parole board member to interview the inmate, and of course their decision was an output. And the customers were varied. It included the community that parolees would go back to, the prisoners themselves, their families, the victims families, and a variety of other customers for this process as well. Being able to visualize the whole process and all of the players from end to end is very important because the risk associated with altering that process was great. This is not something you could take easily or lightly because lives literally hang in the balance of getting it right the first time. This course covers tools that are available to use when planning a Six Sigma project. These include the work breakdown structure, Gantt chart, diagrams, and charts. This course also introduces Tollgate reviews and their purpose in projects. Managing projects in Six Sigma starts with understanding what project management is all about. Project management is a conglomeration of knowledge, skills, tools, and techniques that are used to meet project requirements. Project management began to emerge as a profession more than 50 years ago. One example of project management was Walt Disney Company's creation of the Epcot theme park back in 1979. I actually worked on the Disney team using program evaluation review techniques on computers in 1979, but that's another story. The 5 phases of project management, according to the Project Management Institute, would be initiating, planning, executing, monitoring and controlling, and closing. In Six Sigma, projects can vary dramatically in their duration, from just hours on a simple problem-solving exercise to a year or longer in other cases. The size of the project is what dictates our commitment of time. If a single meeting would get things done, it may be very short. However, if we're taking on a major Design for Six Sigma initiative that impacts a large strategic area of the organization, the project could be years in length. Let's discuss what is contained in a project charter. There are many key elements that we need to understand. The first is a clear problem statement. Determining what we're trying to solve and defining the problem well is often more essential than the solution itself. We also need to understand the scope and the boundaries of the project. There must be a clear goal statement or purpose statement to guide the team. Next, we need to identify the tangible and measurable deliverables we want to get out of the process. We need to recognize the required resources in terms of people, financing, equipment, software, research, and anything else we need to execute our project successfully. And then finally, what are the important roles that are needed to develop the charter and ensure a successful project? This would include sponsors, process owners, project managers, and team members. During the charter stage, it is important to define both the problem statement and the project scope. The problem statement describes what we're after, what we're solving for, and the result we want to achieve. The scope is a bit different, as it defines the beginning and ending point and may include a baseline. Problem statement describes the impact this problem has on the organization and how success will be defined. On the other hand, the scope helps us set the stakeholder expectations about what is and what is not included in the project. As we move forward, we need to answer questions like, what processes are being addressed at what level, and what's not included in the scope. Key deliverables provides a roadmap, a sequence of tasks that need to be accomplished to do our project on time and on target. This would include completion dates and important milestones that we're going to work toward. And this is generally aligned with the various phases of a project. No matter what methodology you are using, it is important that we identify key activities. When will they take place? How will we know they're successful? What's the end goal or the benchmark that we're working to complete for each of the major phases in our project? Resources, roles, and responsibilities start out with the question, who? Who are the people that we need to be involved and for how long? What are the team's roles and responsibilities? We'll sometimes use what's called a RACI chart. RACI is an acronym that stands for Responsible, Accountable, Consulted, and Involved for any given step in the process. Reporting relationships are very important. For the purposes of the project, there may be some temporary lines of reporting to a team member or to a project manager. We need to determine who's going to do the work, who's going to be assigned to which tasks, and for how long, and when. Most importantly, who are they accountable to, and who will they report to? We must provide the right amount of direction, support, coaching, and training to facilitate the tasks that must be accomplished in order for the project to be successful. Project charters have an important goal statement that gets things started. We use the goal statement to describe the anticipated results that we want to achieve for our project. How will success be defined, and how might we measure that? We want to outline our quality focus and perhaps some metrics for things like safety, quality, delivery, cost, morale, and productivity. We want to answer some critical questions such as what results we anticipate from completing this project. How would we measure these results and know that we actually accomplish what we want to as an organization? One of the important things that we should consider when setting goals is to think about setting SMART goals. The SMART acronym is often used as a principle in personal goal setting, but it's also an excellent guide we can use when defining project goals. So let's discuss some of the elements of a SMART goal. First, it must be specific. After that, it needs to be measurable. We'll have to have data now as a baseline and then make it part of our project to measure our results at the end of the process. Our goal must be agreed upon or attainable, and something that our sponsorship and our leadership has agreed that we need to pursue. It needs to be realistic. And then finally, it must be time-framed or time-bound so that we have a very clear target or end date for our project. Let's explore a simple goal statement, such as improving the average cycle time to 3 days by December 31st. Or in manufacturing, we want to reduce the order cycle time from 14 weeks to 6 weeks before the end of the year. Or reducing scrap due to our equipment and tooling by 25% in the next 6 months. Or in the services sector, reducing the hiring time from 6 months to 90 days or less within the next year. Or in a contact center, increasing the number of calls handled per hour of work to 3 or 4 or better in the next 90 days. These seem to fit the criteria for SMART goals. So what is baseline data? This helps us understand the kickoff point, or the starting point for our project. We use a goal statement to understand the problem and do analysis, and we certainly can rely on that to give us a benchmark of where we started and comparing that to where we ended up. For example, if we're going to analyze a customer contact center for technical support, we might start out with a little assessment, such as, what are the top 3 call types that make up 80% of the call volumes? For each of those call types, we may conduct a time and motion study to break it down. Such a study can break down, map, and record data for each of the steps in a technical support call. What percentage of the steps go right the first time? and what percentage fail. And finally, how much time and effort is associated with handling any rework so that we can quantify the overall work in our process. In this topic, we will discuss problem statements. Problem statements describe the problem to be solved and the impact of that problem on the business. This helps us set up meaningful goals, focus our efforts, and answer critical questions such as, how big is this problem? How is it measured? And what does it impact? Formulating the problem is often more essential than the solution. It's not always easy to do that. Let's say we have a problem statement around improving customer satisfaction. Well, that's pretty broad. It might be better if we said, we need to improve customer satisfaction and specifically how we handle support calls. So now we're being more specific, but maybe it's still too broad. It might be even better to say, how do we improve our customer satisfaction with support calls for product line XYZ specifically? That is a much better problem statement because it is more specific and clear about what we're trying to improve. There are many issues associated with problem statements, and there are some key things we should not do. First, we shouldn't state an opinion about what's wrong. We want to avoid starting out with the answer in mind. The goal is to discover the best answer. We should leave this creative and open. We don't want to describe the cause of the problem. That's our team's job to carefully determine by using the tools from Lean Six Sigma. Another issue we want to avoid is that we don't want to describe the problem too broadly. Doing so could create a large or vague scope that is poorly defined. We should never assign blame or responsibility for that problem up front. This can create fear and cause people to retreat or become defensive, and then they certainly wouldn't support our project. Finally, we should not appear to be prescribing a solution right up front. If we do, we could shortcut the discovery phase and miss opportunities to find the root cause. This would shut down creative thinking and tempt the team to skip through doing a thorough analysis for the project. Let's take a moment and review a problem statement. Our current cycle time for order delivery is 5.5 days. This falls short of the customer requirement of 5 days. So right away, we know where we are and we know what the target is. We can immediately identify the gap that we want to address right away. Then we read the rest of the problem statement, which says the shortfall has resulted in the loss of customers and $100,000 in lost revenue every month. This part of the statement is important because it suggests how customers react to our poor service. They are leaving. It also quantifies the losses to the business. This gives us a solid financial baseline and one more thing that we can measure and monitor as we implement improvements in our project. Finally, we should take some time to refine the problem statement. For example, let's review our original before statement. Our average on-time delivery rate is falling short of customer expectations. Let's be more specific. We currently have an on-time delivery average of 65% for product A and 75% for product B. This statement provides more data and specifics about the problem. This problem also states what the customer's expectation is, which is 100% on-time deliveries. With this level of detail, we can begin a root cause analysis. For example, why is B doing better than A? What is the difference between the two? Is one using better processes? We can follow this train of questioning to identify the true root cause and make sure that we're addressing the right problems. The project scope is essentially the boundaries for the work that will be performed to fulfill the objectives for our project. There are various purposes for defining the project scope. We must define exactly what's required and, just as important, what's not. When discussing requirements, what are the boundaries, end to end, within this process that we want to focus on? We need to understand areas and levels in the organization where this project could extend or expand into. Give some critical thought to just how deep we will go to get to the results that we're seeking. We can also think about bounding the project or putting some boundaries around it, left to right and top to bottom, to clarify the focus of the scope and what's included. Let's explore a project scope statement and break it down a little bit. This project will focus on help desk operations at the company's Toronto facility. Okay, so we have a specific location. The project team will review inbound customer support processes at all levels over the month of July. So we are dealing with the inbound customer support process, which is pretty specific. We're also clear about the time period in which we're going to do this. It's July. We are going to determine ways to reduce customer wait time. This is very important because we know the scope of exactly what we're trying to improve. The final sentence states that hardware and software, infrastructure, and staffing will not be examined. So, we've also made it very clear what's out of scope for this particular project. Now we're going to explore the concept of scope creep. Scope creep has many dimensions, but generally we'll start with defining some boundaries around our project, from the beginning to the endpoint, and how specific we're going to get. What can happen over time is that other work can begin to show up in our project that we did not intend to do earlier in the effort. When we take on more work than was originally agreed to, it can also take a lot more time and more money, and it can create some problems with the project sponsor and stakeholders. After all, scope creep means we are doing things that they never intended for us to do. There are many reasons for scope creep. Sometimes the team can get a little excited and maybe bite off more than they can chew within the time and money committed. We might rationalize it, saying, it's just a little extra thing we're going to do. It's not going to matter much. Or maybe the project champion is expecting too much, and there's a misunderstanding about the defined scope. For example, after the project begins, the project champion might say, "This is really cool. While you're at it, let's also do this and that." There can be good intentions, but this can get us into a lot of trouble with scope. As good project managers, we must carefully define scope and then use our tools and techniques to carefully control it. Let's explore some of the issues associated with too narrow or too broad of a scope. First, we don't want to be too narrow because we won't get the results that we're seeking. We may only address part of the real problem, or we may not address the biggest issues for this particular project. We may even miss the root cause that we're trying to identify. On the other hand, if our scope is too broad, we may again be missing the true root cause. We could get lost in the data and end up taking a lot longer than we should, which delays completion of the project. Or we can get overwhelmed or frustrated. Failing to scope our project well could make it a lot harder to overcome barriers to change and roadblocks that often pop up for us in typical projects. A well-scoped project has these attributes. First, it's defined around the benefits to the customer and the organization. It addresses the true source of the problem. It has achievable objectives. It's budgeted properly. And we have a continuous flow of input from all the stakeholders. One very important aspect of the project charter is the project communication plan. This document describes how communication will be planned, structured, monitored, and controlled. We need to think about why Lean Six Sigma projects fail. A failure to communicate is a top reason, and many organizations do not acknowledge the need for communications planning or make the necessary investment of time. Unless we have a well-defined communication plan, we are not likely to communicate effectively, and our project will not be set up for success. An effective communications plan must address all of our stakeholders, and it must include communications on a continuous basis. Communication in projects is much like advertising, where we need to repeat the message multiple times before it will stick in the minds of our audience. Let's think about some of the benefits of a good project communication plan. First, it clearly captures the required project information. It secures resources for our project, and it's clear about where they're coming from and when they're going to be needed. It's very effective at keeping our stakeholders up to date. This plan should be a living, breathing document that's assessed continually. Is it effective? Do we need to adjust it? Is it time to change it? It's not a bad idea to use plan, do, check, act thinking in your communications plan, with the intention of continually replanning. Finally, it needs to be very clear about communications responsibilities as well. There are some important components of a good project communication plan. It should include things like, what are the communication constraints we're dealing with? This could be things like the location of people, the shifts that they work, and their access to technology. What are the requirements for stakeholders? We should try to answer that "what's in it for me" question for each group of stakeholders as thoroughly as possible. What about those individuals responsible for the communicating? Are they capable of delivering clear and unambiguous communication? How about those who receive the information? How will they get it, and how can we confirm that they got it? How can we validate that the message sent was the message received? And finally, we need to allocate sufficient resources for communication so that we know that we have what we need to accomplish this. We also need to remember that our communications plan needs to meet the needs of your specific project and your specific stakeholders, and it needs to comply with the practices and policies of your organization. In this topic, we will examine what effective team communications are, both for the team itself and for the stakeholders. We need to get it right the first time. Timing is everything in projects. If it's too soon, people can forget what we just shared. If it's too far into the future, it may appear we didn't follow through, which could lead to frustration or confusion. Or if we communicate too far in advance, we may have to communicate it all over again. The next thing we must pay attention to is the information and the meaning. It's always a good idea to build in validation feedback. This can help us confirm that the message we sent is the message received as intended. We have to be aware of a lack of clarity, because a lack of clarity can be disaster. It can lead to a lot of frustration on the part of our audience. And ineffective communication can mean a very ineffective project, because we may have people doing the wrong things at the wrong time for the wrong reasons. Let's talk more about effective organizational communication. It starts with meeting the needs of our stakeholders. We need to identify the internal and external customers that we need to communicate with. For internal customers, the message could often be very different from the message we might send to our external customers. We might share a lot about our issues and things we wouldn't want our customers to know. For external customers, our communications may be more informational and serve to support collaboration and promote cooperation. It's important to remember that we can't make customers listen to anything, so we have to be careful about how we craft our messages. Stakeholders require timely communication, just the right amount of information at the right time, and finally, we need to create opportunities for feedback. Failing to obtain feedback could lead to our message not being received the way we intended, and we never know it happened without the feedback. There are different communication methods that we can use. Written communication is a one-way communication, often in the form of an email, newsletters, or memos. This is best suited for messages that are not particularly time-sensitive, and when information is factual and short. It could include announcements of events or status reports. When we use email, it indicates to the recipient that the message is information-based, routine, and uncomplicated. The use of voice, telephone calls, and web conferencing is important too. This is a form of two-way communication. Two-way communication is appropriate when we have an urgent or complex issue that we need to address. It also can be helpful for clarifying issues or dealing with issues that don't require a lot of documentation. Using the telephone indicates to the receiver that we really care about this message and that we care about them. Finally, meetings and face-to-face interactions are a third method of communication. This method is ideal for sharing sensitive information or tacit knowledge that's best shared through observation. Maybe we want to be highly collaborative, or it's a very complicated matter with a high risk of misunderstandings. It could even be a volatile situation with a lot of fear and anger. We want to be careful about how we convey emotion and handle delicate situations. It is easier to gauge reactions when communicating face-to-face. Meeting in person indicates that the message is very important. It requires commitment and is potentially very significant to them and the larger organization. The volume of information is something we need to consider carefully when we choose a method of communication. What is the volume of information compared to the attention span of the audience? Shorter is often better. There is value in being more concise but still getting the message across. We don't want the message to be overly complex. We need to think about the nature of the message and make sure it's appropriate. The degree of collaboration helps us to select the method as well. If we don't need to collaborate, it's just a one-way communication, written is fine. But if we need that two-way, in-person validation, and we need to do it quickly and confirm understanding, nothing beats a good face-to-face meeting. There are many different purposes for the planning and monitoring tools we use for Lean Six Sigma projects. We use those early in our project planning to identify all of the activities and creating what's called a work breakdown structure, where we detail out the tasks, the subtasks, the resources, timing, and many other elements for a successful project. Then we create our schedule, including the timeline, start and finish dates for various activities, the relationships of activities to one another, and dependencies from activity to activity as well. We use tools during our project to monitor progress. This is critical in the execution of Lean Six Sigma projects. They allow us to detect where performance and outputs could vary from our expectations. We can use the plan, do, check, act cycle to iterate on our improvements and correct our project plans on a continuous basis. A Gantt chart is a very common tool used throughout the project for various purposes. We use this for tracking progress and to control our performance. A Gantt chart is constructed in rows, each with a task. This can include major tasks and subtasks. For instance, we may have major task A and subtask 1 and 2. Each task has a duration. In this case, it is measured in days. The tasks can be visualized along a chronological timeline, where we can recognize how they relate to one another. Using this timeline, we can also say, as of this point in time, this is where we stand on the project. PERT stands for Program Evaluation Review Technique. A PERT chart incorporates some important data. For each step in the process, we're able to create relationships with the preceding and succeeding steps. For example, a relationship could be finish to start, or finish to finish. We can create lags and other kinds of relationships between different activities. We can diagram these out and begin to calculate what's called the critical path. This allows us to do additional project risk analysis, identify slack time, and things like that. CPM stands for Critical Path Method, and with computer tools, or good old pencil and paper, we can go through and calculate which path, the red arrows in this case, dictates the longest amount of time to get through the entire end-to-end process. Reporting and planning tools have many different uses in the practice of Lean Six Sigma. For example, charts may display the status of a project in graphical format. This can include Gantt charts, PERT charts, CPM charts, or calendar charts, and many other views are available to us. Our chart can also provide data to us regarding variance or percentage complete. We can even assign a red, yellow, or green status on project items, or a risk priority number, so tasks in the project can receive added attention. An advantage of using electronic reporting and planning tools is that they can be easily emailed, uploaded to a shared system, or shared with others. They also can make reporting very simple. There are many cloud-based tools, such as Microsoft Project. Even a simple Excel spreadsheet can be very effective. The types of tools you use on your project may depend on your available resources and the complexity of your project. The Work Breakdown Structure, or WBS, is an excellent tool that allows us to divide or decompose project work into smaller pieces. The goal is to break the work plan down to its smallest level, the work package. The idea of estimating the effort, cost, and the schedule for a project could be daunting. Using a WBS allows us to identify tasks which can be easily estimated, making the overall project a lot more manageable. Let's take a moment to identify the pieces of a WBS. The top level is the overall project that we're chartering. Underneath that, we have major deliverables that are necessary for project success. Major deliverables could be major phases in our project or external sub-projects as well. Each of the major deliverables in turn has tasks associated with them. As we break these down even further, we can identify subtasks. At the very bottom of the WBS, we have the lowest level, called the work package. The work package is the very specific work that must be done to accomplish the objective. There are many benefits to using a work breakdown structure or WBS. It facilitates control of your project by dividing the work into manageable units. A WBS can be used to define responsibilities on a per work package level. It also facilitates scheduling. When we consider relationships and dependencies between the tasks, we can do backward scheduling, working from a given due date out into the future and backward to when we need to start the project. Or, working chronologically, if we started today, we can determine the soonest date we can complete the project. Another benefit of the work breakdown structure is that it helps us to determine the true budget for the project once we have fully broken down what needs to be done. Let's think about a work breakdown structure and just walk through one together. Let's pretend we're going to do a time and motion study. Well, first of all, we're going to have the various tasks, so let's create one here. First, we'll set up the information, so it lists the task number, a description of the activity, and with the description, we'll list who's responsible. We ought to have the hours. How much effort is this going to take so that we can budget it? And then finally, the date we want to finish this. Let's say the week it should be finished. We're going to capture this data as we go through the process. So our first task, with the major task number 1, is to actually pick the process we'll do a time and motion study on, and also who the subject matter experts or SMEs are. Next is identifying who's responsible for that, and it's going to be Al. Now, we're not going to put a due date on that because we actually have a subtask A and a subtask B. For subtask A, we need to actually pick the process, so let's list that as identify the process we're going to use. And Sam will tackle that for us. Sam's going to need at least 1 hour of human effort to get that done, and we want that done in week 1, in the very first week. Then we move on to subtask B, where we're actually selecting the SMEs that are going to be involved with the time and motion study. Al is going to handle that. Al's going to need a couple of hours to get that done, and it's also going to get done in the first week. So then what we would continue to do here is to break it down further for task number 2. We would have subtask A and B observing 80 different calls, and then subtask B finalizing it. We would have Sam and Al 40 hours and 20 hours respectively completed in week 2 and then completed in week 3. These are all elements of a work breakdown structure to conduct a time and motion study. In this topic, we will explore the Gantt chart in depth. This is typically a time-scaled activity list, usually displayed chronologically from left to right. The scale can be measured using any unit, from hours to days to weeks to years. Gantt charts are fairly easy to maintain using various kinds of project management software, or a simple spreadsheet. There are also cloud-based tools and very large-scale enterprise-level systems that can be used to build Gantt charts. No matter which type of software you use, the Gantt chart provides a clear picture of what's to be done and the current status. It can report varying levels of detail with information such as resources, percentage complete, and more. We can even use a Gantt chart for what-if scenarios, allowing us to assess the impact of a task being done sooner or later than it's planned in a project, or assessing the change of scope for the project, or evaluating resource constraints and how they can impact our overall project. Let's cover some of the elements of the Gantt chart. First, we have the task ID number and a task name. For instance, we have a major task A with subtask 1 and subtask 2. Then we have major task B with subtask 1, 2, and 3. All of these subtasks go together. For each of these tasks, we have a duration and an expected start and end date. In this case, we are using days as our unit of time. Each task will take a certain number of days against the project timeline. The Gantt chart illustrates this visually. The next thing we can determine is when there is a relationship between the tasks, which is shown by an arrow between them. Some tasks must finish before others can start. For instance, task A-2 must finish before task B-1 can begin. Then we have the status line, showed as a dotted red line. This is today's date, and this is where we are in the process. We can use the status line to determine what has been completed, or if we have a problem. For instance, we have a bit of a problem with task B-2, where we are slightly behind our timeline. And because task B-2 must finish before task B-3 can start, this can have repercussions for our overall project timeline. We can also add extra columns to a Gantt chart, such as the assigned resources, or additional information about an individual task that might provide helpful at-a-glance information. It is important to understand how we interpret a Gantt chart. There are 4 critical areas that we should review when we're evaluating Gantt charts. First, we can evaluate resources. For instance, if we select task F, we can determine that Alan and Inez are the 2 critical resources for this task. This Gantt chart even breaks down how many minutes they will need to spend on each task. We can aggregate these durations to determine how many total minutes each person is going to spend over the course of the project. The Gantt chart can show the engagement time for Alan and Inez across the project, as well as which of their tasks are independent and which are overlapping. We can plan ahead by determining what will be happening on the calendar over the next 10 days. The other thing we can include is important milestones, which are represented by a diamond shape. Diamonds usually reflect a critical milestone in the project. Milestones can be triggers for new activities, or a Tollgate review, which requires approval before we can continue with tasks for the project. Finally, the Gantt chart can show slack time. For instance, in task D, we have a little bit of slack time, meaning that although the task is scheduled to finish on day 11, it can actually finish as late as day 12 without impacting the project. So a Gantt chart can contain a wealth of information at a glance that is helpful for controlling the schedule. An activity network diagram, or AND, is a visual tool which depicts the relationships between activities. We have an initial, as in this case activity A, that kicks off the process. Often processes can diverge into different concurrent processes. In this case, after activity A, the process diverges into activity B and activity C. These concurrent paths follow their own processes, and then they merge again into activity I. A network diagram is useful for a quick charting of concurrent, parallel activities such as this that end with the final product or service that we're going to deliver. Let's follow another example of an activity network diagram. We will review a software development process of creating a new game. At the beginning of the process, we have the first activity, strategic planning. Once this activity is completed, it kicks off 3 different concurrent strings of work, which could be 3 different teams or team members tackling different things. We have the project design period and the project development cycle. This path feeds into sales and dispatches and onto the finished product. Material procurement is on its own path, and then it merges into product development for the remainder of the process. Software development feeds to marketing and distribution. It rejoins the other paths in the process for the sales and dispatching activity and ultimately to the finish of the project. And AND, or Activity Network Diagram, has several purposes. It can help us discover ways to complete our projects sooner. If time is of the essence, and the AND can facilitate our evaluation of the critical chain, and perhaps re-engineer what's going on with the process. We can also use an AND to describe the flow of activities. we can identify a logical flow of activities through the process. The activities should be physical and/or a flow of information across the value stream in an electronic form. We can also use the network diagram to communicate the plan and also risks to our stakeholders. To make the AND easier to visualize at a glance, we may need to add some kind of annotation, starburst, color coding, or footnotes. We use this technique both in the define and improve stages of process improvement. In the define stage, we want to understand the as-is state and how is the process currently unfolding. Then, in the improve stage, we try to identify opportunities for re-engineering or doing some activities differently. All of this can be illustrated in our activity network diagram. Now we will introduce the concept of critical path. The critical path in an activity network diagram is a series of steps that dictate the longest cycle time for the project. In this example, if we do an analysis and add up the activity durations, we can calculate that tasks B, D, and F take a total of 10 days. Tasks C through H take a total of 8 days. So with a very quick analysis, we can say that based on this data, the critical path of activities that defines the longest duration for our project is A, B, D, F, and I. There are many benefits to using activity network diagrams. They are very powerful visual tools that communicate a lot of information at a glance. We use these to show the sequence of tasks, concurrent or parallel tasks, dependencies between tasks, and the duration of tasks. And finally, activity network diagrams provide a quick and easy way to identify the critical path of activities that make up the longest possible time that our project may take to complete. In this topic, we will discuss affinity diagrams and how they are used in projects. An affinity diagram is a very powerful method to take many ideas and organize them underneath a problem statement. Quite often, teams will use tactile tools and techniques. So in affinity diagrams, we may decide to use paper cards. Flip charts and spreadsheets work as well. For this discussion, we will use the card method. Affinity diagramming is very effective when used immediately following any idea generation exercise, such as brainstorming, nominal group technique, or a focus group. We can also use survey responses or interview answers if these are something we would like to organize. The affinity diagram allows us to organize all this feedback and ideas into a useful output that we can use to drive our project forward. It will help us to determine what goes first, second, third, and so on, out of all of the ideas that we might generate. Let's review a sample affinity diagram. Imagine we're a bank, and we're going to be evaluating our loan processing time for our various bank branches. As a Six Sigma team, we want to consider the variability of loan processing at the various branches, and what may cause different or inconsistent customer experiences. We can use an affinity diagram to organize a list of potential factors into the categories that would have the most impact on loan processing time. So let's examine the different categories. Under loan-specific factors, we have the nature and the category of the loan, completeness of the application, whether the loan was initiated online or in person, and the amount of the loan. In other categories, we have issues associated with staffing, the loan applicants, organizational factors, and external factors. This is by no means a complete list of all the potential categories, but based on a loan processing scenario, these would represent some of the key categories. When do we use an affinity diagram? It's very important to recognize we'll use it again and again throughout the entire DMAIC process. DMAIC includes define, measure, analyze, improve, and control. In complex Lean Six Sigma projects, we can generate waves of brainstorming many times across the lifetime of a project. So we could be using affinity diagramming again and again to organize large volumes of data. An affinity diagram helps us to better understand complicated problems and make them easier for everyone to work with. It is also helpful when we have a lot of group inputs to consider, and agreement on the choices is needed. Using a visual affinity diagram is an excellent way to build collaboration, consensus, and commitment in accomplishing our process improvement goals. We can use this to stimulate creativity and take an approach to a familiar problem in a new way. And by including outsiders who aren't normally involved with this process, we can benefit from a fresh perspective, apply some critical thinking, and perhaps challenge our status quo. Now we will assess a problem statement and then walk through the affinity diagramming process. Our problem statement is, we need to improve the product design process. This statement is not particularly leading or confining, nor is it presuming we know the answers. Nor is it a close-ended question with just a yes or no answer. A problem statement should be action-oriented and elicit some kind of response from our audience. From there, we want to capture the outputs. A brainstorming session is an ideal way to do this. We aren't organizing the ideas in any way. We are simply collecting and listing them visually on a board. From here, we will group the outputs. We can sort them under logical areas that make sense to our team. For example, we may have a category for customer-related issues, or things that relate specifically to our customer. We may also have categories for things related to performance, or internal processes that we can examine and work to improve over time. And finally, we may have management-related things as well. Effective affinity diagrams have many elements, and there are some helpful tips to successfully facilitate a session. First, we want to make sure the board is very visible and that participants can read it from a distance. Large sticky notes, cards, or flip charts may be helpful. Allow plenty of time and don't wrap up the session until everyone on the team says, "Pass. I can't think of one more thing we need to do." It can be difficult to predict how much time it's going to take, so allow adequate time for a session. Encourage the use of intuition and gut reactions. We might also use superheaders to combine groups or categories of ideas when it's appropriate. This can be particularly helpful if we're dealing with a large volume of ideas or a very large scope project. There are some things we'd like to avoid doing when working with affinity diagrams. We don't want to try to predetermine the categories. Instead, we should allow the session to drive that. We will avoid deliberation or criticism during the session. We certainly don't want to shut down team members and stop the creativity. Also, there shouldn't be any side discussions or conversation while we are sorting out our ideas. Nor do we want to get ahead of ourselves and begin to prioritize things until the group has evaluated all of the ideas. It is also important to avoid over-consolidation of our ideas. By following these do's and don'ts, you will have much more success in creating an effective affinity diagram. In this topic, we will introduce matrix diagrams and how they can be used in projects. There is really no limit to how many different ways we can structure matrix diagrams that can help us to understand relationships between various attributes, variables, or activities. For example, the left axis of a matrix diagram could represent various issues, opportunities, features, or whatever variable we choose. And across the top axis, we can have a population of processes, orders, equipment, customers, and other things. And what we are trying to understand is the intersections between these variables. What is the relationship? And what does that mean to us in the practice of Lean Six Sigma as we're working on improvement projects? Let's explore a simple matrix diagram. In this case, let's pretend we're the management team for a transport company. And we'd like to determine why deliveries are being delayed, and what are the issues associated with late deliveries. So we would start by making a list of all the things that could go wrong. We could have the incorrect address, poor training, bad weather, unavailability of delivery trucks, delays at the border, and more. Then we examine various shipments and we determine which of these issues may have come into play. So we have a check mark where a shipment experienced a particular error or problem. The matrix provides us an at-a-glance understanding of which factors have the biggest issue or impact on the stated problem. Once we have enough data, we can begin to identify which issues are causing most of the late deliveries. There are various symbols we use when we produce matrix diagrams. Whenever we use symbology, we want to make sure that a legend is included with the documents so that the readers would have a clear understanding about what we're trying to convey. There are some commonly used icons that are used in a matrix diagrams in the practice of Lean Six Sigma. That can represent the strength of the relationship between two or more things, or whether there is a positive correlation, a neutral correlation, or a negative correlation. You can also use coding to indicate roles and responsibilities. And we can even use a rating scale to indicate the least to the most important items in our matrix. There are many kinds of matrix diagrams, and there is really no limit to all the different things we can do with them. For example, let's start with a T-shaped diagram. This type of matrix allows us to understand the correlation of three different things. Perhaps we are evaluating production plants, along with a list of the various products being produced. And the third variable could be the customers who actually buy the products. With a Y-shaped diagram, it's a little different. We can analyze customer requirements against our internal matrix and departments. For example, one list of items along an axis could be customer requirements. Another could be the various departments and functions in our organization. And a third could be the specific business measure that we want to manage and understand. Using the Y-shaped matrix, we can show the correlations between them. Finally, we have a C-shaped matrix, also called a cube diagram. This type is a little harder to draw, but it can be very helpful to compare three groups simultaneously. We can take the same variables we use for our T-shaped diagram, production plants, the various products being produced, and the customers who actually buy the products. We can then align the variables in a different way to produce another visual illustration of the data. When do we use matrix diagrams? Frankly, there's an unlimited combination of methods that we can use. We can use them when assigning project tasks and the breakdown of work. They allow us to determine and understand the causes and the effects of problems in our processes. We can combine two tree diagrams into a single matrix as another way of analyzing the data. Matrix diagrams are used very heavily during the define and improve stages in the DMAIC methodology. Understanding the correlations between variables can reveal opportunities for improvement. In this topic, we will discuss relations charts and how they can be used in projects. Relations charts are used to show causal relationships between different kinds of factors, ideas, and other information. So let's say we have an idea, and then we want to capture other ideas and then document them on a whiteboard. From there, we discuss those ideas and we try to identify causal relationships or connections between the ideas. For example, how does this idea relate to that idea? And this idea to this one, etc. As we analyze the ideas, we may begin to identify some relationships. For example, one idea may actually be an input to other ideas that in turn are inputs to others in the diagram. So we can learn quite a bit with a little bit of effort. When do we use relations charts? The best way to use them is in the exploration of root causes to problems. We want to discover the influencing factors that impact us in our project. We can use relations charts to evaluate relationships between the various ideas that we're considering. This can be very useful when there are multiple cause and effect relationships. The creation of a relations chart requires nonlinear thinking, which is often necessary when dealing with particularly complex issues. We'll use this technique in the define and analyze stages of our Lean Six Sigma project. Let's review an example where we are analyzing software development delays. We may have started with the idea that there are insufficient project management practices. This connected to irregular client communication and to the large amount of rework. There was also poor specification understanding. But then as we continued, we noticed a relationship between irregular client communication and poor specifications. The poor specification understanding affects the large amount of rework that we're experiencing, and so do the insufficient project management practices. So we have some ideas that are inputs to others. Relations charts are very powerful in recognizing these relationships. In this topic, we will explore the tree diagram, which could also be called a hierarchy diagram. Tree diagrams can be displayed in a left-to-right fashion, or they can start at the top and branch downward through the process, much like an organization chart. The work breakdown structure, an excellent project management tool, is an example of a tree diagram. It starts with the major project task at the top and branches downward into tasks, subtasks, and down to the smallest increments or work packages that need to be done to accomplish our project. There are other types of tree structures as well. One of them is called convergent chain or convergent structure. This structure is much like a tree structure that branches out from the top to bottom, but in this case it's flipped upside down. The structure branches out from bottom to top. You could think of a convergent structure much like a variety of raw materials. Perhaps they are assembled into components, which are then combined into the major assemblies, finally ending in the finished product. A circular chart can also be used to display a convergence or hierarchy. Rather than top to bottom, a circular chart can use concentric circles, or distance from the center, to depict multiple areas or levels. Let's review a sample tree diagram using the question, how can we reduce breakages in transit of our product? We were able to identify two factors that could be contributing to the breakage: improving our packaging and improving the delivery process itself. Each of these could be broken down further. Improving the packaging could consist of updating our packaging machinery or changing the packaging materials. Improving the delivery process could include changing the transport mode or hiring more skilled drivers. All of these are valid ideas, and if we decide to pursue them, we actually have the beginnings of a work breakdown structure that represents the project work. There are many benefits to tree diagrams and their application. First, they are easy to read and interpret, and very visual and intuitive. They also show links or relationships between the parts of the diagram. They also help us to trace the parts to the key process outputs. This can serve as a checklist or the basis for a tally sheet or a data collection method. Tree diagrams help us to promote step-by-step thinking through the organization. They help us to highlight complexity in a process. They assist us greatly during the define stage in the DMAIC methodology, as well as in the improve and control phases of DMAIC. There are some important steps and considerations when creating a tree diagram. First, we need to define the process and break down the details. From there, we can define the criteria for determining when the lowest level has been reached. We don't want any more than 4 items at any given level. Keep things simple. Don't let the groups or levels merge. Then review that completed diagram to make sure everything adds up. Each level should equal 100% of the work of the level above it, and on as you aggregate back up to the highest level. Finally, we identify ways that we can improve the diagram and the overall outputs of our process. By following these best practices, you will be able to create a tree diagram that is simple to read, yet contains all of the necessary detail about your process and its parts. In this topic, we will discuss Tollgate reviews. A Tollgate review is basically a checkpoint process that determines if the goals and objectives at each stage of the DMAIC project have been met, before moving on to the next stage. DMAIC stands for Define, Measure, Analyze, Improve, and Control. So for example, before we move from the define phase into the next phase, we would want to do a Tollgate review. We would do this as we move from phase to phase across the entire process. The Tollgate review works as a sign-off for the next stage, and it can be carried out at each step as we go. There are many benefits to using this Tollgate process, including making sure our sponsors and process owner are well informed and engaged with what we're trying to accomplish. It can validate that we're on track. We can verify that our scope and charter is still valid. It also gives us some discipline to document our outputs and that we are adding to our knowledge base and lessons learned for our project. In the agenda for a typical Tollgate review, there are many different components. We state which phase we are in, provide the facts, and list the actions we've taken thus far. We provide a status on our conclusions and recommendations. We indicate the next steps we'd like the steering committee to approve. From there, the project team will present a report to the sponsors and the black belts. There may be questions and discussion during the session, including any issues, whether we are controlling our scope, and perhaps whether we are producing the deliverables as expected. We may receive feedback or an evaluation at that time, and then finally we need the sign-off. This will give us the green light to move forward, along with some coaching and mentoring about what we need to consider or adjust in the next stage of our process. Many different people will attend a typical Tollgate review, including project champions, sponsors, black belts, green belts, and other members of the team. The sign-off piece is very important as well, where the master black belt and possibly members of the project council and/or the champion can review our work and provide us direct feedback. The Tollgate review is an opportunity for the team to receive guidance about where we can make improvements in our Lean Six Sigma project. There are many elements to Tollgate reviews. We must be very clear about our project milestones and whether we are meeting them. Have we met our goals and objectives for the phase that we're working on? Do we have good data, metrics, and performance information that we can review? Many tools will be referenced during a Tollgate review. Check sheets, charts, diagrams, matrices, and more could be referenced. We will evaluate the outputs of using these tools as well as evaluate whether the tools themselves are meeting our needs and helping us properly control our project. Is our communication plan effective? Are we getting the correct level of quality in the deliverables for our project? Are we getting a clear go, no-go decision on next steps for our team? Are we getting the correct coaching, guidance, and recommendations for success that we need from our executive team and the sponsors for our project? All of these elements are vital parts of an effective Tollgate review. This course will introduce you to basic statistics and how they are used during the measure stage of a Six Sigma project. We're going to look at two types of statistics, descriptive and inferential, focusing specifically on measures of central tendency and dispersion, such as the mean, standard deviation, and variance. The idea of population and sample data revolves around the population. And the population is essentially a collection of units we're going to study. This can be people, places, objects, time periods, products, services, procedures, all kinds of different things. Much of statistics is concerned with understanding the numerical properties or parameters of this entire population, often using a random sampling from that population. Defining a population means we're going to have a well-defined collection of objects or individuals known to have similar characteristics. All of those individuals or objects in that population usually have a common or binding characteristic or trait that we're interested in. The samples are a collection of units from within the population, and sampling is very often a process of taking a subset of those subjects that's represented over the entire population. It needs to be of sufficient size so that we can actually warrant a statistical analysis. So let's move on now and take a look at the next aspect of understanding this notion of population parameters. There are several keys here that we need to focus on in understanding population parameters and key data elements. For example, the mean, which is represented as the m(u) sign for population parameter, with x bar as a measurement or a symbol that would represent that. Of course, standard deviation is to the left or to the right of our central mode in our histogram, represented by this symbol, and then the sample statistic we would have is called the standard deviation, or the little s here. And then variance, of course, would be sigma squared, or the standard deviation squared here. And the square of the sample deviation gets us at the variance there. So it's important to understand here that the relation of samplings to statistics to this population parameter is that they are somewhat similar. The statistic describes what percentage of the population fits in the category, and the parameter describes the entire population. For example, 50% of dog owners might take their dog to the vet 2 times per year. That would be the kind of statistic we want to get about the population of dog owners. Moving on, let's take a look at a couple of sample charts and try to understand what descriptive statistics is all about. Descriptive statistics are numbers that are used to summarize and describe data. And data refers to the information that has been collected from experiments, surveys, historical records, or whatever. Any other number we choose to compute also counts as a descriptive statistic, and that's specifically for the data that's being computed. Several descriptive statistics are often used at one time to get a full picture of the data. We need to remember that descriptive statistics are just that. They're descriptive. They don't involve generalizing beyond the data that we have in hand. Generalizing from our data is another set of cases referred to inferential statistics. Now, let's take a quick peek here at some outputs from Minitab. So we have a histogram that contains some good information and some data around mean, standard deviation, and nominal measurements. And we also have a variable chart in which we can get a clear understanding of the count, the mean, standard deviation, and variance that has been calculated for this particular set of descriptive statistics. Now we'll take another look at output from Minitab to get a sense for the kinds of data that we're going to look for. We can see data is here at a more granular level. For example, the mean value, the standard deviation. And from here we have what's called a 95% confidence interval. We could say with some assurance that about 66 to 67% of all the data we're going to find in this sample is going to fall plus or minus 1 standard deviation from the middle of our histogram. There are some important things to recognize around what's called inferential statistics. We have the approach, goal, tool or techniques, and interpretations. For example, the description with descriptive statistics is inductive, describing the characteristics. We'll often use histograms, bar charts, measures of central tendency, and it's pretty straightforward and easy to understand. Inferential statistics is a different branch of statistics concerned with drawing conclusions about the population from a sample of the data, and this is usually done through random sampling, followed by inferences made about the central tendency, or any number of other aspects about the distribution. So these are more deductive, infers characteristics, allows us to do hypothesis testing, and tends to be much more complex. Let's take a minute to explore the frequency of distribution in a histogram. The histogram is the type of plot that shows us how data is distributed, showing intervals across the dispersion of the data. It is made up of an x-axis and a y-axis. The y-axis, which runs vertically, defines the denominator, or the value range of what our measurements might be. The x-axis, which runs horizontally, gives us the range, or how many different periods or samples we're going to be taking to include in this dataset. So, for example, by looking at a histogram depicting the number of drop calls per day at a help desk, we would know how many calls were dropped, and be able to look at that series of data for each day. What we look for is a normal frequency or shape of the data, and we'll be looking for a central tendency. We can use this to compare other data to what we have here for two processes. We can also use this to go back and look for changes after we've implemented process improvements after the fact by taking new sample data and repeating the analysis. Now, let's move on to talk about how to actually construct the histogram. It starts with determining what's the frequency that we're likely to understand in the process, in terms of the number or volume of entries, and then who are the operators that are going to be involved in collecting the data. Then we can determine the intervals we want to collect. For example, in a contact center, we could use something such as a form or a template, like a tick sheet. Give it to our operators and say, okay, on Monday keep track of how many calls you had, and each time you had one with any of these issues, just add another tick mark to the sheet for that. Then throughout the 10 days you would allow people to collect the data, and then you would gather that and compile for an analysis. Another option is to set it up in a spreadsheet or put it directly into a table in Minitab, where you might have the time periods that we want to capture on one side, and then you can record the values on the other side of the spreadsheet in a series of columns to understand the data over time. We can then take that data and convert it and use it in tools like Minitab later. Central tendency is a very important aspect that we need to understand when it comes to the behavior of data in its distribution. Central tendency, or more commonly called the measure of central tendency, is that probability distribution we're looking for. It could also be called the center of location of the distribution itself. The most commonly tested content and measures of central tendency are the arithmetic mean, which is the vertical line located in the center of the distribution or curve. Central tendency can be calculated for a finite set of values for a theoretical distribution, such as the normal distribution we'll look for. It's important to remember that the central tendency is a distribution of data typically contrasted with a dispersion of variability. So it's the width of the distribution that gives us an idea for the amount of dispersion we're seeing in our data. Then we can use that to judge whether the data has a strong or weak central tendency based on its dispersion and the general shape of our curve. Histograms can have a range and potential outliers of data that could distort the picture of our study. What this represents is the frequency and distribution of values displayed left to right across this example histogram. By drawing a line connecting the top of each bar in the histogram, we have a visualization of a bell-shaped curve. In this example, we see the slope is fairly even on both sides of the mean, which suggests we don't have a lot of issues with the data, or the process did not appear to have special issues that are skewing the shape, or making one side or the other lumpy on the curve. Let's take a look now at some distribution examples. So in this first curve, we see nothing special is going on. The calculated mean or average value is right there in the middle of our shape. If we look at this next example below it, and we compare these two, we can draw a conclusion. One thing that we can say is that both act normally, and they have a strong central tendency. But this second one has a much narrower range of dispersion across the arc than the first one does. They could have exactly the same mean value, if you will, but the difference is in the range. Now these two histograms on the right represent what we call skewed distribution. In these two examples, we have what is called a positive skew or a negative skew, meaning that the calculated mean or average is to the left or to the right of where the tip of the data might suggest it should exist. Let's examine central tendency and important measures that we need to be concerned about as we look at data and the dispersion of data across the plot. There are three key things that we want to pay attention to. The first is called the mode, which is the most commonly recurring value in the population of measurements that we take. The second one is the median, and the median is the point at which 50% of all of the data is to the left and 50% of all of the data is to the right of that value. So it's right in the middle of the various values that we capture. The mean is simply the division of the total number of observations divided by the number of observations made. What this does is it allows us to get at the average of all of those values that we looked at. So in this example, the highest point of the curve is the mode. The median indicates the point on the x-axis where 50% of the data is to the left and 50% of the data is to the right of that value. The mean is the average of all the values examined. What's interesting in this example is that the curve is asymmetric, with greater dispersion to the right of the mode than to its left. This curve represents an interesting dispersion where the average value is way over to the right, but the most frequent value is actually further over to the left. The most common measure of central tendency is the mean, and this is the one that we'll use quite often as we describe the data. What this does for us is to help quickly see and understand what normal looks like. It's the summation of all the values divided by the number of values. If we look at the formula for calculating the mean, which is x bar is equal to the sum of x divided by n, the mean is the sum of all of the values that we capture divided by the number of observations. An example might be the average handle time for a tech support call coming into a call center. And by comparing that over time, we can compare the mean to the mode and to the median, which would give us lots of clues about the data and how it's behaving compared to a fully central tendency that we might look for. Seeing when these things are different is very instructive about what's going on with the process, and gives us clues about where we want to focus for continuous improvement efforts. Remember, we are solving for the x-bar mean value, derived by adding up our sample values presented by the sum x symbol and dividing by the number of n samples to calculate the mean value. For example, if we weighed the amount of ice cream dipped by hand at the corner ice cream stand, we might see ounce values of 4.5, 5.5, 4, 6, and 5 over 5 successive orders. We add these up to get to a total of 25, divided by 5 measurements, which gets us to a mean value of 5.0 ounces per ice cream scoop. In this topic, we're going to discuss how to calculate the median. The median determines the midpoint of a data set and describes non-normal or skewed data. In other words, it's the point at which half of our data observations are to the left and the other half are to the right. What this helps us to do is to understand and describe non-normal or skewed data in our process. So if we think about our bell-shaped curve, and for example, we have calculated an average value in the middle, but if we did the calculation of our median and found that when we plot it, it's off to the right, then it's the difference between the central line and the plotted median that tells us things about the data that's very, very important. So how do we calculate the median? Well, to do that, data must be ordered and the middle number located. The equation for calculating the median is median equals n plus 1 divided by 2. So it starts with ordering the data, and generally we're going to start with a bunch of random observations. Then we move through and actually order them, descending or ascending order, and from there move through the process of locating the middle number. So there is an important implication here that there is an even number of observations. We're going to have to do a little calculation to come up with the average of that. So basically, we've sorted in order, ascending or descending. We find out if we have an odd number. We can simply look for the value in the middle, but if it's an even number of observations, we're going to need to add the two measures closest to the center and divide them by 2 to get to the answer. So let's take a look at how that works. Let's say that we had 6 values that we listed in order as follows: 8, 10, 12, 15, 19, and 21. Because we have an even number of values, we can't simply pick the middle value. We will calculate it by adding together 12 and 15, the middle 2 values. The product is 27. We divide this by 2 to get 13.5 as the median value for this data set. In this topic, we're going to discuss the mode. The mode is the most commonly occurring value across the population. Or in other words, it's the number that happens most often in a set of observations we've made. It doesn't necessarily represent the center of the data set, and that's instructive all by itself. One interesting thing to remember is that if no value appears more than any other, there is no mode. We also can find that we can have different conditions around the mode. It could actually be bimodal. We can have more than one value, or even trimodal, or even more. Now this is interesting because more than one mode can exist, which isn't a real surprise if you think about mode and how we capture it in the sample of the data that we're using. For example, if you're comparing shift-to-shift kinds of data we're collecting the same data on multiple shifts, it might not be a surprise to see that the mode moves depending on which shift it is. Different things can drive that, like equipment being used, different individuals, different divisions of the company, or different populations that you're gathering the data from. The next way to get at the mode is very simple. We do that by using the histogram, and basically if we just take a look at the actual stack-up of how many observations we have found with a given value, you can spot it very quickly and easily with a histogram. Without the histogram, it's also very simple to get to the mode by simply counting the most common value. So again, we can use the histogram, or we can use simple techniques like just reordering your numbers from the largest to the least, the frequency that it occurred, or we can calculate it using a spreadsheet and a pivot table. or simply sorting the number of times we found a given measurement. The usefulness of the mode for nominal data is that it can often be seen as the only center value by some experts for analysis purposes. Remember, it's the most frequently found value. For example, let's just say you're a retailer. It could be very useful to find out which particular product people would buy the most of in a particular category that you're offering to the market. Let's take a look at actually determining the mode. Let's use an example of the number of garden seeds found in packages opened. Let's say the range on our ranges is from 30 to 36. If we had the following counts recorded, what would be the mode value? The counts are as follows: 30, 34, 32, 33, 34, 35, 33, 36, and 34. What's the mode? By counting how many times each number recurs in the data, we can see we have 34 as the most frequently recurring value with 3. The second most recurring value is 33 with 2. The rest of the values only occurred one time on our data set. This limited data suggests a possible multi-mode condition. If you have a lot of values to consider, you'd want to use a tick sheet, a computer spreadsheet, or quality data software like Minitab. In this topic, we're going to discuss the concept of dispersion and why that's important to us in the practice of statistics and using this for our Six Sigma projects and analysis of data. It starts with getting at understanding central tendency of the data. So is the data tending to look like normal distribution once we can put it in a form of a histogram? Or is it severely skewed left or right? And what's going on with that? From there, we want to understand dispersion. How far does this data stray from the central point that we're looking for? How far out to the left? How far out to the right? The other thing we're interested in is typically within one standard deviation. How much dispersion is in there that would take in 66 to 67% of the entire data population for our project? So let's examine some characteristics of histograms and look at a couple of examples. We can be looking at call handle times for a tech support center. What we could have going on between this comparison here is that this one over here is we could have essentially the same number of observations. We may even have the same mean value at the center, but we could have a big difference in the dispersion between them. So, for example, in this case on the left, here we're handling password resets in a contact center. We've got more automation, maybe an automated IVR kind of system for handling inbound calls. Whereas over here in the histogram on the right, we could be handling a more complex kind of call, where we have to ask more questions. Now, the handle time could be the same in terms of the average handle time, but there could be a much wider range in terms of what it takes. Let's now take a look at more of the understanding around three important measures of dispersion: standard deviation, range, and variance. Standard deviation essentially measures the amount of dispersion from the average, left or right if you will, from the center value in our data. The range is essentially the spread of the data, how far to the left and how far to the right of our central measurement. And the variance, or the variable data that we're looking for, is the square of the standard deviation from that list. This is the numerical value that characterizes for us the difference between the individual measurements in the entire study. In this topic, we're going to talk about range. Getting at and understanding the range of the data is a pretty simple exercise. Range is the difference between the maximum value and the minimum value in a data set. So, for example, if we're looking at a whole range of values that we captured, we could use a spreadsheet or simply search for it and look for what would be the highest value in this data set. We see here that the highest value that was measured was 21, and then we look for the lowest value, and that was 11. So the range for this particular sample is 10. It's the difference between the highest and the lowest value. Now, this is useful data to get a sense for the variation that we're seeing from a target value in our process. For example, Let's just say that we're going to measure the diameter of a turning of a machine. You know, the machining center of some kind. And let's say for the sake of discussion that we want to be plus or minus 10,000ths of an inch from this targeted value. So if we were to compare two different processes and we had a bunch of these values, we found that process A was only varying about 5/10,000ths of an inch for a range of about 5/10,000ths. Then we looked at a different process and we found we were varying plus or minus 50/10,000ths of an inch. We could very quickly say, wait a minute, process A with only a variation range of about 5/10,000ths of an inch apparently is a lot more capable and repeatable than process B, which is plus or minus 50/10,000ths of an inch. There are different uses of range, and there are some limitations that we need to be aware of. First of all, the whole thing is based on just two numbers, that highest and lowest value. And this really only gives us a very limited inference that we can make about the data. Also, the range is very sensitive to outliers, which are data points captured that are well outside of the range. For example, in an IT help desk contact center, a caller may simply call and ask, "Hey, do I hit this button to reset my password?" And the rep answers yes, and the call is over in 10 seconds, even though the average handle time is normally about 5 minutes. Or in the worst scenario, you have a language barrier or a really bad phone connection, and the call takes a half hour or 45 minutes instead of the normal few minutes. These situations could give you some significant outliers. And what that can do is give us some headaches with respect to how we're going to manage the quality of the data and capturing those outliers and managing them. Understanding standard deviation, how we work with it, and the practice of Six Sigma is a critical skill that we need to master. We take a look at normal dispersion of data with the central tendency of the data across the entire chart. We begin to do calculations to understand the sigma values for what this data looks like. We begin to learn some important things. First of all, we would always expect to find 99.97% of all of our data would fall within 3 standard deviations, working from the mean value in our data. Remember, out to the left or out to the right, we'd only expect to find about 3 defects per million opportunities, or some outliers out there to the left or to the right of our data. So we might think about an example of IQ being measured for a population of people. We would expect to find a lot of people at this average value of intelligence. A relatively small number of people on the smarter side, and a really small number out here at the genius grade, or profoundly not so smart out here to the left. Next, we're going to get into what's called the empirical rule, or the 68, 95, 99.7% rule in the practice of Six Sigma. So the empirical rule says that if a population of statistical data has a normal distribution, with a population mean and a standard deviation that's sensible, we can draw some important conclusions. The first important conclusion we can draw is that 68% of the data we're going to find is going to fall within plus or minus 1 standard deviation from our mean. The next important conclusion we can draw is that within 2 standard deviations, about 95% of our data is going to be found. The value is actually found, and finally at plus or minus 3 standard deviations, we're going to find 99.74%. All of the data is going to fall between this plus or minus 3 sigmas from a nominal value. So again, about 95% of everything is going to lie within those 2 standard deviations, and about 99.7% within 3. So this empirical rule is something we use to describe a population rather than a sample. But you can also use it to help us decide whether a sample data came from a normal distribution, if the sample was large enough, and that we can see what this histogram looks like and how close this is to a bell-shaped curve. With this, we can check to see whether the data follows the empirical rule, the 68, 95, 99.7% specifications. If we can say yes to that, it's very reasonable to conclude that the data came from a normal distribution. Let's take a minute to talk about the characteristics of standard distribution. First of all, we only use this to measure dispersion around the mean. The next thing it's important to recognize is that there will always be a positive value to how we express the standard deviation. The reason for that is it's a measure of variation. So we express it as a positive value, even though on a normal distribution graph, you would have -1 sigma or -2 sigma to help show the dispersion around the mean. You also need to remember that it's highly sensitive to outliers. There is a bit of warning here around if we have issues with our data and reliability of the collection method, and we have significant outliers way out to the left or way out to the right of 3 standard deviations that give us some real headaches in understanding the data. And then, of course, greater data spread means we have a higher value to that standard deviation. So in other words, the wider our bell-shaped curve looks, the wider the range of data is going to be inside one given standard deviation of the data. Let's take a look at the key components that go into the calculation of the standard deviation. The formula for standard deviation is that the standard deviation equals the square root of the value found when the sample mean is subtracted from a score in the distribution. This value is squared, and the resulting value is divided by the sample size, -1. Okay, let's go through this. S, or standard deviation, is a product of the square root of this formula. In the formula, we would have the sum of the score within the distribution, subtracting the mean values, converting them to positive values, and the total of that gets squared. Then we have the score within the distribution that we're looking for. We have the number of our mean value within the data, and the product of that is squared, and then we're going to divide that by the sample size, or the number of observations made, -1. What we're doing is we're subtracting that value that we're going to use in the calculation from the total, and that way when we do the square root, this gets us to the number that we're looking for. With this example, we've taken 10 different pieces of pipe, and we've weighed each one. We add these all up and then divide that to get to the average weight per piece, or the mean weight for each of our 10 samples, which works out to be 10.02 ounces. With that, we can then perform the next step. We're going to take the 10.02 and then subtract the actual weight for each sample to get to the differences between the two values in the column titled xi-x bar. We then convert each negative value in the column to a positive value, and square it in the column labeled xi minus x bar squared. The sum of those squared differences is 1.9760. We can then proceed with dividing this by the number 9, which is the number of 10 samples minus 1. That produces the variance of 0.2196. Finally, we get the standard deviation by taking the square root of 0.2196, which is 0.4686. We round that up to the solution of 0.47 for the standard deviation. What's all this mean? Standard deviations aren't good or bad. They are indicators of how spread out your data is. The bigger this number, the wider the dispersion of the data. The smaller it is, the narrower the dispersion of the data is from the mean. The value we got in this example indicates low dispersion. In this topic, we're going to discuss variance. Variance is expressed as the sigma value squared. And this is pretty simple and straightforward at this stage, but we need to recognize that this is something that is not expressed in units of data. It's actually a measure of the variation. The other thing we want to recognize is that this is a very important calculation that's central to our projects, where the objective is to reduce variance. And what we mean by that is our goal is to close the gap, if you will, between where we are today and a target value. For example, if our curve has lots of dispersion in the data, then getting closer to the middle value is something more important to us. What we'd like to do is to make this a much tighter curve, where the desirable outcome is to come up with a lower level of dispersion across the variation of our data. Keep in mind that standard deviation is a measure of dispersion from the mean, and variance is an expression of how much that value is different from the mean and how that's expressed, and how many sigma values it might stray from the mean over time. Let's next talk about explained and unexplained variance. Explained variance measures the proportion of our model, the part of that data that can be accounted for in the dispersion of the data from a given dataset. The unexplained variance breaks that down into two major parts. First, the random variance, which tends to wash out with the aggregation of data. And the second is the unidentified or systemic problems, which can definitely introduce bias to our conclusions. So with random data or random issues with our unexplained variance, this could basically be okay because, again, as we have more and more data we're going to use, let's assume that this will wash itself out and equal out over time. With unidentified systemic issues, though, this can give us some bias issues and could be a problem and something we may need to deal with later as we continue to work with the data. Let's take a look at the components of what goes into calculating variance. Variance is equal to the value found when the sample mean is subtracted from a score in the distribution. This value is squared, and the resulting value is divided by the sample minus 1. In other words, the actual variance measurement, which is squared, is a product of the sum of the score of the distribution, subtracting the mean, the sample mean, and then we square the results. And then that in turn is divided by taking the number of observations and subtracting 1. In this topic, we're going to focus on central tendency and inferential statistics, including different tools you can use. Let's review the attributes associated with normal distribution in our data, which is, by the way, is very common and important to us in the practice of statistics, and natural and social sciences, and certainly within industry as well. What's important to recognize is that most of the values are going to be close to the average within our data set. We would expect that the standard deviation is going to be small, and we would expect this to allow us to easily infer things about the population based on a sample that we've taken. This is very useful in the practice of deductive, descriptive, and inferential statistics. Let's now review the central limit theorem, and the theorem of large numbers, as the case may be. This is very important from the perspective that there are many statistical exercises we may do over time because of these things being in play. The basic tenets of the central limit theorem revolve around the sampling of distribution and the mean approaches of a normal distribution as the sample size number increases over time. Let's take a look at the effect of increasing the sample size and what that does to the shape of the data. So if we look at our example we have here, if you will, a number of samples of 100, and if we take that and we do the calculations, it gives us a curve, which may not tell us a whole lot. But if we increase that sample size now to, say, 500, we can see what this begins to do. When we increase the sample size to 1,000, we can see that this theory of large numbers is in practice. We can see with this example the central limit theorem coming into play. We can see here this beginning to give us what we expected as the sample size gets bigger. Let's take a look at confidence intervals. And not only can we introduce the central limit theorem, we can also apply that to inferential statistics. Remember, we've been talking about measurements used to describe descriptive statistics so far. Here we're going to take a look at the technique used in inferential statistics in the confidence intervals. How we use confidence intervals is to determine at different levels of confidence what that given interval estimate is for the population. It's a test whether a parameter is true, calculated from the observations. So what we want to do is understand what's going on. If we take a look at this data for just a moment, we can see that what we want to know is how reliably can we expect the value to fall within the range at a 95% confidence factor. So in this particular case, we have the data. In other words, the measurement of what was expected to fall between the range of 9.1 and 9.3, and then test that out. We would want to be able to look at the confidence interval and know that working off the mean, what we are getting with this particular process. Statistical and hypothesis testing is an assumption about the population parameter. This assumption may or may not be true. Hypothesis testing refers to the formal procedures that we use to accept or reject statistical hypotheses. The best way to determine whether the statistical hypothesis is true would be to examine this entire population. But that's usually impractical. So typically we're going to examine a random sample from the population and find out if that data is consistent with our statistical hypothesis. If it's not, we can reject it. So, for example, there are two types of hypotheses we can draw. There is the null hypothesis, and then an alternative hypothesis. The null hypothesis is denoted by this H and little o acronym, suggesting that the sample observations resulted as expected purely by chance. With an alternative hypothesis found, this indicates that the samples are influenced by some other random cause. For example, let's suppose we wanted to determine whether a coin was fair and perfectly balanced, resulting in a perfect 50-50 heads and tails results when flipped. A null hypothesis might be that half of the flips will result in heads and half of the flips in tails. But suppose we actually flip the coin 50 times, resulting in 40 heads and just 10 tails. Given this result, we've been inclined to reject the null hypothesis. We'd conclude, based on the evidence, that the coin is probably not fair and evenly balanced. Okay, there's one more inferential statistic tool I want to discuss, and that's the control chart. Control charts are probably one of the more important tools that we use in measuring and providing feedback to organizations about their processes. And this one is loaded with lots of great information that we can leverage. For example, this vertical axis represents the range of measurements that we're likely to find as we're monitoring the measurement, for something typically over a time series, days, weeks, hours, or even by the second depending on the process. And in this horizontal axis, we've got the time periods that we're measuring and paying attention to. We also have what's called the upper control limit and a lower control limit. These are the levels at which we'd be exceeding the design parameters we're looking for. For example, at this level, we'd reject or scrap the part. And at this level, we could rework, fix, or scrap an item. And then we would want to see these points are happening in here that indicate that we have brought this process back under control. Just like a run chart, we're looking for trends in the data. For example, is this average trending upward or trending downwards, signaling big problems with our process? Again, control charts are a very, very easy way to get some great deductive and some inferential statistics from our data. In the practice of examining data, it's important to recognize why we have to have a combination of measures for both central tendency and dispersion to depict the dataset correctly, since using just one measure doesn't really give us all the information we're looking for. So let's take a look at a couple of examples. Here we have 4 different bell-shaped curves. These curves represent the same range but different mean values. With these first 2 charts on the left, we can see 2 data sets with exactly the same mean in the center. However, they're different with respect to range. So these respective data points can spread around and mean different things depending on what we're looking at. The other 2 curves on the right are skewed, one to the right and the other to the left. We have 2 data sets that have exactly the same kind of shape to the overall curve, but we have a different mean. This helps us understand the central tendency and whether or not we're having some skewing effect, negatively or positively, on this population of data. An outlier is an observation point that's distant from the other observations in our dataset. This may be due to variability in the measurement, or it may indicate some kind of experimental error, which we may want to throw out of our dataset. Outliers can occur by chance or in any distribution, and they're often indicative of a measurement error or the population has what's called a heavily tailed distribution. The frequent cause of outliers is a mixture of 2 distributions, which may be 2 distinct subpopulations, or it may indicate an incorrect trial issue versus a measurement error. This is often modeled by what's called a mixture model. If we take a look at the data that we have in this chart, we can understand the impact this has on us when outliers are involved with our data. For example, if we look at the column here representing data with no outliers, we have the mean, the median, the mode, and the standard deviation. But if we include the outliers in the data, look at what it does. It kind of blows up this mean value and the standard deviation, which could actually act to invalidate conclusions and findings from our study. Okay, so now let's talk about the phenomena of skewed data and the importance of median versus mean as we look at our data. For example, if we just use the mean, this is not going to tell us the story about the central tendency of this data set. Using the median is much more helpful to us in understanding what is the central tendency of this data, and is it behaving the way we expect it to. And finally, we get to compare data. For example, we could have a multi-mode effect, where we're having two different modes taking place within our data, versus a data set that has significant outliers out there. So let's just say we're looking at this multimodal data set, and there's many reasons for this to exist. Finding this in the data is very important in the practice of Six Sigma, because we could find out there is a very good reason why we have these two modes, and just knowing that is very, very instructive. So we need to recognize there are limitations to mode. It does not provide a good description of central tendency in all cases, especially when there is more than one mode, or we have significant outliers as we can see here. For some reason, something happened to create a whole bunch of values in this outlier bucket. We don't want to let that destroy the validity and the usefulness of our measurements.